ينفع كده؟
كده.
شوفي كده شوفي كده صح؟ صح توفر لنا كل بس
Good morning, Your Highness, Excellencies, ladies and gentlemen. Hello and welcome to the Future of Semiconductor event. I am Jude Abu Hamid. It is my pleasure to be here today, part of such an incredible event. We have an interesting agenda for you today, focusing on the importance of the semiconductor industry in the kingdom and its plan to promote the digital economy and enhance the development sector. Shedding light on the importance of localizing the electronic chips and the semiconductor industry in the kingdom, anticipating future technologies that the kingdom can play a role in developing. Lastly, highlighting the importance of the research and development support for the semiconductor industry. Now, to start us off for the day, here to introduce the Future of Semiconductor Forum, the Director of Materials Science Research Institute, please welcome Dr. Saeed Al-Shahri.
Assalamu alaikum. Good morning. Your Highness, Prince Salman bin Bandar, Your Excellency, Dr. Munir Dessougi, President of King Abdulaziz City for Science and Technology. Your Excellencies, distinguished participants, guests of honors, ladies and gentlemen. I would like to welcome you all at King Abdulaziz City for Science and Technology for this Future of Semiconductor Forum. and it's my pleasure to acknowledge the joint efforts of Research Development and Innovation Authority, King Abdullah University for Science and Technology, and King Abdulaziz, along with King Abdulaziz for Science and Technology, for the preparation and organization of this forum. I would like also to thank our sponsors for their great contribution. Semiconductors are the heart of technology innovation. The IC chip today power every aspect of our lives. These technologies are transforming our world, forming the basis of vital fields ranging from power, sensors, into information technologies and beyond. So I would say that the semiconductor technologies are the physical foundation of the third and fourth industrial revolutions. Immense international focus is currently on semiconductors, especially after the shortage of the chips due to the pandemic. So the crisis has raised a fundamental question for policymakers, investors, consumers, and researchers. What is the future of semiconductor technologies and manufacturing? The security of semiconductor supply chain has become a national priority in many parts of this world. This forum is well aligned with our Saudi Ambition Vision 2030, where advanced manufacturing and technologies are central focus. Therefore, CACS and KAUST, two leading semiconductors R&D institutions in the kingdom, are organizing this future of semiconductor forum, simulating discussions and building partnerships toward a strategic plan. If localized, this industry will serve the ambition goal of many sectors in the kingdom, including automotive, manufacturing, industry, and defense. The capability we have at KACST are based on human talent. We have more than 30 PhD holders at the field of semiconductors, graduated from the top schools around the world, employing their knowledge in our state-of-the-art clean room, equipped with advanced lab resources of designing, fabrication, and characterization. In this forum, we discuss several technical topics, including beyond Moore's law and 5G communications, photonics and display, automotive and aerospace, and sensors and MEMS. So the goal of this forum is feasible, considering the participation of our distinguished speakers, presenting the latest solutions for smart tools and processes, along with the effective engagement of you all. Now, let me repeat again my sincere hope that this forum will result in success, and with your cooperation will establish a cornerstone of the future of semiconductors, along with a good stay at Riyadh and enjoyable social events. After all, I would like to convey to all of you our gratitude at KACST for your presence toward the success of this meeting. Thank you very much.
Thank you, Dr. Saeed. More with the Vice President for the Research at King Abdullah University for Science and Technology. Please welcome Professor Donald Bradley.
Assalamu alaikum, good morning. Your Highness, Excellencies, honored guests, ladies and gentlemen. My name is Donald Bradley. I'm the Vice President for Research at King Abdullah University of Science and Technology, KAUST. It's my great pleasure to welcome you to this event, the first Future of Semiconductors Forum, on behalf of KAUST, who are co-organizing this forum with KAXT and the Ministry. We especially welcome our many distinguished guests. We particularly welcome Nobel Prize winner Shuji Nakamura. And on a personal note, I would just like to mention that many years ago in 2007, when I was head of the physics department at Imperial College, it was the centenary of Imperial College. And we decided to organize a set of lectures that were called Nobel Lectures in Physics. And they were connected to the 3 Nobel laureates at Imperial College, so Blackett, Thomson, and Abdus Salam. And so we asked Shuji Nakamura to come and give the Thomson Lecture, Nobel Lecture in Physics. Of course, 7 years later, he gave the Nobel Lecture in Physics. And we're delighted to see him here today with us, gracing this particular event. So KAUST started its Future of Semiconductors initiative last year to draw together the many strands of our comprehensive semiconductor research and innovation activities. They span a very wide range of materials, deposition processes, characterization and fabrication techniques, devices and systems, and multiple applications. And many of those activities will be presented today and tomorrow in the meeting. We're truly delighted to partner with KAXT and the Ministry of Communications and IT in the Saudi Semiconductor Program, and to support the growth of new industries in the kingdom. Now, as for many things in life, timing is critical. Timing is critical to success, and we find ourselves today standing at an important juncture in the history of semiconductors with many challenges and opportunities at hand. It really is an ideal moment to think of the future and make plans, which is a focus for this meeting. So Moore's Law is creaking, so time to think of new paradigms. Our reliance on global supply chains has been shaken by COVID, by material shortages, and by an increasingly complex geopolitical environment. Sustainability and circularity are rapidly moving up the semiconductor agenda, and the required energy transition that is needed to avoid climate catastrophe is placing real constraints on how the data-driven digital realm that we increasingly rely on can be equitably delivered to the world as a whole. The Kingdom is rapidly developing a new reality, which is guided by the hugely ambitious Vision 2030 program, and clearly semiconductors are a critical, essential element of this program. So the timing is right. So I wish to thank you all for being here, thank you all for participating in this meeting. And the last thing I would like to do is to say that this is the first Future of Semiconductors Forum, and we very much look forward to welcoming you back to the second Future of Semiconductors Forum, which will take place at KAUST next year. So thank you very much.
Thank you, Professor Donald. With the introduction of the Saudi Semiconductor Program, SSP, please welcome Dr. Yazid Al-Askar.
Assalamu alaikum. Good morning, Your Royal Highness, Your Excellency, honored guests. Semiconductor industry is an industry of more than $500 billion of sales revenue. Not only that, but also bone back of many enabling technologies of the fourth industrial revolution. We're talking about artificial intelligence, talking about robotics, AI, and others. Recently, COVID had showed us how the disruption of this value chain can cause a shortage of chips that will disrupt other technologies and industries. CACS and other universities, research centers in the kingdom, have significant efforts in this field, from state-of-the-art facilities, the clean room in CAUS, the clean room in CACS, and a talent pool of semiconductor experts. Today, under the supervision of the RDI Authority and the execution of CACS, we are starting the Saudi Semiconductor Program to accelerate the RDI activities in semiconductors through improving the research quality, developing the talent pool that can cover the value chain of semiconductors from design, manufacturing, and testing, and also maintaining the national lead in this field. This program will offer access to a set of design tools where the researchers can design their chips, send it to a factory where it can be fabricated, packaged, sent back to the researcher in a very efficient manner. With that, please join me to welcome His Excellency Dr. Munir Dessougi to launch this program.
Thank you, Dr. Munir. Thank you to His Highness Prince Bandar Salman bin Bandar. Thank you, Your Highness and Your Excellencies. Now, it is time for the signing ceremony between King Abdulaziz City for Science and Technology and Saudi Arabian Military Industries. With the President of King Abdulaziz City for Science and Technology, please welcome Dr. Munir Dessougi. And the Chief Technology Officer and Acting VP of Emerging Technologies Division at the Saudi Arabian Military Industries, please welcome Dr. Mohammed Al-Qahtani. Time for the second signing ceremony. Saudi Aramco, the Advanced Electronics Company, and Yokogawa. Here, to tell us about the strain relaxation over full 2-inch substrates and UV emitting devices, the inventor of two-flow MOCVD, the first person to develop Group 3-based high-brightness blue-green LEDs, as well as receiving numerous awards, including the Prince Asturias Award for Technical Scientific Research, the Harvey Award, the Technology and Engineering Amy Award, the National Academy of Television and Arts and Science Award. He is the 2021 Queen Elizabeth Prize winner for Engineering. Please welcome on stage the Nobel Prize winning Professor Shuji Nakamura.
Okay, thanks so much for inviting us today. We came from UCSB. So today I'd like to talk about, at first I talk about UV LED, and next I'd like to talk about the new invention of strain relaxed template. This is totally new technology. So using this new technology, because especially for 3-5 compound, we use heterostructure. Heterostructure means always strain. Using this SRT, we can control the strain. So, yeah. So this is, okay, I don't know, sorry. I don't know how to use. So at first I introduced, so UVC LED team is, Abdullah, Buhan, and other student. So Abdullah, is, he worked for to develop the best N-type aluminum gallium nitride layer. His thesis is N-type aluminum layers. So he, reduced the resistance of the N-type aluminum gallium layer. So we use this best N-type aluminum gallium layer to reduce the voltage, to improve the wall plug efficiency. Also, Buhan developed all kind of UVC LEDs. He's a hard worker. He made a lot of UVC LEDs using silicon carbide substrate. And SR team is a student, basically our students. And the professors are, Steve, Jim Speck, and Mike, and Umesh Mishra. Umesh Mishra worked for the, high power, high frequency electron devices. He's very famous in the United States. Okay. So UVC, UV means UVA, UVB, UVC. So basically, UVC is wavelength is 100 to 280 nanometer, and the UVB is 280 to 315 nanometer, and the UVA is 315 nanometer to 400 nanometer. So we like to now work for mainly for the LED and the laser diode from UVA to C. Especially UVB and UVC is interesting for disinfection of all kinds of virus and bacteria. And example is, right now water purification, mercury lamp is used, but we want to replace UVC LEDs in the future. It doesn't work. Okay. So UVC LEDs are used for the disinfection of the COVID-19. So basically, by irradiating the UVC light, we can destroy the DNA of the virus. And for example, COVID-19, company name Seoul Semiconductors demonstrated the UVC LED to disinfect the COVID-19. You can see that for for example, 10 milliwatt out power, irradiate the size of a coin. 1 second, we can, disinfect all the virus in the coin size using 10 milliwatt LEDs, irradiate the coin size. So most important, we need a high power. For example, 100 milliwatt UVC LEDs, 10 times area of the size. 1 second, we can disinfect all the COVID-19 virus, And this is a history of the germicidal UV irradiation. So basically, since 1930s, they use a mercury lamp to disinfect the virus, bacteria, and purify the waters. And now, 2021, now we are developing the solid-state lighting, UVC LED, also laser diode, to disinfect all of the virus, bacteria, or the purified water. So, for example, now all of the conventional lighting, like incandescent bulb lamp, fluorescent lamp, are replaced by solid-state lighting, white LEDs. So same things should be happen for the UV lighting. So right now, all of the UVC lighting, we use a low pressure mercury lamp, but still this is older traditional vacuum tube type. But now we are developing the LEDs, UVC LEDs. We should replace the conventional mercury lamp. I don't know. Okay. Oh, sorry. So now UVC LEDs are already used for the portable consumer product. For example, for example, the water bottle. Top of the water bottle, they put the UVC LED, and the UVC LEDs are operated by charged battery. Battery is charged, And you use a water bottle for hiking, and you can take the water from the river or somewhere, But the UVC LED irradiate the water, purified water, to disinfect the bacteria or virus. So this is very convenient. Also, for using a portable disinfection system, the mask and iPhone, So this is a comparison of the UV light source. So top is a UVC LED. You can see the yeah. So top is a UVC LED. So problem is wall plug efficiency. First one is wall plug efficiency is only 2 to 5% right now, not so high. But low pressure mercury lamp is efficiency is 30 to 40%, very high. So right now UVC LED is not so good. But the cost, cost UVC LED is $400 per watt. And the low pressure mercury lamp is only $2 per watt, because the mercury lamp efficiency is very high, much cheaper. So that is the reason, not so, not use UVC LED, not so used for the many places. But you can see the visible LED difference of visible LED. This is a white LED or blue LED. Efficiency is 60 to 70%. This is a white LED lighting. And the cost is $1 per watt. Cheaper than the mercury lamp, no? So we can make the high efficient UV LEDs with the overall power efficiency is like 60, 70%. Cost become $1 per watt. So in that case, we can replace all of conventional mercury lamp. So right now, efficiency is 2 to 5%. And now, recently, UCSB achieved the world price is about almost 8 to 10%. So now, recently, world price increased dramatically. So I think we are expecting that in a couple of years, we can achieve the 50 or 60%. So in that case, we can replace all of conventional mercury lamp. So almost there, It doesn't, oh yeah, oh, sorry. Okay, so this is the application of the UVA, BC lighting. So, for UVC is around 250 and 60 nanometer. So you can see applications, the water purification, and also the washer friendly dishwater, and the sterilization, food and medical equipment. And the UVA-B, you can say wavelength is 360 region, 360, 370. Also around between 300, 350. There are many applications for UV-ABC region. But right now, only available light source is the LED. No laser diode as a product, zero. Only LED as a product. Laser diode, we can make laser diode, we can increase the power 1 watt, 2 watt. So we like to develop the laser diode, but right now nobody can make a laser diode as a product. Problem is that everybody uses sapphire substrate to grow gallium nitride, aluminum gallium nitride. So huge number of dislocation density. LED is okay, but no laser diode. But later I talk about using SRT, we can use gallium nitride substrate. So it means that we can reduce the dislocation density dramatically. So we can make laser diode, UV laser diode in the near future. So new technology is very important. So recently, this is 2021. From January, we could increase the UV quick test power of UVC LED dramatically. Just 2021, just 1 year, because we changed the substrate from silicon carbide to sapphire substrate, because aluminum nitride template grown sapphire substrate has been commercially available since 2021. So we switched to the sapphire substrate. So that's the reason, dramatically increase. Also, there are several breakthroughs. P-type superlattice for whole condensation, also active layer, optimization. But the basically big change is that we change the substrate. Oh, I don't know how to. It just, oh yeah. Yeah, so also this shows our peak wall pressure efficiency as a function of the emission wavelengths. So also there are other groups data is plotted. So you can see the circle one is a rectangular shape, yellow and red one is a UCSB result. So recently UCSB is around 290 nanometer region, 280 nanometer region, top 3. Just in 1 year, 2021. Because we are now, dramatically increase world power efficiency. in the UV series around 260 nanometer, we already achieved 4%, 260 nanometer around 4%. So it means 260 nanometer almost top level. You know, so still we are increasing the wall efficiency dramatically. Okay. So this is an example of the EQE and the wall plug efficiency. Just check the wall plug efficiency. The peak wall efficiency is about 8%. Peak EQ is 10%. And the emission wavelength is this one, 280 nanometer. So this is a top 3 result. And so this is the structure of the UVC LED. So basically, N-type layers, also P-type layer, and the middle is active layer. So we need a good N-type layer and a good P-type layer, good active layer. So I told you, good N-type layer developed by, Abdullah. Abdullah thesis is an N-type aluminum galvanized layer. So this shows the, right side. This shows the threading dislocation density as a function of the ear. So also substrate kind of parameter is a substrate. So you can see the annealing is annealing means red one. Annealing means aluminite template grown on sapphire. That one is triangular red one. Is threading dislocation is dramatically recently from around 2020. So that's the reason we switched to the aluminite template grown on sapphire substrate. But still important is the dislocate density is order of 10 to the 8th. 10 to the 8th. 10 to the 8th, we cannot make laser diode, I show, as a product. LED is okay, but laser diode, no way. Too much dislocation density. So this shows the N-type argon layer resistivity of N-type layers or N-type aluminum galvanized layer. You can see lower the better, lower the better. So red circle one is red and blue rectangular shape is UCSB result. So red one is resistivity, lower the better, red triangular, rectangular, and the blue rectangular shape is contact resistance, lower the better. You can see both resistivity and contact resistance lowest among other competitors. UCSB achieved the best N-type argon layers. Thank you for Buhan and Abdullah. Especially Abdullah, his thesis is this work. So they are very, very good. Especially Abdullah is a good worker, and Buhan is a hard worker. No? So thanks so much. Without their help, we couldn't achieve this best result of N-type argon layer. And recently also we proved that P-type layer. P-type layer is another big problem. So initially we used a P-type bulk layer, but recently we use superlattice to use polarization doping. Polarization doping is, later show you. Polarization. So using this one, superlattice, we could increase the EQ. Oh, sorry. Yeah. So using this superlattice, we can increase the EQ word percentage almost 4 times. 4 times. Because we use this superlattice, polarization doping. So basically, this is a C-plane aluminum galvanized. So it means that there is strong phase polarization. Especially aluminum gallium nitride has a strong phase polarization. So, so basically for both sides, plus charge or minus charge, minus charge. So minus charge region, hole accumulate, and plus charge region. This is a valence band structure. So hole is easily activated, and the hole is accumulated, minus charge region. So you can see So effective acceptor ionization energy of the 80% argon is very deep, 400 milli eV. But using this superpolarization doping, effective acceptor ionization is about 40 or 67 milli eV, almost 1/10. So that's the reason we could increase the whole concentration dramatically using polarization doping. This was, first observed by, theoretically observed by Professor Umeshi Mishra, UCSB. Yeah, thank you, Umeshi. Umeshi is still here. He is a very good, device guy. Yeah. Oh, sorry. So also recently we demonstrated high power UV CLDs. This is outpower is 100 milliwatt. So I told you, so this infection of COVID-19, we need high power, so 100 milliwatt. 100 milliwatt means this size, we can irradiate 1 milliwatt LED, irradiate this area. 1 second, we kill all kind of COVID-19 virus. 1 second. And the next is strain relax template, SRT over 20 substrate. So this is the size of substrate determined by the reactor, MOCV reactor. You can use this technology for the 10-inch substrate, 12-inch silicon substrate. Any size, okay. This is a totally new invention. So you can see this technology applies. So basically, we can control the strain because the 3-5 compound, device is a heterostructure. So all the heterostructure has the strain. Strain helps the device power. Sometimes strain is bad. But using flexible SRT layer, we can control all kinds of devices, control strain. Meshes, helmet, and the gallium nitride radar, and the power devices. Also, lasers, UV lasers, any kind of lasers, and the LED, everything. So this technology is for everything, especially for 3-5 compound now grown on silicon substrate, because silicon is used for everywhere. So in this case, 3-5 compound grown on silicon, always huge strain. It's causing a cracking of the bowing. But using this technology, no strain. It's flat. It's a very simple technique. So for strain, for example, this is a strain relaxation method, conventional method. A nanowire, quantum dot, nanocolumn. Also UCSB, Umeshi's group developed the porous gun technology to control the strain relaxation. Also Soitec, company Soitec, also developed the freestanding ingot layer using a smart cut. So using this technology, they can control the strain, but the problem is that this device processing is so complicated. Only tile size 10 micron or Soitec one 300 micron size. It's so complicated process. Students don't want to use this technology. Also, you can see nanocolumn is so nanowire contact, so device process so complicated, But we developed an easy technique. This is I don't know what's here. So you can say enzyme gallium nitride DL. DL is decomposition layer. So enzyme gallium nitride red layer is grown on gun template, and the next we grow high temperature gun. During high temperature gun growth, this ingot layer is decomposed. And the ingot layer shows like an air gap or void. So high temperature gun becomes almost, thin flexible layer. And high temperature gun layer, we grow, also ingot buffer. So this 300 meter 4% ingot is fully relaxed, no strain. And the quantum well same. So different sample is no DL, lower one is no DL. That is a conventional method. In that case, ingot layer has a huge compressive strain. Whoa. Oh, sorry. So using this technique, we grow this 294% ingot on high temperature gun. So you can see that ingot DL layer is decomposed, and using TM, you can see the void, and the indium and the gallium metal after decomposing the ingot layer. And on the ingot, decomposed ingot layer, there's a gallium nitride high temperature gun and 200 nanometer 4% gun. So 4% indium gallium nitride is relaxed, in this case 85%. X-ray, no, relax. So strain is 85% relaxed. So now we can relaxation control 100%, 150%, up to 150% we can relax the strain. And for example, when we grow the, so right side we grow the magic quantum well on using a decomposed ingot DL layer. So left side is a reference sample, no DL, no decomposed DL, just a conventional method. So conventional MQ, both samples are co-loaded and just grew the ingot magic quantum well. So conventional method is blue emission, photoluminescence blue emission, but the right side is green emission. So right side using the relax technology, 75 meter rate shifted. So it means that MQW has a much higher indium composition. It's called the composition pulling effect, decrease of the composition pulling effect. So if strain is high, compressive strain, ingot has a compressive strain, indium corporation is very small. But using a relaxed ingot, we can increase the indium corporation a lot. So that's the reason green emission. So using this technology, we can demonstrate the red LEDs. So amazing thing is that usually to make a red LEDs, active layer of the MQW is grown around 750 degrees. But using this technology, we could increase the gross temperature up to 870. We can make green, red LEDs using high gross temperature of 870. So this is one example. And we can demonstrate very good red LEDs. I want to skip this one. So these are, right now, this shows the LED display. So tomorrow, Professor Steve must talk about micro LED, I guess. So right now, micro LED, the biggest problem is red LED. When we make a small chip size, using micron size LED, we can make the display for smartphone, also AR, VR. It's called the micro LED display. So in that case, biggest problem, red LEDs. Currently, red LED means we use aluminum indium gallium phosphide LEDs. But the chip size become micron size. EQ is efficiency is almost less than 1%. But nitride, indium gallium nitride based red LED, green, blue LEDs, even for the chip size become micron size, still efficiency more than 1%, 2%, so even for red LED. So that's the reason we have to develop indium gallium nitride based red LEDs. So this is a comparison of our SRT red LEDs, top one. You can see, and others are, conventional strained red LED, ingot strained red LEDs, conventional method. So conventional method, ingot MQW, huge compressive strain. But using SRT, relax ingot MQW, so we can minimize strain. So in that case, emission rate is very long, 647. And the EQ is, this is on wafer, no package. So in that case, 0.4%. After packaging, almost 10 times increase the EQ. So you can see these are very good result. Also, another big thing is voltage relatively small. So next I talk about the UVA laser diode, UVA laser diode. So 355 nanometer laser diode. So we need, I told you, right now, no UV laser diode as a product, only research report, because due to the huge number, dislocate density. So right now, several groups reported a 355 nanometer laser diode using sapphire substrate, using sapphire. The problem is they have to use, for cladding layer, they use 20% argon layer, 20% argon layer. So that's the reason. Because they use the gallium nitride substrate, always cracking happen due to the huge lattice mismatch between gallium nitride and 20% argon, cracking. That's the reason they have to use sapphire substrate. you can see dislocated still, to reduce the dislocated density, they use epitaxial lateral bagels, but still dislocated density is the order of 10 to the 8th. 10 to the 8th, no, 2 times 10 to the 8th. But using a right side, using SRT, I told you, strain reduced temperature technology, we can use the gallium nitride substrate. Gallium nitride substrate dislocated density is less than 10 to the 6th. So it means even for, we can make the 20-30% alga layer, dislocated density is less than 10 to the 6th. So left side, you can raise the lifetime as a function of the dislocation density. If dislocation density is 10 to the 8th, lifetime of laser diodes is only 100 hours. 100 hours. But dislocation density is less than 10 to the 6th. Lifetime is more than 10,000 hours. So that's the reason currently all laser diodes are grown using gallium nitride substrates in order to improve the lifetime. So, but UV laser diode research results, every have to use sapphire substrate due to cracking problem. But using a new invention of SRT, we can use the gallium nitride substrate. So we can make the best laser diodes in the near future. So, so the method novel strain relaxed temperature method to produce relaxed ingot buffer on full 2-inch substrate. This is a reactor size. We can use a 10-inch, 15-inch silicon substrate, no problem. And demonstrate LED as one example. But also, we like to use this for the UVA at first, next is UVB and UVC, using gallium nitride substrate to make real laser diode as a product. Thank you, that's all. Okay, nothing. That's it? Okay, thank you.
Professor Nakamura, please stay seated on stage. You could stay seated on stage. Thank you, Professor Nakamura. Take a seat on the stage.
Good morning, Your Highness, honorable guests. My name is Thomas Antopoulos. I'm a professor of material science and engineering in KAUST, and what we will do today, afterwards, we will have a small so we will move with the to the panel discussion, and I would like to invite to the panel VPR of KAUST, Professor Donald Bradley. Also, we have Professor Yazid Alaskar from KAXT, and Mr. Fahad Al-Suleimani from the Ministry of Investment. Please join me in the panel. So, So welcome. I would like also to take the opportunity to thank our guests, our hosts here at KAXT, for organizing such a beautiful venue with a microprocessor podium. I haven't seen this before. It's really, really nice. So I have prepared a few questions that I would like to ask you. Perhaps we will start with the ministry. I think it has one of the most, the biggest gravity in the kingdom, and will define a lot that is to be, will be happening in the area of semiconductors in the country. So there's been a lot of talk about semiconductors. Is a reason why we're here. Semiconductors have been on the spotlight for the past few years, the shortage in microchips, the damage the shortage has inflicted in industries, especially automotive industry. But reading articles from experts, this shortage was not caused by the pandemic. It was foreseen in a way. simply because of the demand for electronic semiconductor components, it's been increasing, and the semiconductor component in electronic items has been increasing as well. So we've seen also recently very important announcement from the kingdom. We've seen the unveiling of the first Saudi-made, of course, smart chip. We also, last month alone, we had, of course, the announcement of the Aramco and Japan's Yokogawa that we are also present here of the localization chip manufacturing in Saudi Arabia. So my first question is that does the ministry consider semiconductors a strategic area for future investments in the tech industry? And being here, of course, that most likely is a yes, I would imagine. But what are the short-term and long-term, I would say, plans for investing in semiconductors, both in relation to what's already been announced, but also perhaps if you can tell us what is to come in the near future?
Well, thank you first, Dr. Thomas. I'd like to thank everyone and Their Highness for hosting this here in CAST. It's definitely imperative for Saudi Arabia to understand the semiconductor industry and as well as the supply chain that comes along with it, the value chain. We have to understand the business opportunities that are brought to Saudi through this supply chain of semiconductors. First, allow me to kind of elaborate a little bit about the mandate of the Ministry of Investment. So the Ministry of Investment mandated to develop businesses and attract businesses to Saudi Arabia through foreign direct investment or through domestic direct investment. And both of those can be done through either joint ventures or partnerships between the public and the private sector. There are a lot of deputyships under the Ministry of Investment, and I think definitely we have to go through some of them. I'd like to just touch upon a few of them. We have the Investor Relations and Advisory that takes care of the investors and their journey through setting up shop here in Saudi Arabia, as well as helping them with all of the admin needs in terms of the visas and what have you. All of that can be facilitated through the ministry. As well as we have the Financial Transactions Deputyship, which takes care of studying the financial plans, studying a lot of the IRRs and what have you in terms of the financials to incentivize some of these companies that are strategic to come to Saudi Arabia. Definitely incentivizing needs a kind of a long study with the companies and understanding their business plan and their business model to bring them here into Saudi. So from our end, I think let me also talk about what I do in the Ministry of Investment. I am part of the Business Development Deputyship, and the purpose is to develop the business, and that, like I mentioned previously, accounts for the supply chain, the value chain, developing the ecosystem, bringing the talents, understanding the talents need in the market. So let me kind of give you a short answer for the short terms and the long term kind of plans for Saudi Arabia through the Ministry of Investment. We are currently meeting with a multitude of companies that are the global leaders in terms of the semiconductors. We're talking about design houses such as ARM, Intel, AMD, all of the different companies that are leading in design. We're talking with foundries. We're talking with the big names that you see everywhere in terms of the manufacturing. We're talking with different kinds of companies that are participating in the supply chain just to localize this industry here into Saudi Arabia. To localize it, we have to understand also the moving targets, the viability of the industry. We don't want to open a capacity for industry in Saudi Arabia without having a full understanding of the ecosystem and as well as what it impacts around the world. As for the long term, I think definitely we have to keep an eye for the moving targets and as well as the obsolescence. We don't want to bring a technology that can become obsolete within the next decade. It is a long discussion, and I think definitely we can get into it at a certain point.
Absolutely, thank you. That's really, really important information. Which brings me to my next question, which relates to emerging technologies. a lot of has been done about established technologies, especially when we talk about semiconductor. We had Professor Nakamura talking about the latest developments, light emitting diodes based on inorganics. I come from the area of emerging semiconductors for quite some years now. I don't know if we can call them emerging, like printable, soluble semiconductors and the industry that's being created right now. These are emerging, and a lot of these technologies are new opportunities for especially investment. We mentioned a few companies, but we also have, for example, Pragmatic here, Richard Price from UK, I know for a long time. This is one of the leaders in flexible microprocessors manufacturing, using a completely new kind of settings, infrastructure, but at the same time aligned with existing design tools and everything. Is the ministry considering such emerging technologies as potential opportunities for long-term investment?
Absolutely. I definitely think we have to understand that emerging technologies and traditional technologies are both fundamental today in our life. And whatever is emerging today, tomorrow is going to be one of the traditional kind of technologies. And for us in the Ministry of Investment, we encourage these companies to come set up here in Saudi Arabia, meet up with the local institutes such as KAUST and KAXT and the different institutes here to develop their technologies even further. And we can support in the matchmaking, the establishment, and having said that, we allowed technology into our lives, and we integrated them in our lives. We are surrounded by smart things, and I don't think a lot of us can go through the day without relying on their smartphones or smart devices, their wearable devices. Printable integrated circuits definitely is one of the important things that we have to consider today when we are talking about the personal fitness as well. There are a lot of applications for printable electronics. In keeping up with your posture, you want to understand your daily habits. All of this can be facilitated easier if it's integrated within your clothing. You don't want it to be devices connected to your device to your body and walk around bulky. So this is enabled by companies such as Pragmatic and different companies. We're looking at also different companies, for example, from Japan, that has a similar technology that is supports sensitivity in sponge, for example. You can walk on these sensors and it gives you a result of your posture, your walking habits, and how to fix it as well. So all of this, all of these things are absolutely under the livability, and livability is one of the things that we have as a focus under the vision of 2030.
Yeah. That's great. I can personally see a lot of opportunities there, and it's very encouraging to see that a lot of our visions are kind of aligned. Which brings me to the other question, perhaps to Professor Yazidi, if I may. Donald, you will have to wait for a few minutes. And relates to KAUST, what organizations like universities at the leading edge of research like KAUST, together with R&D places like KAXT, can do to help the various governmental bodies, ministries, investment, and not only to enable more things to happen. From, of course, very accurate, I will say, advice and consultation, to really facilitating more. Essentially, I believe in exponential growth when people talk to each other. And what can we do as KAUST and KAXT to assist with that effort?
Sure, thanks, Thomas. So in order to foster the R&D ecosystem, we need to have the right enablement. And when we talk about enablement, we're talking about facilities, talking about human talent, and basically aligning the RDI activities toward the national need. Making everything aligned toward one goal. We cannot do everything at the same time. At KAUST, we like to have state-of-art facilities related to semiconductors. We just launched here the clean room at KAUST. KAUST also, they have state-of-the-art clean room. Easing the access of these facilities and make it available for researchers, not only in these universities, but in all universities and for all researchers in the kingdom, will definitely will accelerate the research in this area. Not only that, but also since this industry is capital intensive, so we don't see like many universities have these programs of semiconductors. Opening these facilities to other universities where they can build on it and establish academic programs that can generate good talent, that can support the RDI activities in this, definitely will accelerate the efforts for this. And this is what we plan to do. We're happy to open these facilities at subsidized fees for researchers, and also train the talents that is needed to have a very healthy RDI ecosystem in the kingdom. Definitely, I mean, when you talk about R&D, it's very, very important to have a very solid R&D community in order to attract the right investments. We need to have a competitive advantage. So this will complement definitely any efforts that need to be done with attracting investments. It's still in the beginning, and I think once we start, this will become very mature, and we'll have more going into this direction.
That's a very important point you raised there. I think the talent, it appears to be an issue even for developed economies, you know, countries that have a tradition in high-tech industry and is still struggling to identify enough talent to supplement their activities. So I think that's an important point that would need to be addressed. And I think this is where KAUST and KAUST can come in, train the young and ambitious scientists, engineers, and essentially kind of complete this ecosystem that it would be needed in the long run. Yeah. Another question I have is about KAUST's vision in the area of semiconductors. We heard already about initiatives, and I will tell you why I'm asking this, because we at KAUST, we start really discussing about that maybe a year and a half ago, simply because we're not doing enough in semiconductors. We're doing a lot in semiconductors, but it's not as glamorous or as used to as other things, like doing bio electronics, for instance, or something more with a kind of comes with a more fancy title. But semiconductors are in the. Is this a kind of a reaction to perhaps what's happening around us, or it was a kind of a vision that predated the pandemic, at least with KAUST? I would like to know.
It's a combination of both. Okay, we at KAUST we started this effort in the semiconductors long time ago, and as a result that we have a clean room built now, very capital intensive facilities. It was not easy decision to invest all that money long time ago without foreseeing what's coming in the coming future, and also developing the right talent. We have at KAUST we have more than 25 PhDs working in this field, graduated from top-tier universities. So definitely that was, this was started like a few years back. However, with what's happening right now with the COVID and the disruption of the supply chain, and this brought also a sense of urgency. This is a shock. This is okay. It's and it's not a normal industry. It's an industry that also related to national security. Many other industries depending on this industry. We need to act faster, and as a result, today the Saudi Semiconductor program was launched to accelerate this effort to make it also more, to make the resources more available to all researchers, not only CACST, but all researchers interested in the kingdom, lowering the barrier to enter this area as a student, as a researcher, having more of talent pool in the coming future, basically to build an industry around this.
Thank you. I think we are on the same page on this, and I believe that I believe also in miracles myself. I believe in technology. Professor Suji Nakamura's talk is very inspiring because I use it in my lectures. The case of gallium nitride LEDs, a technology that a lot of it was known, but it took a few key developments to change a technology which was hundreds of years old, you know, the incandescent light bulb.
Right.
And that's nothing short of a revolution in science. And we don't see often this happening.
True.
And that was one very example, which was a fundamental discovery, and that led a chain of events. And I think we should be expecting such developments in the future, and why not in the kingdom? So not just to follow, but to lead at some point is very important, and creating the foundation for this will be critical. And I think this is the role of institutes like CACST, and a lot of other universities. But we need to create the connections and amplify the impact. That brings me to you, Donald. Sorry for leaving you at the end. I want to ask you, as a pioneer, you're a pioneer in light-emitting process in conjugated polymers. And yesterday, during the fantastic dinner that we had, you were showing Professor Nakamura some of your photos. And I was wondering whether you mentioned to him that it was an organic light-emitting diode, your display. An inventor of electroluminescence in conjugated polymers, an inventor of inorganic gallium nitride-based LED technologies. So what I would like to ask you is your point of view, coming from this emerging semiconductor side of semiconductors and the current situation. What is KAUST's angle? We discussed this a lot together and with colleagues at KAUST, but it would be nice to share our kind of views, perhaps, what is to happen.
So Thomas always asks very simple and straightforward questions.
Sorry about that.
So thank you, Thomas. So I think KAUST is a university that has a lot of expertise in semiconductors, and that expertise runs through many different material systems, many different processing regimes. There's a lot of very strong capabilities in characterization. There are lots of people working on a wide variety of devices, and then applications, many different applications. So I think one of the reasons why we were interested in the future of semiconductors as an initiative and the forum that has been established to work with CACST and ministries is that it's very important also to have some broad ideas of topics that you can bring people together. So, I can work on my semiconductors, organic semiconductors, quite happily. I can improve some parameters of those materials. I can think about making slightly different device types. I can stay in my own comfort zone. But I think often real developments, changes, inspiring activity comes from bringing people together who have come from different backgrounds, have different sets of knowledge, different expertise, and asking them to try and address some very specific questions. Defining those questions is obviously challenging. You have to think quite carefully about that. But I think we are at a time where some of those questions need to be asked and answered. We are seeing some of the traditional paradigms changing. We are seeing new paradigms coming into existence. And that's happening everywhere. I mean, I personally have worked a lot in the display sector. We've seen big changes in displays. I'm old enough to remember cathode ray tube TVs. Now, the thing about cathode ray tube TVs is they could never be too big, just because they were too heavy and bulky and everything else. We moved to flat panel displays, originally using liquid crystal systems. And today we now have organic light emitting diodes as a very key component of display technologies. But actually we have a lot of other things happening at the same time. So we're seeing people working on quantum dot displays. Sometimes they're hybrids between liquid crystal using the quantum dot as a fluorescent filter. We have people trying to use the quantum dots as the semiconductor element in an LED. We have people looking at completely different ways of processing. The integration can prove very difficult, and I think it's interesting today to look at whether some of the changes in processing make that integration slightly more easy. We have to work on the compatibilities. There are many things that we need to understand. But I think challenging ourselves is key to making those advances. I think also challenging ourselves to think about different application opportunities. So we heard Shuji Nakamura talking about using UV light for sterilization to address microbes and bacteria. We think that there are many other opportunities that can be developed in terms of life science. KAUST sits on the Red Sea. The Red Sea is increasingly important for the kingdom in terms of thinking about how to develop new industry, tourist-based opportunities, the giga projects in Neom and at Amala and the Red Sea development. And there are many ways in which we can think of complementing and enhancing that development through the use of semiconductors. So we have groups that are looking at underwater communications. We have groups that are looking at sensors that can be used as a tag to put onto a turtle, for instance, and collect data as that turtle is swimming around. So not only do we have the Internet of Things, we have the Internet of underwater things. And I think those sorts of challenges can really help us to identify new ways of doing technology, new ways of thinking about how to use it. I think also we have to think a little bit more about sustainability, about circularity. So we have all of these devices. Where do they go when we stop using them? What is done to reclaim the precious metals, the components of those devices? What are we doing to make sure that semiconductors are a sustainable technology for the future?
And Donald, allow me to interrupt you here. That's very important when we talk about emerging technologies, which directly relate to high volume manufacturing. Where all these things will end up, how are they going to be managed? Right now, only now, really, we start discussing the circularity of the electronics. So, yep.
Yeah, so I think these are some of the things that we will be looking to address, and we very much will be looking to address that in collaboration with our partners in the kingdom, with KAUST, with the ministry, identifying some key projects that we can work on together to train new skills, to bring together the skills that we have, I think will be a critical component of how this semiconductor program can advance and deliver real results for the kingdom.
Thank you, Donald. And I would like to thank you all for participating in the audience. Thank you very much for your attention. Thank you again.
Thank you.
Thank you. Thank you. Thank you.
Thank you, Professor Donald. Thank you, Dr. Yazid. Thank you, Professor Thomas. And thank you, Mr. Fahad. And it is currently time for the coffee break and the poster session with the students of King Abdulaziz City of Science and Technology and King Abdullah University for Science and Technology students. We'll see you all back here in 30 minutes. please. Okay. Hello. Hello and welcome back. It is time for our technical discussion, more and beyond more. His research work on submicron transistor reliability won the Best Thesis Award by the French National Scientific Research Center. He is the chairman of the Electronics Division, the Alliance of Electronics and IT Companies in Egypt. Please welcome on stage Professor Hisham Haddad. He is the SI Wired System. He is the chairman of SI Wired Systems, here to talk about the innovation, semiconductor, and the future.
Bismillah ar-Rahman ar-Rahim. So I'd like to begin by thanking the organizers for giving me this opportunity to address this audience. So my talk today will be addressing actually several points. I will be talking about Moore's law, more than Moore, and then I'll talk about a strategic overview for the semiconductor industry in the region. Maybe I'll be focusing on Egypt, but everything applies to the region. So if you look back to the history, there are three very important milestones. And in 1959, as you all know, the integrated circuit was invented in the US. And since then, this has led to what we call the knowledge revolution. And it has been the foundation of the knowledge economy later. So if we think about the technologies that have had significant impact on humanity, like the internet, like wireless phones, like all these technologies, without the integrated circuits, none of that would have been possible. As I said, I will be talking about several things, and they are linked together, actually. I'm not sure why is this. Okay. So I'm trying to link all these things which are not really linked together through a journey of a lifetime, actually my lifetime, which is insignificant, but actually it relates these topics together. I started 40 years ago as a soldier working to extend the life of Moore's law. So I've been working on reliability and aging of transistors, and at that time we were working on, which was state-of-the-art actually at that time, 3 micron MOS transistors. Today we have 3 nanometers, so it is like downscaling of 1,000 times in 4 decades actually. Then maybe a decade or so later, I moved to the industry, and I actually, when I started doing something in the business world, I found that more than more is much more interesting, actually. More than more is very rich in terms of innovation and opportunity. Then later in my lifetime, I became interested in innovation as a strategy for sustainable development. And as you will see, the electronics industry, and in particular the semiconductor industry, is one of the most innovative industries in the world, and it has been the driving force of the world economy for so many years. So as you see, all these things, I have done them on an individual level and at a macro level in later years, and I'll be talking about them through my slides. So what's innovation actually? Innovation is not just an interesting idea that anybody comes with. Innovation has a formal definition. It is the transformation of technology and knowledge into economic value. So if you have the brightest idea and it doesn't get transformed into a product or a service and it doesn't develop into an economic benefit, then this is not innovation. Innovation is not an invention. It could be something actually not even novel on a global scale, but novel in a regional sense. So people who study innovation, they divide innovation into two categories. Small I innovation, which is the application of knowledge, like, for example, digitalization. Like if you bring digital technology to a sector, a traditional sector like transportation and logistics, this is small I innovation. Big I innovation is the innovation based on R&D and deep tech. So innovation is the best strategy as we speak for economic development. Thanks to Moore's law, the semiconductors industry is the biggest innovation-based industry in the world. So innovation is the foundation of knowledge economy for you who are interested in strategy and the macro level. So actually Moore's law has been really responsible for this nature of the semiconductor industry, which has been driving innovation for 6 decades. So Gordon Moore predicted he was the founder of Intel, one of the founders of Intel, and almost 60 years ago, he predicted that the number of the transistor count per specific area will double every 2 years or every 18 months at that time. This was not a physical law, and it might not have been a valid law, but people made it valid. People worked to make it happen. So people worked hard to make this law happen. It's not a physical law. It's just an empirical. It's an observation that he did. So today we have, because of this, when you have continuous increase in functionality and performance by doubling the transistor count, and you have that for a specific fixed silicon area, then you have more value for the same amount of dollars. And this is transforming technology, as I just mentioned, transforming technology into economic value. This is innovation. So Moore's law has been driving innovation for 60 years. Sustainable innovation, continuous opportunities, and unprecedented growth. So, as I mentioned to you when I started in my early years, actually I used to fabricate transistors myself in the clean room, and we did, as I mentioned, 3-micron transistors 40 years ago. Today, the transistors that we have today are in the 3-nanometer state-of-the-art processes, and the chip, this is an Apple chip, not the most recent, by the way. The most recent is a 3-nanometer node, I believe. But this is the Apple M1 chip. And you have on the chip 50 billion transistors. The first integrated circuit had 1 transistor in 59. Now we have 50 billion transistors on this chip. So modern chips can do a lot of things. They can sense the surroundings, they can store data, they can compute, think, decide, and act. Unfortunately for Moore, and maybe for the world economy, Moore's law didn't go in a linear fashion as he predicted. Started slowing down due to lots of problems. And actually, even in the very old days, people thought that Moore's law was coming to an end. When I did my PhD thesis, we were talking about ballistic transport and hot electron effects, and people thought that this was the end of Moore's law because we're talking about sub-1 micron transistors, which was very small at that time. Now, we know that this is not the case. So people worked hard to make Moore's law sustainable. However, this came at a cost. a cost of a huge economic cost. Today, if you want to build a fab that does state-of-the-art technology, you have to pour billions of dollars into that fab. And the machines, they have to be upgraded and updated on a yearly basis for tens of or hundreds of millions of dollars. So it's very costly to build state-of-the-art fabs that does microprocessors with these kind of features that I've just shown. So what happens going forward? Today we're talking about nanoelectronics. It's not microelectronics anymore, and this has been, I mean, for maybe a decade or more. So what happens next? More downscaling, or beyond CMOS, looking to something else to replace CMOS, a new technology. But to replace CMOS, this is a very, very difficult task, because CMOS has been a very faithful servant for the electronics and semiconductor industry. CMOS is a scalable technology. So not only you have to find a technology that is mature and robust, but it has to be scalable, and it has to go down into the atomic scale, and this is not easy. So beyond CMOS and nanotechnology, finding disruptive functions and devices that could replace CMOS is not for the near future, although people are working hard to make this happen. The last or third alternative is more than more. Remember that from an economic point of view, it's all about adding value. So what Moore's law provides is adding value, shrinking the chip, or having the same area but adding more transistors. This means more functionality and also higher performance, because shorter transistors have higher performance in terms of frequency. So this means adding value. So this is what Moore's law have been doing for the last 60 years. Every year, every 2 years, you would go to a new node and you would have in your hand a handset or a portable device that has an enhanced performance for the same cost. So this is innovation, actually. This is the definition of innovation. Without even having or putting on the table all the bright ideas and applications that people come up with based on these new technologies, the mere fact that you are introducing more transistors, more functionality, and higher performance, this is continuous innovation, and this has been driving the world economy for 6 decades. So finding a new technology that could do the same is not an easy task. But what does more than more offer? It offers the same thing. It offers additional functionality, additional performance, but not by continuously shrinking the chip, by adding other functionality through adding other technologies in the same package. Not necessarily, we're not really bound to have everything on the same chip. So silicon in package is now the most important technology that has been developing in the last few years, or I'd say more than a decade now. So silicon in package is now a much more developed technology than it was maybe 2 decades ago. So you can put, and 3D integration, all these technologies together with accumulating MEMS, RF, power, and everything in a single package. This does potentially the same thing that Moore's law has been doing during the last 6 decades. So if we take a look at the 3 alternatives in a little bit more depth, not that deep, but I'd like to go through them one by one. So more is still going on, and people predict that it will go for maybe 10 years. Remember that we're coming close to the dimension of the atom. The atom is like 0.1 nanometer in terms of diameter, or something like that. Now we are at 5.3 nanometers, so we're approaching physical limits. The most important thing that has been challenging for more, and I will see the challenges here, I will show the challenges here, is power. Actually, dissipating the heat that is generated on a chip is the most challenging thing today for continuous reduction of shrinking the feature size of the transistors. Not finding new transistors. People have been very imaginative about finding new transistors and new architectures and things like that. But there are physical limits. You cannot dissipate. In order to dissipate the generated heat, you need to have a big surface area, or you need to have some cooling or something like that. So it's very challenging to handle the dissipated, to handle the generated power and dissipate the heat generated. However, the most important, the biggest challenge, even bigger than that, is the cost. It has becoming, as I mentioned, very costly, and it takes more time, as you have seen, that if we look at Moore's law as a train, it's kind of slowing down. And to make it go farther and farther, you have to pour billions and billions and billions of dollars. So it's not suitable anymore for any kind of chips. It's only suitable for chips that have very high volume production, microprocessors, memories, and SoCs, which are very high volume in demand. So as you see, the end of Moore's law is always 10 years away, and yes, it is still 10 years away. And I've been, as I mentioned, as I said to you, since I've been doing my master's in 81, this has been the case with Moore's law. Moore's law is going to die and things like that, and it has really delivered for 6 decades. So beyond CMOS, this is the playground of nanotechnology, actually, and there are lots of efforts, people trying to find the replacement for CMOS, which is a very, very difficult task, because as I said, CMOS is a very reliable technology, and it's a technology that is scalable. So the question is how to really replace something like that, something that could take us to the next 2, 3, 4 decades, like CMOS has done for 6 decades. It's not an easy thing. So there are lots of technologies and materials and nanotubes, nanowires, nanodots, molecular state devices, spin orientation devices. However, all these are still very far from being mature and scalable replacement for CMOS. So here comes my favorite. As I told you, when I moved from, like in the early 90s, 30 years ago, I moved to industry. I have been a professor at the university doing research. I moved to industry, and I came across MEMS, and I loved MEMS, and more than more in general. So more than more is you put many technologies together and build an intelligent system. And this is at the foundation of everything smart that we hear about today. Smart manufacturing, smart agriculture, smart farming, precision agriculture, smart homes, everything. It has applications in everything. So you have to put all these technologies in a package, which is not easy. It's not really something simple. It's something that could still take us for years, driving the economy and adding value and enabling innovation. But as I mentioned, it requires a lot of innovation in terms of packaging and 3D integration and other technologies. So this is what a smart system would look like. It's a combination of more, and more than more. So here we have more. It's a digital SoC with memory, and so potentially a microprocessor, a memory, and software. And on the right side, the other part of the system is more than more, where you have maybe sensing, communication, and actuation. So all this is more than more. And today, systems are hybrid. So you combine CMOS with more than more, and you get what we call smart systems. I'm moving now to another phase of my life, which is a more than more company that I have founded with a couple of my colleagues. That was 20 years ago. So this company is called Cyber Systems. It's the first company actually in Egypt doing Semiconductors. Now, I'm proud that it's a company that is becoming global, and I will take you through what we have done to make this company more valuable, actually. So I'll be focusing on a specific technology and a specific product, which is today protected by more than 80 US and international patents. It's a more than more system, which is a spectral sensor. I'm not sure if you're all familiar with spectroscopy and spectrometers. So a spectrometer is traditionally a benchtop device, benchtop instrument, which is bulky, expensive, and it's used to analyze materials by virtue of identifying their spectral print. So each material, like each human being has a unique fingerprint. Each material has a unique spectral print. So each material absorbs certain wavelengths. And if you detect this pattern, what are the wavelengths and the proportion of absorptions that this material absorbs, then you can identify the material and its exact composition. So spectrometers have been around for decades, and they are used in all applications across the board. Medical analysis, like when you analyze blood, urine, anything like that. Soil analysis in agriculture, and feed analysis in farming, pharmaceuticals. So it's in every industry. Spectrometers are everywhere. So what we have done is this bulky desktop instrument, which costs $100,000, $50,000, depending on its accuracy, we've put it on a single chip. And this has been the smallest spectrometer in the world. So this is a more than more example by excellence. As you see here, this is the architecture of the core module, which we call the OCM, the optical core module. And on the right here, you see someone holding it in between two fingers. So it's a very small module. Actually, it's a package. And inside this package, you have like 20-something component. Two chips, actually, one digital and one analog, ASICs. And you have a MEMS, which is the heart of the spectrometer. It's the interferometer itself. And you have passive optics, and you have many other things. And of course, you have a photodetector. And then you have a glass lid. So the key features of this spectrometer, which we coined a new name for a spectrometer, we named it spectral sensors. And we were the first company to put this name in public. And now people are talking about spectral sensors, and there are competing technologies to what we have. But fortunately, till now, we have the best performance and the best kind of integration and the lowest cost, actually. So it's very highly integrated in terms of form factor. And it's very, very cheap compared to a lab spectrometer, which could be selling for tens of thousands of dollars. I mentioned here the cost is tens of dollars. It has a wide spectral range. The wider that you have in terms of spectral range, the more materials you can identify. So this operates in the near-infrared spectral range, but can be extended, and actually we did extend it to the mid-infrared. In the near-infrared, you test a lot of liquids and solids. In the mid-infrared, you can test gases, which is totally different applications, and it has applications mid-infrared in defense, environment, and all kinds of bio warfare, environmental applications, things like that. Today, we're focusing on the near-infrared with applications that we're targeting precision agriculture, smart farming, and healthcare in the near-infrared. So this is the cross-section of the device, showing the MEMS chip and showing light. So actually, the light that goes into the device is either transmitted through the material or reflected from the material you want to test. So there are two modes of operation. You can measure in transmission mode or in reflectance mode. So the light then goes into the chip, and using molded optics, it goes parallel to the plane of the chip, where you have on the chip, it's a MEMS chip, you have vertical structures fabricated using deep reactive ion etching. And here we have a world record in deep reactive ion etching. We have vertical structures which are 400 to 500 micrometers in depth, which is unheard of. So this took us 3 to 4 years to master. Deep reactive ion etching, people do 20 microns, 40 microns, 60 microns, but doing 400 to 500 microns in deep reactive, this is a patented technology. And not only you have such deep vertical walls, these walls have to be of optical quality because we're building here mirrors, beam splitters, moving mirrors, things like that. So the surface roughness is very, very small. So this is a very, very demanding process. And it took us, as I mentioned, several years to perfect the manufacturing process of the MEMS. Now, the timeline for this is, as you see, it has maybe taken us 10 years from the day we started. And this is what you should expect when going into demanding MEMS devices. So it's a marathon. And this is something I always tell universities. My nature is inside me is an academic. I've been at the university, I teached and did research and then moved to the industry. When you discover a new technology in a university and you have a proof of concept, and then you license this technology to the industry, sometimes people at the university think, well, this is my idea. I need like 50% in terms of ownership or royalties or something like that. But it's a long marathon. And in order to make this idea a reality, a reliable product that goes to market, and sometimes it gets transformed maybe totally along the way when you are industrializing it. So it's a long marathon, and you pour tens of millions of dollars to make this happen. And here I'd like to maybe say something that I'm not sure that everybody knows. Scyware is a company that has been collaborating with KAXT for 15 years. And Taqniya, which sort of related to KAXT in a way, has an equity share in Scyware. So we really highly appreciate and value the relationship with KAXT. This product has won many awards. The most important of them is the PRISM Award, which is a very prestigious award in photonics. And it is like the Oscar of photonics. It happens every year in San Francisco, in the Bay Area. And our product won the Best Product Award in metrology, and many other awards, actually. Unfortunately, for hardware guys and semiconductors, whatever you do, whatever valuable thing you come up with, you're at the bottom of the value chain. And your company will not have real value unless you go higher in the value chain. The more you address the application, the more you develop things that go directly to the user, the more your company is valuable and the more you can have a handle on your supply chain. If you get content with developing modules and sell to system guys and then application guys, you will get squeezed. So what we did is totally changed the strategy, and we built a whole cloud-based system that would go directly to the end user rather than selling OEM chips or modules. And this has raised the valuation of the company from 10 to 20 times. So I'll try to go fast here. This is another phase of my life. 5 years ago, I have been commissioned by the government to lead a team to put a strategy for semiconductors in Egypt, and that we did. This shows all these companies were born in the last 15 years or 10 years, and Today we have a growing and vibrant semiconductor ecosystem in Egypt. And tomorrow we're launching what we call the Egyptian Semiconductor Alliance as an affiliate to the Global Semiconductor Alliance. And this will be in an event attended by the president and founder of the Global Semiconductor Alliance, which is a privilege that she would travel to Egypt to launch this event. So going to the strategy, what we did is the semiconductor industry or the electronics industry is very complex. So if you are coming late, like all countries in the region, you have to think, where do I penetrate? What do I do to be, to have a footprint on the global map? So you put things like all these, on the left, these are the business patterns people are doing. There are companies doing products and systems. There are companies doing electronic manufacturing services, like the big names like Foxconn and Flex and all these guys, they do manufacturing services. Or you could be a fabless company. A fabless semiconductor company develops products, does design, but delivers chips to the customers. You could be a pure play foundry, you could be an OSAT, you could develop IP, you could do design service. There are lots of things. And you cannot do everything. And each of these things requires special requirements that you have to avail and address. So in our strategy, we put here something. We wanted to come up with some figure of merit, and that we did. So this figure of merit combines things related to the requirements of each of these levels, industry levels. So technology, required infrastructure, talent pool or labor, what kind of market risk in each of them, what kind of valuation you can achieve or value you can achieve, what investments you need, what capex you need, and what edge does Egypt has in any of those. And we came up eventually with this matrix. And here we have put the things that we want to focus on, which are the dark blue things. The red ones are the things that we should not think about, like doing an IC fab, for example, or being an IDM company that does that is a vertically integrated company and does everything. So the things that we want to focus on are the things which we believe have the highest value and are low to moderate in terms of investment and capex. So we have two dimensions here. One is the innovation dimension, and one is the labor-intensive dimension. In the first one, we will focus on fabless IC and system and product development, actually, not service. As you may imagine, if you develop companies that develop new products, new ideas, this is much more valuable. Develop new technologies, new products, new ideas. It's much more valuable than doing services to others, enabling others to do this. Like, for example, if you are a services company, you're enabling a European company to do something very innovative, but eventually they own it, and you've just got your return from doing the service to them. So we'll focus on developing technologies and products ourselves, and also because of a socio-economic dimension, we need to go into manufacturing, but low-tech, not very low-tech, because nothing is low-tech in this industry. We'll focus on systems manufacturing rather than OSATs or fabs. So for the sake of time, one strategy enablement recommendation that we give is we need to have a dedicated body. In Egypt, we have something called the Information Technology Development Agency, and I'm on the board of this agency. This is, for the time being, driving this strategy, but we need something parallel for the electronics industry, because the Information Technology Development Agency is more on the software and the information technology side. So it's very important to have an owner for driving such kind of strategy. So this brings me to the end. As you have seen, I tried to cover very diverse topics from Moore's law, more than Moore, and then gave you an example about Cyware's product, which is more than Moore, which I believe is very convenient and very rich in terms of innovation, especially for late entrants, and then try to give you insight into what we are doing in Egypt in terms of strategy and things to develop the ecosystem, like building an alliance for the companies and hooking up this alliance to the Global Semiconductor Alliance. And thank you for your attention. I hope I haven't been too boring. Thank you very much. Questions or after?
Thank you, Professor Hisham. Please welcome Professor Thomas on stage.
Thank you, and good morning. Hello again. This time I will have a chance presenting some of the work we've been doing at KAUST. Thank you very much, Professor Hadar, for the very nice introduction from a pioneer in the field of conventional, established microelectronics. So what I will do, you can have my presentation. I will talk about sustainable manufacturing of large area electronics. So essentially, ideas that we're trying to develop and technologies that will enable these large area electronics to be applied to a range of emerging applications. And I will, this is the brief, essentially, outline of my talk. I talk a little bit about the historical developments. Have already been covered very nicely. Then I talk a little bit about the work we've been doing. So this is a kind of a brief history of electronics, and Professor Hadar, I think, covered very nicely. And this is where we are today, at the very right end of this journey. We have a lot of interesting developments. When we take a cross-section of these state-of-the-art microchips, we can actually see features that you can count the silicon atoms from one side to the other. What this has enabled is the industry, of course, to pursue this Moore's law and essentially stay with it. But we already seeing deviations, has already been described previously. Nevertheless, we are at the point now we're experiencing the hyperscaling era. A lot of different ideas are pursued, a lot of heterogeneous integration and putting things in order to increase the value of these microprocessors and microchips. What I'm personally interested in is not in, or I'm not involved in this type of activities, but I'm involved in other emerging trends. These emerging trends include the new concepts. We heard a lot about quantum computing. Of course, this is still under development and most likely will be ideas and implementation that hidden in the cloud. We also see neuromorphic engines and hardware and software being developed, already in place. So industry learns from these new ideas and emerging ideas. But what I'm more interested in, the new form of electronics, large area electronics. I believe in the future, these electronics will dominate our landscape, will improve further the machine and human interface interactions, will enable a lot of intelligence to be integrated with ordinary objects. But there is some issues which I will describe recently. So if I want to predict the future, this is what I will say. Probably in the next 5 years, we will see already seen a lot of prototypes and new industries being created. We've seen flexible electronics. We have Pragmatic here, one of the pioneers in the field. We'll see more soft or mechanical compliant electronics, or even transient electronics, electronics that you can implant in the human body and dissolve away after they have performed a specific function, perhaps even delivering a drug at the right time, the right moment, when the right biosignal is detected. This will create a lot of new opportunities. Already started these new opportunities to be materializing. And we're hoping this will be environmentally friendly and more sustainable new industries coming out of this. And this is where majority of interaction between basic research done in R&D centers and universities, and industry and key stakeholders will occur. So we are trying to do exactly that, bridge the gap. So this is a kind of the future I see. We'll see mass market applications. We're already seeing new products being adopted to existing applications, but we will see more and more functionalities, more value into these products. And if we look far into the future, we will see what I call technology proliferation. We will have fundamental basic technologies that are along the lines of large area, large volume electronics, be penetrating totally new markets, perhaps where silicon wouldn't be the most suitable technology. We don't have these technologies right now, but a lot of these different ideas have been pursued. But there is a problem, so this is the only technical slide I present. The moment we're deviating from the left-hand side of this chart, where we're going essentially to extreme downscale silicon transistors to larger, more cost or more economical solution, printed electronics, we pay a huge penalty on performance, to a point where if we take the best state-of-the-art, let's say, printed electronics today, large area electronics, and we want to interface them with silicon, it's not straightforward. Essentially, we always need a silicon chip, because these large area electronics are not good enough, they cannot operate at the required frequencies. And this is down to the specific device physics. We have transistors that if you're not small enough, or you don't use a semiconductor with good enough charge transport characteristics, you can't achieve these operating frequencies. As a result, you need to use more sophisticated fabrication techniques, which are not compatible with large area manufacturing. So there is a big chasm there, a big gap. And this is explained better in this plot, where we say essentially nature, if we take natural self-assembly, can take single atoms and make us through biological processes. So we know it's possible, but could we replicate that somehow in electronics, come up with simple solutions and deliver high-end products? When we look at the technologies available to us, of course, we see we are nowhere there. We have technology that complement each other. There is not a single manufacturing technology that will allow us to access the nano world, but also apply it over meters of substrates, or very relaxed in terms of economics. And this is where this performance gap exists, is between the high-performance electronics we have on the left and the emerging forms. Large area electronics would provide a cost benefits and for a lot of these emerging applications. So how do we bridge that gap? There are not many solutions available to us today. So this is what we've been doing in my group, trying to come up with simple ideas, and we will be able to address this gap. So what developed a very small variant of conventional lift-off lithography step. So essentially what we do, we start with a substrate, we deposit a metal, and on top of this metal we apply a self-assembled monolayer. This self-assembled monolayer attaches only to the metal, but not on the substrate. So we can tune the surface energetics, how adhesive that surface might be, maybe very hydrophilic or very hydrophobic. And depending on the metal we have, we can choose the right self-assembled monolayer, small organic molecules, which only like a nanometer in length. So we can make it hydrophilic, we can make it hydrophobic with extreme precision, atomic precision, because we can control the chemistry of these monolayers. Then what we do, we apply this glue on top. First, on the left, we deposit a metal electrode everywhere in our substrate, metal 2, and then we apply a glue and mechanically peel it off. And what we discover is that the areas of the metal 2 in touch with metal 1 that contains this self-assembled monolayer doesn't really adhere on the surface very strongly. And the adhesion forces are very weak, and as a result it's delaminated, while part of the metal 1 that comes in contact with the substrate remain in place. So the end result is a very tiny nano gap formed between metal 1 and metal 2, in very close proximity to each other. And then we can remove the self-assembled monolayer by just burning it off in a few seconds in our oxygen plasma, for instance. And then we end up with a structure with a coplanar electrodes, which may be metal 1 and metal 2 are different metals. So it's quite interesting for a lot of optoelectronic applications, for instance, where we need electrode injecting a whole positive charge and another electrode injecting electrons, negative charges. And this is a small video. I don't know if we can play that, if somebody can press. I don't have access to this. No? That describe this process. It doesn't matter. So what essentially happens there, after you have this mechanical exfoliation, peeling off process, we end up with two electrodes very adjacent, very close to each other. We didn't expect to be so close. Essentially, you see on the right there a cross-sectional analysis of such electrodes, where we see the two electrodes are 10 nanometers from each other and fully electrically isolated. There are absolutely no shorts between these two electrodes. Then what we do, we start placing semiconductors on top of these electrodes in order to create functional devices. So essentially, we have access to the nanoscale dimensions using these macroscopic, very relaxed processing protocols in place. And we can make these nanogaps very tiny, but the two electrodes can run along each other for long distances, meters or hundreds of meters. We demonstrated prototype nanogaps of very high aspect ratio, and on a number of different substrates. So what have we been doing? We've been using these coplanar electrodes as the foundation for building a number of devices. And all these are device examples that we have been developing over the years. And one of the most important ones is the diodes. Why you have chosen diodes? Because Schottky diodes in particular allow current to propagate in one direction but not in the other, but they can be used for a number of applications. And one of them is the Internet of Things. In the emerging forms of Internet of Things, you will have elements that will be able to sense information, process information, transmit to a base station, etc. But they also need to be powered. And diodes can be used to harvest RF energy from the ambient, but also contribute to the telecommunication component of these systems. The key challenge in this diode is to be able to operate at the required frequencies. If you want this diode to operate at a Wi-Fi frequency, then you need to be able to deliver a couple of gigahertz of operations, of frequency. And this is not easy to access with printed diode technologies or large area forms of these electronics. So that's what we've been developing. We've been using this adhesion lithography technology on a wafer size prototype devices. We're creating these coplanar circular-like electrodes. We deposit a semiconductor on the top and essentially probe their performance. And this is some data we published a few years back. So essentially what you see here in the middle top, you will see the DC output of a little circuit that picks up this RF signal being transmitted by an instrument, rectifying it, and essentially converting into a DC output that we can then use to power a load. That might be a microprocessor or part of that IoT node. And what is impressive is that we can now have this very simple to make coplanar diodes that operate with cutoff frequency of 5.7 gigahertz, much higher than anything done on using compatible techniques. And this is based on a zinc oxide as a semiconductor in the middle, which has been solution processed over a large area. And at the time, these results were quite ahead of its time for comparable technologies. More recently, we're able to lower even the process time and complexity of what we do. So we took this technology, we developed it further, and we removed the need for this application of the glue on top. So essentially, we have a self-formed nanogaps that are created due to the surface interaction between the two metals, which results to a spontaneous microfracturing and a creation of the nanogap. Then we took this wafer and we combined it with photonic sintering technologies. Essentially, what we do, we take a solution processable metal oxide precursor, which is transparent. We apply it on top of this wafer. We put it on this big xenon lamp in this novocentric optical sintering system. We flash it for a millisecond. And essentially what we discover is that because of the proximity between the two coplanar metals, if you place a semiconductor precursor in the middle, this middle semiconductor essentially experiences the temperature of the metals. And these metals, as they absorb part of this outputted light, because of high intensity, can raise their temperature up to 600 degrees Celsius. You can see at the bottom there the autothermal simulations. And essentially induce the chemical conversion of the semiconductor in the nanogap, just within the 10 nanometers between the electrodes. So essentially we have a very rapid manufacturing of these diodes. And how these diodes perform is summarized here. Apologies for the technical details, but on the right-hand side, you will see essentially the summary of these results. We have the intrinsic cutoff frequency, which can be up to 100 gigahertz. These coplanar diodes can really operate very fast. And the extrinsic, what exactly our diodes can do, on the right with the red color there, we see now we have rich cutoff frequencies of 50 gigahertz on these large area diodes, which can be manufactured even on plastic, very rapidly using very low energy input. This is where we stand today. Our diodes actually outperform most of the reported diode technologies that are sort of compatible with large area manufacturing and are actually even comparable with commercial products. This is how, it's kind of a showcase, is how simple solutions can potentially deliver very interesting products or potential devices that could be incorporated with emerging technologies that we see coming our way in the future. And what we do more, this is a plot I borrowed from a publication we're preparing with Professor Vincenzo Pecunia from Canada, and we're applying the similar technologies in all sort of different device ecosystem around IoT, from new materials in combination with our nanogap electrode technology, because our nanogaps are actually material agnostic. We have recently removed the oxide semiconductor and replaced with organic semiconductor, and we showed that we can actually make diodes that operate 10 gigahertz, even if the semiconductor is organic. So suddenly we're reaching dimensions which enable adaptation of more different semiconductors without really compromising a lot in the performance. And there are a lot of challenges, but at the same time, a lot of opportunities. And with this, I would like to summarize my talk. Just showcase a very simple technology can deliver exceptionally good results. And now we're trying to explore what else we could do with this, with our technology. Thank you very much for your attention.
Thank you, Professor Thomas. Please welcome Professor Abdel Fattah Abed.
Okay, Bismillah ar-Rahman ar-Rahim. Alhamdulillah, wa salatu wa ala Sayyidina Muhammad Rasulullah. So this is quite maybe a different topic than the very advanced technology topics that has been addressed so far. And it is on a proposed design methodology for reconfigurable solutions, which is my area. So let me start by just very briefly introducing the overview of the points that I'm going to discuss. We're just going to first talk about the rationale. Why do we need to have reconfigurable computing, and what is reconfigurable computing in general? And then what are the main new concepts that has been emerging in this field, and show some examples of available reconfigurable solutions in the market, and then propose a design methodology that will help us take care of all the aspects for the reconfigurable architecture, the proposed reconfigurable architecture to be useful. But let us start with a very soft start here. What do we do as electrical and electronics engineers? I've been taught by one of my dearest professors that we electrical and electronics engineers, we only do generation, transmission, and reception of an electrical signal to better human life. So this signal can be as big as the one in a power plant, and we transmit the signal, then we can use it in home appliances. And here we're more interested in the power of the signal. So electrical engineers there, they try to find the best ways to generate the signal, to generate the power, and transmit it with minimal losses, and receive it in adequate manner to do something useful, to better human life. Or it can be a smaller signal like satellite communications or mobile communications. And there, the most important thing would be to transmit the information at the lowest cost. Maybe the power or the energy is not what we are after, but the information is then what we are after. And to do that, we'll have to do very smart things in terms of, coding, transmission techniques, and what have you, to make sure that we send information and we receive it from larger distances at high fidelity. Or it can be sometimes we are not interested in the signal or the information itself, but we might be only interested in what's happening in a channel. So, for example, what happens in radars. Our knowledge of what we are transmitting and how we are receiving it, the codes we transmit, the waveforms, will tell us what is happening in the channel and what reflections do we get and how can we identify the information in this channel. Or also in medical, for example. Maybe in an MRI machine or what have you, where you transmit some power and receive it back, and then you need to know what is happening in between. So to do all that, in terms of transmitting information, we need to do a lot of computations. And now, because of the advancements that we've been hearing about here from my most esteemed colleagues that talked before me, you can really, it would be very, very difficult for you to imagine any field that does not have any electronics. And most of these electronics, they do computations. They do computations because you need these computations to happen for several reasons, and you need them to happen in adequate time, in real time. If you are talking about communications, you want to reach the Shannon information limit and transmit as much information as you can in the channel approaching the theoretical levels of information technology or information theory. So you have a lot of appliances and applications around you, and what you're really doing is that you are doing computations, mathematical operations. There are two main traditional ways to do computations. The first one, everybody knows about it, it is the microprocessors or the microcontroller or a DSP. And there, if you're using a DSP or a microcontroller or a microprocessor, the functionality you can achieve is more or less limited by your imagination. How can you write good software that will run this machine and carry out the application that you are after? But not all the time are you able to carry these computations in real time or in the time limitations given to you. So then people tend to design what they call application-specific integrated circuits, which are circuits which are ASICs or chips, ICs, that have functional units or, that is carrying out a given function at the most efficient and the fastest way. Okay. So microprocessors are very flexible, but they are slow. ASICs are very limited in flexibility, but they have the highest performance. And between this and that, we must have another solution that will be a little more flexible than ASICs, but still better in performance than microprocessors. Let us look now at this curve. This curve shows what we call the theoretical computational efficiency in millions of operations per second per watt. And you can see there that there is an increasing gap between the intrinsic theoretical computational efficiency and the programmable processor. Okay, and this is because the programmable processor in nature is irregular in terms of the its architecture and the electronics and the circuits inside. And also because the old computers, more or less, are operated under what they call the von Neumann paradigm, where you do an instruction fetch and then instruction decode and then data fetch, and then you do the execution, which is the only useful part there, and then write the result back to the memory or wherever it should be written to. So all these 5 steps, only one step is execution, and the rest 4 is just there for flexibility purposes. Another issue is what we call the integration gap. And you can see, for example, in memories, for example, which are very regular, the basic cell, the basic memory cell, is very carefully designed and then replicated to to be able to shrink and miniaturize and also load as many devices in a given chip. But in contrast, the microprocessors are irregular, and there is increasingly a widening gap between the integration density levels that you can achieve in the microprocessors because of the control units and the other peripherals that helps it be flexible. It is not regular in nature, and therefore you cannot integrate as much in the given area. And one more issue is a very important issue, not a technological issue, but it is more or less a market issue now. In the mid-90s, the time in market started becoming less than the time to market. So that means that now you spend much more man hours or engineering hours developing a product than this product is going to live in the market itself. And this is a dilemma. Okay. So I'll have to be a little bit faster, they tell me. So in general now, a new technology emerged, which is called reconfigurable technologies, or FPGAs, and there are a lot of products have started to emerge since '85 until now, and we now find we find many applications that were not really seen before. So we can use FPGAs to implement digital functions, to replace, in many cases, ASICs, to do prototyping, and also to do real-time compute engines, like what people do now when they program GPUs or what have you. They can have a lot of programming power that was not available for them before. Okay, and also you can on-site now modify your designs without needing to recall it or take it back to the factories. Many also concepts emerged when reconfigurable technologies started emerging, and these issues are very specific to reconfigurable technologies. So in terms of volatility, there are volatile solutions, and there are non-volatile solutions, and they're one-time programmable. Okay, and you also have the issue of granularity. Do you want to have a solution that is 1-bit granularity, or maybe 1 vector of granularity, or a mix of this and that? To connect resources, you have different interconnection topologies. You have different reconfiguration features, like runtime reconfiguration, like single or multi-context. You can have multi-configurations on one chip, then you can switch between them. Okay, coupling, how do you couple it to a microprocessor? Because there's no one solution fits all. So all these solutions, as Dr. Hisham has mentioned before, you need to have a very nice collection of elements in your solution. So a microprocessor should be there, and the reconfigurable unit also can be there, but the integration with the rest of the system really also influences and impacts the design. Studies show that although field programmable gate arrays are good solutions, but you really pay a very high penalty. For classical fine-grained FPGA solutions, you're really using effectively 1% of the area for computational resources, and the rest goes for reconfiguration as a reconfiguration overhead. And therefore, now people started thinking about having coarse-grained or coarse-grained blocks in the architecture itself. Okay. So I will just very fast try to give some examples of reconfigurable solutions and what features do they carry. Just to take a look. Some of them, which is a very good idea, are influenced by given VLSI or DSP applications. For example, this solution we have has several interconnection resources and the interconnection topology, but it also has two main types of processing elements, one for arithmetic and one for memory manipulation. This solution here from the university, one university in Turkey, also is a very smart solution, but it also had solved a very important issue of having a software solution or a software compiler that can help the designer use high-level language to realize the design on the FPGA itself, to shorten the time to market, and also to reduce the technology barrier that needs to be addressed. Another solution here also from another company in Egypt called ASIP, and it is an application-specific integrated processor. In that case, it is not really an array of reconfigurable elements, but it has in its core a microprocessor or a microcontroller that is designed behind OFDM requirements to be able to realize different communications or OFDM standards at different times to shorten the time to market and the development. With that, they have also produced a compiler. This compiler has a high-level component and a low-level component to be able to interact between the user and the hardware itself. Just maybe skip through that because of the time. And I just want to take you now through an example to show, this is a very interesting example. There is something called the Radix 2 single delay feedback architecture for FFTs. And this is a very interesting architecture, and I use it as an example to show that you cannot really design FPGAs coarse or fine-grained just given the that you want to, what is reconfigurable technology, and you want to design your own. You have to really understand what kind of problems you are solving. So this single delay feedback architecture can do FFTs, and you can see here that we have different stages of this what we call the dynamic butterfly, and the dynamic butterfly can either do transfer of the data, or it can do a butterfly, and each cycle these butterflies flip in terms of their functionality. So we can then gather that we have features that we have to address. Number one, for example, we have to have local storage of coefficients. We have to have a data flow structure. We have to have a butterfly interconnectivity between different elements. We have to have dynamic configuration in one cycle to flip between different solutions. We have to have local FIFOs or memory elements, and need to have operation and reconfiguration control to ensure that the data is coherent at each cycle of time. So after studying all that, you can come up with the features of the field programmable gate array or the coarse grain reconfigurable solutions that you want to design. tackling the target application, what kind of architecture, you have to start from that, and knowing what kind of coupling and what kind of compilers even, and the software issues. So in summary, to conclude, reconfigurable solutions can help reduce time to market and bridge a number of technology gaps. Reconfigurable technologies introduce a new computational paradigm and many new concepts that were not available before. As I have mentioned, now you can prototype as you are sitting in the comfort of your own disk rather than needing to go to a fab, or you can do very complex and very heavy computations, programming things like GPUs, also at the comfort of your own disk or research lab. To optimize the efficiency and the utilization of reconfigurable solutions, you have to consider the targeted family of applications. There is no one size fits all. It will not really work very efficiently. And the software barrier is probably one of the most important barriers, and people now started finding solutions of software where you can have a normal programmer utilize this hardware. For example, like what people do with NVIDIA GPUs, they use CODA or they use some MATLAB features to be able to directly program this reconfigurable solution. And with that, I conclude, and thank you very much.
Thank you, Professor Abdel Fattah. Please welcome Professor Hussam Niman al-Sharif.
Let me just do a quick test. Is the presentation there? Okay. Let me just do a quick test. Okay, Assalamu alaikum. First of all, this is, it's playing games with me. I can't move. I can't start at the end. Can you please reset it to go at the beginning? Okay. Sorry about that. Good afternoon, everyone. My name is Hussam al-Sharif. I come from KAUST, Material Science and Engineering. I want to start by actually extending my sincere thanks to my colleagues at KAUST and KAXT for the efforts they put to organize this event and for asking me to come and share some of our research with you. The distinguished speakers before me talked about circuit design. They talked about MEMS level integration, and they also talked about large area cost-effective integration. This talk is actually materials focused. So I'm going to talk about a new materials, group of materials called MAXenes. In my group, we work on solution processing of two-dimensional materials, and MAXene is one of these materials, is processed by solution processing. And MAXenes actually were discovered in 2011 at Drexel University. Originally, they were discovered for actually lithium-ion storage and capacitive energy storage. They are energy storage materials. And we got involved with this because my group is also working a little bit in this area. But along the way, we realized that they may have some interesting applications besides energy storage. And so we started to look at them for electronic applications. And let me first talk about the materials themselves and then the applications. So to talk about MAXenes, we must talk about what's called MAX phases. These MAX phases were discovered many years ago in the 60s. People who work in the ceramics field know these materials very well. They are high temperature, highly stable, wear-resistant materials, and ceramists have always been interested in them. These materials have the general formula MAX, where M is a transition metal. A is one of these blue highlighted metals. Notably, aluminum is one of the common elements there, and then carbon and nitrogen. So if N is 1, you will end up with what's called the 2-1-1 max phase. If N is 2, you'll end up with 3-1-2, and so forth. So these phases are known. So you can buy those, or some of the exotic composition we can make in our lab right now. So these are the parent phases of what we call MAXenes. To get the MAXenes, actually, this was discovered as I said, at Drexel University by Yuri Gogotsi and Michel Bersoum, who's actually from Egypt also. The process is like this. You start with the max phase on the left here, and then on the left, and you see these blue atoms are actually the aluminum atoms in the structure. It turns out that for this material, the bonding between the transition metal and the carbon nitrogen is very different from the bonding with aluminum. So the ionic character is largely different. So if you put them in a polar solvent, you attack one of the bonds much faster than you attack the other. So you can selectively remove the aluminum and end up with these two-dimensional materials. Of course, because you use wet chemistry, you could end up with surface functional groups on the MXenes, depending on the chemistry that you use. So far, people have prepared over 30 MXene compositions. And actually, if you combine transition metals, you could make many more. So this is the process, again, showed on the left here. We have the max phase, and the blue atom are the aluminum there. You remove them. After you remove them, this is called etched MXene. You could intercalate organic species and actually delaminate them more. And you end up, if you look under the microscope, oh, there was an animation there, which I guess I missed. To make the MXenes, you actually do like this. You start on the top with powders, like a ceramics processing, and you can make pellets, which you sinter, and then you crush down to form the max phase powder. Using wet chemistry, as I mentioned, there are many wet chemistries you use. Each has its own advantages and disadvantages. You create MXene suspension. If it's stable enough, then you can process that and make a variety of different materials. You can make membranes, you can make gels, you can make hydrogels, aerogels, and we have been trying to make films of it because for electronics, you're going to need to make films. Now, before I get into the devices, so what can we expect from MXenes for electronic applications? Actually, there's a lot of simulations. And so we summarized a lot of the DFT work in this review. And what you see here is on top, for example, for carbide MXene. You see, like on the y-axis, these oxygen, hydroxyl, and fluorine. These are functional groups that could be on the MXene surface. And then horizontally, you see the transition metals. So, for example, this means, if you take yttrium, for example, if it has oxygen on the surface, you could, in principle, end up with a semiconductor MXene. The truth is that most of them are metallic. And if you go to the nitrides, they're even dominated by metallic behavior because the nitrogen has one more electron than the carbon. The truth is that these are the simulations. When you try to make it experimentally, for example, nobody has really been able to make a large enough band gap in MXene. If one can do that, we actually could have a breakthrough in the field. So it turns out that the MXenes is still an art. It's an emerging material, if you will, and it is being optimized and getting better every day. So with that, we started looking at how can we use MXenes in electronics. Okay, we envision three ways. Okay, one is to use them, because they're metallic mostly, as contact material in various devices. People are using them as antennas or electromagnetic shielding materials. You can actually use them as active material. For example, plasmonic, they have plasmonic modes, and I will show that in a minute. You can use them as a photodetector. They also are photothermal. Or you can use them because of their 2D character to make 2D semiconductor materials in two-dimensional form that are not normally two-dimensional. So I'm going to share three examples. Two of them where the MXene did not really work very well, and one, in my opinion, that looks very promising. Okay, so these are some of the thin films, and you can see under the microscope how they look like. They are made from large flakes. So this is, again, solution processing. This is not going to compete with, like Hisham talked about, silicon or 3 nanometers. This is printed large area electronics type of field. We make them over large areas. One of the actually motivations for this work, a lot of people that have been for years trying to replace ITO in transparent electronics because of its cost. So people are talking about ITO-free electronics. So this is the context here. So we made them over large area, and we tested their bending and effect on their conductivity. And they seem to do very well, actually comparable to ITO. And then this is a comparison of. This is a common curve that people show for the transmission of contact materials in flexible electronics. You can see compared to graphene or silver nanowires, some are also conducting polymers, that these MXenes actually, they have comparable behavior, but they do have one advantage. that in principle, you can actually tune their work function over a large range from 2 to 6 eV, meaning that they can give you different types of devices because each device would require a different work function. But right now, at this stage of development, the control over the work function, to be honest, is not very good at this point. So here's the first device we made out of Maxines. This is a CMOS device, basically made by solution processing. We looked at the semiconductors we have in our lab. We have been working on oxide semiconductors, and we found out this Maxine with the engineered work function of about 4.6 eV can actually have nice band alignment to both of these semiconductors, SNO and zinc oxide. And so we tried to make a CMOS device using these two semiconductors. And you see the process flow. I won't go into the details at the bottom left right here. And in fact, you can do it, and it works as a contact material. The transistor performance, I would say, is decent, but still can use a lot more improvement. If you look at the inverters, for example, we can get a gain of about 80, which for a first shot for this material is actually not too bad. Another thing you can do with this material, since we're doing solution processing of 2D materials, actually try to combine it with polysulfide, which is an emerging 2D semiconductor as well. Here, we tried to do it by developing photolithography and dry etching processes, because in the end, that would also be nice if we could use Maxine in that way. I won't go to this process flow, but this basically uses polysulfide and Maxine to fabricate, again, transistors. Here, the results were a mixed bag. On the one hand, we were able to get excellent uniformity across the large wafers, even using a dielectric as thin as 2 nanometer for a spray-coated electrode. This is actually pretty impressive. We got excellent yield. Most of the devices work, and they have really nice behavior. The ion life was good, but the mobility is low, which indicates that the process flow is actually not optimized. So maybe the etching process needs to be improved. We also made some simple circuits, basically a diode and inverter and a voltage shift inverter. Again, the functionality is there, but the performance, because of the low mobility, is still actually, I would say, inferior to some of the other contacts. So there's some issue that needs to be fixed here. Another topic, this is moving from using Maxine as contact, is to using Maxine, capitalize on its plasmonic behavior. So there are two applications we thought about. SARES, which is used in sensing. Basically, you can use the plasmonic to enhance Raman signals. Another one is actually to use them as plasmonic photodetector. So this is work we did with the core labs at KAUST. And what we did, we used the EELS and the TEM to try to study the plasmonic mode in the Maxine flakes. And then if you see in the image on the left here, it's a little bit, don't want to get too technical, but there are different plasmon modes that these Maxines carry. And some of them are longitudinal and some of them transverse. And more importantly, what we showed on the right is actually if you change the functional group on the surface of the Maxine, then you can change the frequency of these surface plasmons, meaning your plasmon detector can work in different frequency regime. And then we tried to make a device. These figures are all moving around. I don't know why. But if you see that this polycarbide Maxine, actually, we studied a bunch of them, was the most promising. It turns out that actually it can work as a plasmonic photodetector in the visible. And you can see from the on and off curves. We studied the mechanism for this in collaboration with the Solar Center, and we understand how they work. And now we are trying to improve their performance. And finally, which is probably the most promising application of these Maxines, in many circuit boards, if you look on the circuit board, you see this big capacitor that I circled. This is an aluminum electrolytic capacitor. This capacitor is too big for a reason. If you look at the rectification circuits, when the signal comes out of rectifier, there's some ripple. So these electrolytic capacitors are actually put in these circuits to try to get rid of this ripple effect. And the way you get rid of this ripple effect is actually, if you look at the equation, by increasing the capacitance or the resistance. Increasing the resistance is not a good option because it creates a lot of problems. So you need large capacitance, and this is why these capacitors are very large. And that's why they stick out so much. So ideally, it would be nice if we can actually reduce the size of these capacitors. These are discrete. These are basically, easier to fabricate than a 3 nanometer chip, if you will. So Maxines, we thought, would be ideal for this for two reasons. Number one, Maxine actually exhibits a very large capacitance. It was invented for this reason. And number two, it's metallic. So we actually did that and fabricated magazines over large wafers, 4-inch wafers at KAUST. And basically, if you look at the pattern here, just go to the right hand on the bottom hand. See this optimized flake and optimized photolithography process on the right hand side. This is how the device looks like. It turns out for AC filtering, you need a phase angle of about 82 at 120 hertz. And our devices actually can get that. And they have a crossover frequency of 11,000 hertz actually. If you look at the curves, they actually overlay on top of the aluminum electrolytic capacitor on the right-hand side on the top over there. And if you look at the bottom for the full circuit, there's the original signal, the rectified signal with the ripple, and then there's a blue and red curved lines there that actually show that our maxine capacitor can, in fact, match the performance of the commercial devices. So that's something we actually working very hard on. We're packaging it and evaluating the performance like that. And finally, if I have 2 minutes, if you really want to use maxine at a more integrated fashion, you really have to do them by CVD. So we are trying to actually fabricate these materials by chemical vapor deposition over large areas. And the approach we took is based on a process we had developed at KAUST a couple of years back, and that is to start with oxides and use chemical phase conversion to make actually the semiconductors. So we have demonstrated this process to make molybdenite semiconductors out of moly oxide, like moly sulfide. Out of zinc oxide, we can make zinc selenide. Out of indium oxide, we can make indium selenide. So all these are semiconductor materials that can be grown with texture, with pseudo-epitaxy, if you will. So we try to actually do the same process with maxine. We call them maxine-like films because we haven't yet functionalized the surface. And you can actually start with moly oxide, and you can end with the moly carbide, which is shown on the substrate here, and the AFMs inside the microscope. So yes, maxines can, in principle, be grown by CVD, but there is really, to the truth, a long way to go. And with this, I actually would like to thank you for your attention.
Good afternoon, ladies and gentlemen. So first, I would like to thank our speakers for their interesting talks. They were very interesting about the convergence of Moore's law. So since we are short on time, I'll try to have a few questions here, and then we'll let the audience have their questions. So if I can start with you, Professor Hisham. So one of the questions, we have some stakeholders from the industry. So what do you think is the best approach to start an industry like the ecosystem in the kingdoms? Shall we proceed with the push model or the pull model, just to have the start, since we don't have anything solid at the moment? And what, in terms of fabrication fabs, what technology do you think it's feasible that we should start with?
It's a very difficult question, actually, because as I tried to explain, we've gone through this exercise from A to Z. And when you look at the industry and the applications, you come up with a very complex matrix. And no country can penetrate or can do anything. For example, when you look at Korea back in the early 90s, they were very late. And they sat down and said, okay, we will focus on memories and displays. Okay, so now they are dominating memories. And so focus is very important. So this is one very important thing. So it has to be something. Then you can, once you dominate a certain thing, you can diversify. But you cannot do, and if you take, for example, a country like Malaysia, they started from the back end. And then they are trying to go now into design and so forth. Even China, which is huge, they didn't have any design or any technology. They were trying to reverse engineer and trying to do. They were saying we're the factory of the world. Okay. Now they don't like this anymore. They want to have their own technology. They are buying IP. They are buying companies. We sold them a company, by the way. So it's a complex thing because you have either you can start from the top and address certain applications and do systems, and these could correspond to a national need or a global need, but you're positioning yourself at the top of the value chain. Okay. And then when you start gaining market share, you can start going down.
So shall we approach the stakeholders and ask them what you need, or we just try to find a niche in the...
Typically, when you do a strategy, you want to have all the stakeholders participate in doing the strategy. So I cannot say what can be done here, the stakeholders themselves. So what we did is for 7 or 8 months, we gathered weekly, like 50-something people from industries, universities, and experts. And we had also a small firm to moderate the process, like specialized in strategy development and so forth, such that we came up with what we think can be done, what can be good for Egypt, actually. Okay. So we chose to do products, fab, whether on the chip level or on the system level. And we chose to address, you have applications, for example, you have healthcare, because you cannot say, okay, I'll do products for everything, or I'll do chips for everything. When you do a chip, it matters whether, if you have to understand the application, you have to, is this chip for telecom, or is it for healthcare, or is it for automotive? Exactly. Okay, totally different things. So you have to build the talent pool that addresses the automotive applications or the healthcare applications, and on the horizontal level, you have to understand what kind of things you're going to do. Are you going to do service or products or manufacturing, or so it's a complex thing.
And it's also based on the needs that we should set, the technology that we should target if we are building a fab, right?
Yeah.
So we shouldn't just set a technology, for example, let's say 65 nanometers or 28 nanometers, whatever. We should just start with the need, and then we set our target technology, right?
Yeah. If personally, I don't believe in going into fabs unless you have your own. I mean, if you do a fab to serve the global market, because you don't have an industry, or Egypt doesn't have an industry, so if I do a fab, I have to serve the global market, because I don't have my own product companies. So it's very challenging and very tough. You're going to compete with whom? So you're going to convince TSMC, and we've done that exercise. I mean, the list is very long. Like everybody is trying to convince TSMC to come and if you don't have an ecosystem, they will prefer another country. So it's a battle that is not worth fighting. Having a fab, you have to build an ecosystem, the talent, the products, and then the fab will come to you.
Okay. Yeah, that's good.
So unless you have a strategic need, for example, in areas that are like security or so, and then you would target a very not a state-of-the-art fab, a fab which is, you can buy even a fab for $100 million to address, to do 0.13, 0.18 microns, and this would be very good for any strategic kind of activity. But pure play founders that do state-of-the-art technologies like global, I wouldn't think of even attracting them.
It's very expensive. So just for the sake of time, maybe we'll have 1 or 2 questions from the audience. Dr. Maha, maybe? You have a mic.
Hi, Thomas. For the sake of time, I will go straight forward to my question.
Your voice.
I'll go straight forward to my question here. Thomas, you mentioned exfoliating a layer where the feed you unfortunately didn't work that time. When you the material under consideration, you exfoliate it mechanically. didn't we? So how did you do that? Did you evaporate like stressor layer on the surface, like titanium nickel? Did that? Or there is another technique which I would like to draw your attention to, which has been developed by CACS, where we can exfoliate layer without any cracks or any deformation at liquid nitrogen temperature. Thank you.
Thank you.
Yeah, so it is, that process you mentioned is a very interesting one. Is it just cooling the whole substrate, I guess, yeah? Yeah. So in our case, we started with the mechanical exfoliation by applying essentially sellotape around on our samples. It was a serendipitous discovery, and we exfoliated and we saw that the selective removal. More recently, we started playing with interfaces and building essentially tensile stresses by looking at adhesion layers, like you mentioned. Titanium was one of them, chromium. It's essentially, we tried to explore what industry was trying to avoid all these years. In the microelectronic industry, you want a strong adhesion between your layers. But that was not always as successful. So we use essentially that knowledge to delaminate the moment we have grown a layer of X thickness, a critical thickness, and then essentially spontaneous delamination occur and the formation of these coplanar electrodes at a very, very short distances, below 10 nanometers usually. I didn't show any of this data, but but I was we were also thinking about thermal stressing them. I'll be very happy to actually receive some more information about your technology. Thank you.
So we'll have one more question for the sake of time. Maybe Dr. Hamad.
You spoke about the ecosystem for the country in order to establish such industry for semiconductor. As you know, and I'm sure you have been passing through these things, if not for working at the educational systems, what would be the minimum requirements for the educational system within the country? We have about 40 universities and some other technical schools for the Tier 3 schools. What would be the required, I would say, curricula or courses needed in order to promote students when they go out, they can work in such systems like designing or fabricating the electronics and being involved in the ecosystem of the educational system, not just specifically for that direction. So they eventually graduate and they can find different ways for employment. One of them will be the electronic industry. Thank you.
Okay. So normally, like the case in Egypt, unfortunately, we found that graduates don't have, there is a gap between what the industry or the companies need and what the student learn in terms of undergraduate courses. So we started requiring that students do projects, the graduation projects at least should be in coordination with industry, should address real problems, not like any project. And this is a very good way of giving the students some professional experience before they graduate. But in order to judge whether the curricula are good or not good, I'm not really familiar with what the Saudi universities, maybe they are better than what we have in Egypt. The thing is that when you start thinking, if you think of a company or two, then it doesn't matter. But when you think on a national scale, things start mattering, because you will be trying to, for example, develop the local industry, but in the same time trying to attract foreign direct investment, like attracting global companies to come and open development centers if you're addressing design companies or manufacturing companies. So you have to be worrying about quantity and quality at the same time. You have to develop the talent pool in both directions. And so what we invented, or we started launching something It started actually 2 decades ago when the country was focusing on software. It's an institute that is called Information Technology Institute, and it addresses the gap. It's a 9-month program that addresses the gap between what the market requires and what the university delivers. And now these information technology institutes are spread all over the country, and we embedded in them programs in chip design and MEMS. So this is one way of trying to bridge the gap between what the university does. And actually this, you can find this in many countries. But to comment on Saudi Arabia, I'm not really well equipped, but I'm just saying that in so many cases there is this disconnect, especially when a country is new to this kind of technology or industry. There is this gap that you have to address.
Thank you. Sorry, we'll have to stop here for the sake of the time. So very interesting talks. It was a pleasure to introduce our speakers, Professor Hisham, Professor Abdel Fattah, Professor Sam, and Professor Thomas. We thank you all for your presence today and for your interesting talks. And now we conclude this session, and we'll have Mr. Jewel. Mr. Jewel.
All right, it is time for the lunch and prayer break, as well as the poster competition. We will see you back in an hour after the break.
Attention everybody, the lunch is downstairs. If you could go downstairs. Attention everybody, the lunch is downstairs. Attention everybody, the lunch is downstairs. Then
Welcome back. Again, it is time for our technical discussion, Advanced Photonics. He is the Professor of Materials and Electrical and Computer Engineering, received his PhD in Electrical Engineering, is the recipient of the National Scientist Foundation Young Investor Award. Please welcome Professor Stephen Denbars.
Thank you for inviting me. So today I'll be talking about advanced gallium nitride photonics for sensing, communication, and display. I'd like to thank my colleagues here, Suji Nakamura, Professor Mishra here as well. Jim Speck couldn't make it. But more importantly, I'd like to thank a very large group of graduate students and visiting researchers, scientists, some of whom have come from CAC, so I'll call them out. So I'll be showing some of the work from Abdullah Al-Hassan, Ahmed Al-Yamani, and also Bunoy from KAUST have been collaborators over many years of research in gallium nitride photonics. So talk outline, I'm going to be focusing not on solid-state lighting today, but what I consider to be kind of the new next big things that are occurring in gallium nitride photonics. Starting out in particularly with what we call micro-LED, which is the reduction in size of LEDs from millimeters now down to single microns. And this basically, reduction from 100 to 1 micron, results in a lot of problems in the external quantum efficiency dropping. Over the last few years, we've determined that atomic layer deposition is a key passivation technology needed to improve micro-LEDs. And then show you some recent results of Li-Fi with micro-LEDs. That is, your display will also be your communication device. Then I'll talk about my research in laser diodes, starting with laser lighting, where we've combined blue lasers with phosphors to generate white light for things like automobile headlights, projection display, and then embedding now into that laser the ability to sense, that is, to do a time-of-flight LiDAR systems. That is, you can use your laser-based headlight to not only illuminate the road, but you can use it for collision avoidance. Also, you can do vehicle-to-vehicle communication. And so laser Li-Fi, which is some of the work we've done with CACS and KAUST, is now being realistically used for some of the communication functions in the automobile industry. This chart shows kind of where we've taken gallium nitride in terms of the application areas. So in particular on the LED side, we started with general lighting on the left side here, and we've now, as Professor Nakamura showed in his talk, we've expanded the wavelength range into the ultraviolet, in fact UVC, for sanitization and decontamination of surfaces. But we've also reduced the size of the LEDs drastically so that you can consider now using them for watches, iPhones, but more importantly, what's called the augmented reality world. That is basically putting the display on your glasses or anywhere you see will be a key technology of micro-LEDs. We've also looked at applications in laser and LED for biosensing and in even upconversion into the ultraviolet. The laser diodes applications I'll highlight are the car headlight. So on the road today, believe it or not, both Audi and BMW sell cars with laser headlights for increased safety at night. And in those headlights, we can put functions like the LiDAR, I said. And then there's a picture there of a light bulb, which is actually communicating at very high frequencies, what we call light fidelity or Li-Fi. Next slide. So let's start with micro LEDs. Why are we spending so much time at UCSB doing this? Well, basically, we're seeing here a huge LED screen in back of us. If we reduce the size of that LED, which is currently about 500 microns, to 5 microns, or a 100-fold reduction, you will then bring it down to the size of something you can put in your eyeglasses. Could also be put in a motorcycle helmet or a heads-up display. And the LEDs become so small that whatever backplane you put it on becomes flexible and transparent. You can even make very large screen TVs, so the resolution of this current screen here is probably only on the order of 10,000 or so, but you can make full 5K LED, micro LED TV screens. And Samsung showed one at the Consumer Electronics Show 2 years ago, which is shown there. So we believe that the next big things is to think small. And so this is just a recent announcement. Last week, Google has decided to jump into the micro LED arena for their future AR, and that is the acquisition of Raxium, which is a Bay Area company which has been developing gallium nitride micro LEDs for the past 5 years. And like I said, in that case, they are mainly working it for putting messaging and augmented reality in your eyeglasses. But it's really that we now need to think small, and how small. So those LEDs are about 10 by 10 microns, but we believe we can push it further, and we'll show you data that we can go down to a micron. We now think you could even go down to 100 nanometers or so and still get reasonable light out of your displays. So the main material science or semiconductor fabrication problems that we're dealing with micro LEDs are, as you make the LED size smaller, the efficiency decreases quite drastically, particularly below dimensions of 40 microns. In most augmented reality, they want 10 microns or 3 to 4 microns. So we need to solve this efficiency drop problem. Additionally, we need to make all the colors, particularly for the red and the green, from the same material system would make it very easy to integrate, and you could monolithically make the augmented reality chip in a single chip rather than do a pick and place, which is what we do for the LED screen in back of me. And finally, I'll show you some work we did with transparent tunnel junctions. It became very important as we moved to micro LED size to come up with transparent contacts. And indium tin oxide just isn't transparent enough. So some of the work that Abdullah Al-Hassan had done in tunnel junctions, we've now basically portended that over to make it work for 10 microns and smaller tunnel junctions, and with very small voltage penalties. So this one shows you what we were faced at when we first looked at micro LEDs about 4 years ago, was that as you reduce the size from 100 microns here on the horizontal axis to 10 microns, the efficiency would drop by a factor of 2 or more. And so the way we went about solving this is that it looked like the surface defects were the culprit after some studies. So what we had to do is come up with a better passivation scheme. So normally you don't use atomic layer deposition when you make LEDs, but as the sizes became small enough, we found out that plasma-enhanced chemical vapor deposition, which was the usual deposition method to protect sidewalls, was not working for micro LEDs. And that's because it's a fairly aggressive technique. And we determined that ALD was much better because of its superior material quality. It covered up all the pinholes, but also is a much less damaging process. And you can see that visually here. And on the top row is what's the reference LED with no sidewall. And you can see as we go from 100 by 100 micron LED on the right to a 10 by 10, you basically stop getting light out of the LEDs at around 20 microns or so. If you use the standard PECVD silicon dioxide, which works great for 1,000 by 1,000 micron LED, which is what's in your typical light bulb, you could see that even at 60 by 60 and 40 by 40, the light output has dropped drastically. But it was a pretty outstanding effect that one of my graduate students, Matt Wong, observed, was that when we switched to atomic layer deposition, the LEDs remain bright all the way to 10 microns, and as we'll now see, even now all the way to 1 micron. So ALD really helped solve the surface recombination problem we were experiencing at the interface. And initially, we thought it was all surface damage on the sidewall, but we also found out that plasma-enhanced CVD also attacks the indium tin oxide, and the indium tin oxide, which is used for most standard LEDs, is actually being reduced to metallic indium and tin oxides, which are much less transparent. And so that was causing a fairly steep degradation. And as you can see from the XPS here, we're going from indium tin oxide to metallic indium, which was quite surprising. So that basically attacking of the ITO did two things. It decreased the efficiency, but it also decreased the brightness. And that's shown pretty drastically here. As you went from 100 by 100 to 20 by 20, you were getting about a factor of 2 reduction in the efficiency. So basically, we combined the atomic layer deposition with KOH acid treatment to basically demonstrate the first real size independent external quantum efficiency. So what's shown on the left is without sidewall treatment, and the graph on the right shows you that basically after doing the optimized etching and sidewall passivation, we're able to get fairly size independent EQE from 100 by 100 to 10 by 10 and may recover a lot of the efficiency that we lost with the making the LED smaller. So the micro LEDs can also actually be operated now that the size is much smaller, can be operated at actually substantially better frequencies than they were when they were 100 by 100. A little hard to see on the graph on the right, but 100 by 100, our best was about 300 megahertz. But as we reduce the size to 20 by 20 and 40 by 40, we're able to now routinely get 620 megahertz at 3D modulation. Now, you may think that's not very fast, but there are several companies in the Bay Area that want to use the micro LED displays as a spatially multiplexed transmitting devices. So just an array of 100 micro LEDs, in other words, you'd be able to transfer 62 gigabits per second on wafer if you have a spatially localized photodetector system, which is what they plan on doing. So there's some uses for that. Mainly it's for gaming, believe it or not, because that's where Google and Facebook are, believe, the big people will buy. As you know, the current Oculus glasses made by Facebook, one of their biggest sellers, is currently mainly used by gamers. But we're starting to see more use in the displays now in things like industrial manufacturing, where you want to train somebody to build a part. You can actually show them the map of how to put things together. And in that thing, we need to communicate the data back and forth between the display and what's actually going on. So, so the micro LED as a Li-Fi emitter, it's basically serving two functions. Okay, next view graph. So that was all for 10 microns. But what happens when we start making the LEDs smaller than even 20 microns? You could see we have a pretty drastic drop. This was some work from Oliver on the right showing that from 500 to 10 it drops a lot. And then I showed our work on the left, which is said we have it pretty good around 10 microns now. So we thought it would be pretty easy to go below 10 microns, but there's still a lot of challenges. And next view graph. And so what we've developed is we had to develop a new liftoff process for 1 micron LEDs, and where we use a patterned bi-level hard mask, and we do an undercut etch basically with KOH to undercut it to get our 1 micron size. So what's shown here is our 1 micron micro LED. In this one, we're using the ITO as the top contact with a ring. And then the mesa size is about a micron. And what we can see here is we're able to now shrink the dimension now all the way down from 10 microns to 1 micron. And now this is using our best passivation techniques. And you can see the EQE is still dropping now below 10 microns. So we still have our work cut out for us because KOH and ALD is not good enough to recover all the efficiency. But believe it or not, these devices are still pretty bright, even at 1 microns. But we'd still like to recover this factor of 2 of loss in the efficiency. Anyway, just to show you how bright. So this is a single 1 micron LED driven fairly hard. And what you can see is this is in room light. Even though it's only 1 micron, it's still bright enough that you would be able to see it in daylight through some reading glasses. So even though we've lost half the efficiency, there will be applications in micro LEDs for daylight reading and whatnot. Okay, so one of the ways we can improve the efficiency is by basically making a tunnel junction. So instead of going to ITO after the P layer, instead what we do is we put in that gray layer, the N plus gallium nitride. So this is an NPN structure. So there's no ITO in this device. And some of the earlier work from Abdullah showed that on dimensions of order of 5 to 10 microns, you can get, let me back up a bit. Oh, it's not working. It's going forward, not backward. Okay, here we go. So what we showed is that we can get basically the hydrogen, which is passivating the p-type dopant, out of the sidewall by annealing it. And for zero cycle anneals, you can see you pay a big voltage penalty with the tunnel junction with the ITO. But if you anneal it in a three-step sequence where we do an etch and then sidewall activation, we're able to get only about a 0.2 volt penalty for tunnel junction LEDs. But that may sound like a bit of a penalty to pay, but when you look on the right view graph, you can see that the tunnel junction LED, which is in blue, is basically 40% to 30% brighter than the ITO device. So it more than pays off for itself to use tunnel junctions, especially if you're using micro LEDs. So putting that together, what we showed is now for the very small tunnel junctions, we're able to get wall plug efficiencies on the order of 54%, which in current literature is still the world record for a micro LED with very good efficiency because the tunnel junction gives you decent voltage, but also very high efficiency at the lower currents. And what we determined is that the black curve, which is the ITO, shows kind of that low current, bad EQE behavior, whereas the tunnel junctions both show for the 0 cycle and for the 3 cycle show very good efficiencies at low currents. And we've determined that the ITO, just the act of putting ITO on the LED is damaging the LED. Whereas the tunnel junction LED, you basically passivated the surface by growing N-type directly on it. So the tunnel junction is actually more robust, especially at low currents, which is what, for a lot of applications, they want to use current densities lower than 10 amps per square centimeter for near eye display. So that says that the tunnel junction will probably be the preferred technique for several of the micro LED applications. Okay, so let me switch, because we're running a little behind schedule, to the last part of my talk, which is the laser diode research. So, as you know, gallium nitride laser diodes have primarily been used in Blu-ray DVD. So we had to look at other applications to really, truly fulfill the promise of the blue laser. And believe it or not, the biggest application currently for blue laser diodes is laser cinema. That is cinema displays, but also projection displays, office displays. They've been rapidly switching to from old, what I call metal halide-based projectors, to a blue laser which hits a red, green, blue phosphor wheel and is bounced off a MEMS chip. So most movie theaters in China have already started to switch to this. The US only has about 200 cinema, and I'd be willing to bet there's 1 or 2 cinemas in Riyadh that have switched to laser cinema, which gives you much brighter illumination than conventional cinema projectors. But where I think the real promise is to now use the ability of the laser to pulse, and that gives you the ability to do LiDAR. So in the automotive industry, while we're using it for car headlights, and there's a big advantage, safety advantage there, we're also using it for a LiDAR sensor, time-of-flight LiDAR sensor. And so you can do collision avoidance, and integrated with some other detectors, you can even do higher resolution sensing than what the normal radar gives you. And then on the bottom right, we show a concept of Li-Fi networks. We use the laser light source, basically modulate the blue beam at a much higher frequency than the human eye can see. And I'll show you some joint work with CAX and KAUST where we've demonstrated over 6 gigabit per second. And of course, the real promise for the red, green, blue laser is for augmented reality. And that is what Microsoft HoloLens is working on, is the direct lasers spun around a waveguide for direct viewing. So just a little bit of an older view graph, but I just still holds true today, is that lasers really operate quite well at high current densities, whereas the LEDs droop in the blue and the red here, which is shown on the left graph. You can see that the laser efficiency is, while it's quite low at the low current densities, the LEDs basically stop working at around 500 amp per square centimeter. Lasers, on the other hand, once you hit lasing, in this case around 1,000 amp per square centimeter, the efficiency actually increases at higher drive currents. So what that lets you do is basically we can generate the same amount of light with a single one-chip laser source with an epi area of 0.3 millimeters. The same amount of light comes out from that laser source as comes out from 11 millimeters of LED material. And so this is a big advantage in terms of power, but more importantly, it's the size. The size of that laser headlight is 1/4 that of a typical LED bulb. And so what you see is Next view graph, please. Is that laser lighting, when you replace it, that small point light source, is very good for the high beam in your automotive. And so this is a view graph from BMW showing you basically 700-meter range down the road. Each of those white posts in the ground there is 100 meters out. You can see the LED high beam only gets you out to about 100 meters. Now, it turns out if you're in Germany driving a BMW and it's raining, you need about 180 meters to stop. So they don't drive slow in Germany, and so if it's raining, it's pretty dangerous if you don't have laser headlights. So believe it or not, the BMW, a lot of people elect to have the laser headlight on their car because that lets them see that much further down the road. And so laser light increases safety at night, and as I mentioned before, you can do some nice things with the modulation as well. So this is just some recent data showing you that this is a single chip now. It's only 8 by 1,500 microns, so it's a long bar, but fairly narrow bar, showing you that we can get 2 watts of output power from a single chip. Now, this is enough to do a 40-watt light bulb, and that's basically coming from something the size of a grain of sand. So just to show you how it is, this one's about 12% efficiency. So we've improved on some of the efficiency numbers. A little complicated for this audience, but just to show you that efficiencies can be increased by reducing the loss. So we've gone with undoped P waveguides and showing you that we've been able to reduce the threshold current here on the top left graph from about a half an amp to now about 300 milliamps to lasing with good voltages and good loss. Okay, so I'm going to talk a little bit about using porous gallium nitride. So one way we're trying to move the wavelengths into the green is to come up with a better waveguide material to get the longer wavelengths. I was talking with somebody at lunch, and they were saying, why can't I buy a green laser pointer made with gallium nitride? And one of the reasons is you really can't use the AlGaN as much as you could with the GaN to confine the green wavelengths. And so you need a higher index contrast. And so one of the ways we could do that is to etch what's called porous gallium nitride. That is to etch holes in the gallium nitride. And that gives you a higher index contrast because then you have air in gallium nitride. So shown in the curve on the right, we can get a nice confined beam. So basically what porous gallium nitride is shown on the lower right corner is basically we came up with a process where we etch the N plus gallium nitride will etch an oxalic acid, and we'll get a huge array of holes in it, only in that layer. And you can see that the waveguide or mode confinement is about 2.1% there, as opposed to the standard laser structure in the green, which we're only getting about 1.8% with higher loss. So basically, we believe that porous gallium nitride will be particularly favorable for the green. So the student I had modeled that, Ryan, had been working on this for over 2 years. And how do we fabricate the porous gallium nitride? So this shows you we applied a sample in an oxalic acid bath. And if you look at the epi stack, only the layers that are doped heavily N plus will etch. And so if you look at the SEM, as you increase the doping in the gallium nitride, you can see the pore density will increase. And so you'll have a bigger index contrast in the layers only with the N doping. And so that's how we make our porous gallium nitride to get the waveguide. So this one then proves how it works. So this shows you then, this is the first green laser made with porous gallium nitride, showing you a fairly good reduction in the threshold current density from 36 kiloamp per square centimeter to the curve in the red, which is at 14 kiloamp per square centimeter, made with the porous gallium nitride with our optimized batch. Electroluminescence spectrum here is on the left, showing you that you get a nice single wavelength peak out in the green. That sure looked green on my computer, but it doesn't look green on this projector for some reason. But on the lower right corner just shows you the CW far field pattern from that laser. So that was the green color wavelengths. You can also use these lasers for communication. Li-Fi is also known as visible light communication. And so we've been working with KAUST for over 5 years on using modulation of those lasers. Professor Bunoy has done a lot of work on underwater communication because lasers at these wavelengths can transmit for several kilometers in the ocean. And so we've looked at that with Boone. We've looked at car-to-car transportation communications with BMW and other automotive companies, where you have basically your day running lights on and you're able to communicate between cars. And one of the things we found is, as lasers, and shown here, I'd mentioned before that you were in the megahertz range with LEDs, but what you can see when you combine the laser diode in a phosphor system, you can get much faster modulation speeds due to the fact that you're using stimulated emission now instead of spontaneous. And so this was some work, again, with Bunoya and Ahmed Al-Yamani from CAX, showing you that in the first generations, we were able to get 2 gigabit per second straight out of the gate. We then spent the last couple of years on improving that. One way we improved that is we went to narrower ridge designs, but we also went to what's called a semipolar laser design, which will have basically higher gain, higher differential gain than the C-plane. And what we were shown with this particular laser design is that at this, I call it the violet wavelength, we can get even much higher modulation speeds. So this one shows here now that we're able to get 6.8 gigahertz modulation speed, which is basically right at the photodetector bandwidth limit. Differential gain is higher than what we get for C-plane LEDs. Here on the right, the dashed line shows you what you can get with C-plane, but the semipolar lasers are basically giving you almost a factor of 1 order of magnitude higher differential gain. And so this directly led to higher modulation speeds for our laser diodes. This is the eye test diagram for gallium nitride. So if you're from the fiber optic community, this is very similar to what John Bowers would measure in his lab to see the data transmission rate down a fiber. But this is now done in free space. So this is done in a lab with no fiber, just free space communication. And you can see we can get very highest data rate for a single 3 nitride laser diode with on-off keying at 6 gigabit per second. So this is still today one of the fastest modulation speeds for visible light communication. And you can see down here, most of the work has been going on with the LEDs and micro LEDs. They're still down in the 1 gigahertz to 2 gigahertz modulation speed. And so I think the lasers will, for the very high frequencies, as you know, like telecom, and so we should be able to get up to the 50 gigabit per second modulation frequencies at some point. Okay, so in summary then, kind of showed you some advanced photonic applications of gallium nitride. In particular, the blue and the green and are looking quite good. The red micro LEDs need more work. Micro LEDs below 20 microns still need some more work, but we've done a lot of key technology developments, particularly on atomic layer deposition and on tunnel junctions. In particular, tunnel junctions were used to achieve 54% wall plug efficiencies, which is still one of the best reported wall plug efficiencies for a blue micro LED. A corresponding efficiency using an LCD panel with a filtered light is only 5%. So this is a factor of 10 better than the efficiency you get with LCD. It also demonstrated gallium nitride lasers show very high modulation frequencies. You can use them for communication or LiDAR, and I think there's still a lot of future development. As Suji mentioned, we're also developing UV lasers, which are going to require significant development, but there's many medical and other uses for UV lasers in quantum computing that require us to continue to do this development. Thank you.
Thank you, Prof. Steven. Actually, we are honored to have you here in this forum. So I can allow one question, please. Any question before we go to the next talk? So, Prof. Steven, you mentioned that the display speed is 62 gigabits for the gaming. So, what is the maximum that we can get, you think, like in just in a few years or so?
So LEDs, the modulation speed will always be limited by the spontaneous lifetime.
Yeah.
And so we can, so as you decrease the spontaneous lifetime, the speed goes up. And so making a microcavity that is making is one way. So it's between stimulated emission and spontaneous emission. Yes. What's called a superluminescent LED should get you into the gigabit per second range.
Okay. Okay.
So that's one way to increase it. So I don't want to never say never, but you could probably get several gigabits per second from a micro LED.
That will be great. Thank you. Thank you, Steve.
All right, thank you, Professor Stephen. Now, works at the National Center for Nanotechnology and Semiconductors. Please welcome Dr. Abdullah Al-Miqbal.
Thank you everyone for attending my talk. Actually, this was not supposed to be my talk. This is scheduled for Dr. Burhan Saifuddin at KFUBM, but unfortunately, he could not make it today, so I'm going to give the talk on his behalf. Okay, before I start this talk, I would like to thank the PIs of this project who are at this room with us, Professor Shuji Nakamura and Professor Stephen Dimbers for their valuable insight and endless support throughout this project. The talk today is going to be about the future of AlGaN UV photonics on silicon carbide. I'm going to present the applications of the AlGaN photonics and then discuss some of the challenges that we tackled during our work, and then give some details about the growth and fabrication of our UV LEDs, and discuss some techniques to further improve the light extraction efficiency and show some preliminary results about the tunnel junctions we developed. So the applications for AlGaN photonics. There are so many applications for AlGaN UV LEDs. We are mainly interested in one application, which is the water purification in the wavelength range between 260 and 280 nanometer. And AlGaN is the only material that is known now that can span this wavelength range with known are well established in dopants and p-dopants. And with this technology, we are planning to replace the UV lamps. Although the UV lamps has good power and low cost, it has some disadvantage, like it's shown here. It's fragile, slow to light up, and it cannot be tuned. So it's only produce an emission wavelength in a single specific wavelength. So, yeah, as I mentioned, the wavelength between the 260 to 270 nanometer is the wavelength of the maximal germicidal effect for the water and air disinfection. So we are specifically targeting that wavelength. And this effect, the UV disinfection effect, has been known since more than 100 years now, and there is a Nobel Prize given for that discovery. But still, there is no highly efficient, cost-effective solution, and UV LED has the potential to change that. 40 millijoule dose can kill most bacteria and viruses, so we need our LED to produce that power level, and one of the major advantages of the UV LED is that there is no known a UV-resistant bacteria. So this can target and disinfect all bacteria. So another need for UV disinfection is in the medical field, in the hospitals. The hospital-acquired infections results in so many deaths here in Saudi Arabia, United States, and around the world. A study has shown that adding UV disinfection to the disinfection protocol in hospitals can reduce the hospital-acquired infections by 50%. So the material we are using to develop this UV LED is algan. This is the periodic table. Algan is in the group 3 with gallium, and nitrogen is in the group 5, allowing these atoms together produce with a material that can span the wavelength range from 6.1 eV up to 3.4 eV, which is a huge span. With a very good band gap engineering, we can cover almost the whole UV range. So this is the unit cell of the algan. It's a hexagonal unit cell where every cation atom is tetrahedrally coordinated with a one anion atom. The doping, as I mentioned, we have two choices. We have silicon and germanium. Silicon used to work much better than germanium, so it's the most common dopant for algan. For B-type, there is only one known dopant, which is the magnesium. Unfortunately, it has very low ionization efficiency. Less than 1% of the magnesium dopants is actually active dopants. And there is a polarization effect because the gallium and nitrogen has a different electronegativity, and they are arranged in a polar structure. So you have the piezoelectric effect in the algan unit cell. Unfortunately, we cannot grow a single crystal that is defect-free. It's very hard, so we have to work with different kinds of defects, as you can see here. In this example, in this corn example, there is the vacancy defects, the interstitial defect, the edge dislocation, and the grain boundaries. And we need to minimize the concentration of these defects so that we get a high-performance device. This is one example of edge dislocation. The minimum the defects concentration, the higher the performance of the device. One of the major advantage of the nitride system is that it's very highly tolerant against and resistant against defects. The gallium nitride system and its alloys can withstand dislocation densities as high as 10 to 9 or 10 to 8, and gives a high performance regardless of the defects, regardless of the high defect concentration. Unlike other material systems, for example, gallium arsenide, you need to get the defects density as low as 10 to 4 to get a reliable operation of the device. And this is one of the major advantages of this nitride system. And this is a guide, a figure guide on how for the band engineering. As you can see here on your left side, the algan nitride, the nitride system span from 6.1 eV to less than 1 eV. It covers the whole UV range, the visible range, and the infrared range with good band engineering, with good material, and you can achieve a wide range of applications using this material system. And as you can see here in the x-axis with the second y-axis, it's the band gap relationship with the lattice constant is inverse relationship. This is a more detailed band gap guide figure, including the bowing of the alloy. So how do we grow algan material? So we grow it using an MOCVD, that is a metal organic chemical vapor deposition. The picture here shows the system that we have here at KAXT, Clear Room. The sources we are using is ammonia. We are using high purity ammonia for nitrogen source, trimethyl gallium for gallium atoms, and trimethyl aluminum for aluminum as an aluminum source. And surprisingly, this growth happens at atmospheric pressure or near an atmospheric pressure. But despite that, it can yield a very high purity materials with purity as high as 6N. That is the contamination of this, the film is less than 1 part per million, or even below, sometimes below the detection limit of the system. Here in this, in your right side, here is the 3 main mechanisms of the growth. The 3 main mechanisms are the adsorption, the surface migration or the surface diffusion, and then the desorption. It's the responsibility of the grower to optimize this process as to yield the optimal material with the desired morphological and electrical properties. As Shuji mentioned this morning, the cost of the UV LED is still high. We need to bring the cost by at least 2 orders of magnitude for the UV LED to penetrate the UV market. With this cost still not competitive with UV lamps, so there is still work to be done on this. And here is a picture of our UV LED. We chose, one of the most important things here is to choose the substrate. The first choice that we made is we chose the silicon carbide as a substrate because the silicon carbide has the same crystal structure as argon, and it can be easily removed, and with subsequent KOH roughening of the back surface, we can get a high light extraction structure. So that's what my colleague Burhan did, and so that's not the only challenge here. There is so many challenges in this structure as shown here. There is the argon magnesium doping, which is a not highly efficient process. As I said, the efficiency is less than 1% for this process, so this is a major challenge here. The TEM light extraction is also correspond to the ratio of the photons that emits vertically versus the photon emit laterally, and this is one of the limitations for the light extraction. Another challenge is the N-algan, the doping or efficient doping of N-algan. As the algan molar fraction increases, becomes more and more difficult. So we had to solve all of these issues in order to get a highly efficient UV LED. So by tackling most of these issues, as you can see here, we published so many papers on these issues here, and we have filed many patents as well on each one of these. All of the processes here are proprietary processes that was developed in our lab. So with all of this work, we started to get initial results competitive in the 260 to 270 nanometer range, which is a very important range. And that's on silicon carbide. On aluminum nitride, on sapphire, the results is even better. And we estimate that for the silicon carbide, one of the disadvantages of the silicon carbide is the cost. But recently, silicon carbide has moved into the mainstream of EV industry. Tesla, for example, has chosen silicon carbide for their inventors. So with this development, with this recent development, we expect silicon carbide substrate with the mass adoption of electrical vehicle makers, that the silicon carbide substrate would start to come down and be, in the near future, be competitive with the sapphire and silicon. This is a plot of our NL-GaN compared to other groups. As you can see here, our NL-GaN is very, very competitive. It's actually the best so far, from 60 to 80 percent molar fraction ahead of other groups in this range. And that's for the NL-GaN. I'll show you now the buffer layer. So as I said, the choice of the substrates is very important because it can kill or save your project. So the treatment or the surface treatment of the initial growth over your substrate is very, very important. For that, we developed a unique process that make use of the ammonia, high temperature, and the hydrogen flow. And with optimizing the growth temperature, we were able to solve the cracking issue. So our material used to be cracked because of the stress strain between the dissimilar crystals, between the dissimilar lattice constant between the silicon carbide and the AlGaN. But upon optimizing the annealing temperature, we were able to solve the crack issue and obtain crack-free templates for our UV LED. And as you can see here with this treatment, with this surface treatment, the dislocation density of our material, we were able to modulate our strain state of our buffer layer and reduce the defects density down to low 10 to the power of 8, which enable us to make a high efficiency UV LED. As I said, with high dislocation density up to more than 10 to 9, making a high efficiency UV LED is very, very difficult. You need to bring down the defects in density before start working on your structure. So this is the flip chip process developed by my colleague, Dr. Burhan. And as you can see here, once we grow the whole structure, we flip the device, etch the substrate, and then bond it to another substrate and etch the back surface with KOH. And this yields a very high light extraction efficiency structure. Yeah, this is the picture of the device. You can see here the pyramids or the helics. They act as a very good light extractors. These figures or these structure were able to improve the light extraction by at least 2x to 3x. And as you can see here, there is we're showing here the wavelength, the line width of our UV LED. It's very narrow. It's about 10 nanometer. And this is the 265 nanometer LED, the high power that we developed. This is a SEM picture of the back surface. This is the roughening. This is the result of the roughening with the KOH. We don't use a light source for the KOH. It's just a simple dip. You dip it for 45 seconds, and then it becomes like this, very, very good light extractor. And you can see here the improvement just from reducing the defect density by 1 order of magnitude. The power, the output are improved by 2x. And we compared our device, our 278 nanometer device, against commercial devices. As you can see, it outperformed them up to 100 milliamp. These are, our device is in silicon carbide. These devices are on sapphire and aluminum nitride on sapphire. And as you can see, we are very competitive with them. So this is a summary of the flip chip process. without flipping. We improved actually the light extraction or the overall efficiency, the EQE, by almost 20x, just by flip shipping the structure, the device, and roughening the back surface. So this is the process. It's very simple, and it's yield very high light extraction. So how to improve it now? How to improve it further? As I said, we need to bring the cost down and still improve the efficiency. There is two ways to do that. One way is to improve the back surface mirror. Currently, we are using aluminum, which is the simplest mirror. We plan to move to a new mirror, which is based on the magnesium difluoride. The magnesium difluoride has an advantage over the aluminum that is omnidirectional. It's not angle dependent like the aluminum. And we expect that to further double the light extraction of our device. Another technique to further improve the efficiency is the tunnel junction. The tunnel junction will eliminate the need of the B-GaN. B-GaN is absorbing for UV photons, so with eliminating the B-GaN, replacing it with a highly conductive NL-GaN, we can further improve the hole injection efficiency. And as you can see here in this simulation and the initial results to your right side, although the region, the depletion region is high, is thick. It's about 5 nanometer. The surface treatment, we're able to make the tunneling process more favorable. Surface treatment for tunnel junction is very, very important to get this process to be efficient. So this is a comparison showing the magnesium initial results for the magnesium difluoride deposited by E-beam. And as you can see, it has a very high reflectance at 275. It's about 98, so it's very highly reflective for UV photons. Not so many materials are that has this high reflectance at this wavelength. This is a summary of the flip chip process, and you can see here in this to your right hand, we developed so many UV LEDs extending from 250 nanometers up to 320 nanometers, covering most of the UVC range and the UVB range. And so as I said, we need to bring the cost down. We need to still further improve the devices and the wall plug efficiency, because this is what matters at the end of the day. We plan to do that by further optimizing the light extraction efficiency with magnesium difluoride mirror, and with improving the hole injection by tunnel junction. And hopefully with that, we can get the UV LED into market and to compete with the UV lamp in the near future. And with that, I conclude my talk. Thank you so much.
Abdullah, any question for Dr. Abdullah and his presentation? Yes, go ahead, please, Dr. Ridwan.
I can't hear you, sorry.
Please, the mic, please. The microphone here, third row.
Thank you, Dr. Abdullah, for this nice talk. My question is about the cost. So you're saying, like, repetitively that the cost is the main issue with this technology to penetrate the market. So
Yeah.
do you have like a estimate where is this cost focused? Is it like the substrate you're using, the silicon carbide, which is not widely used material, or is it in the processing or efficiency of these LEDs. Can you elaborate on this, please?
Yeah, so it's mainly in the efficiency. As I said, we expect the silicon carbide substrate cost to come down with the mass adoption of EV makers like Tesla and others. So that's not the issue. The main issue is in the efficiency, the overall device performance, the lifetime of the device. Once you increase the wall plug efficiency of the device, the cost comes down, the lifetime goes up. So we need to focus on the wall plug efficiency because that's where the maximum return can come from.
Any other question? Okay, Dr. Abdullah, thank you so much.
Yeah.
Thank you.
Thank you, Dr. Abdullah. Received his BS degrees at Materials Science and Engineering from Purdue University in 2016. With Distinguished Graduate Award, 2 awards in Materials Science and Engineering in Purdue, please welcome Dr. Cheng Shang.
All right, thanks for the introduction, and thanks for the organizers for inviting me here. We can share our development on the material platform that actually enabled the, is this slides? Yeah, thanks for the organizers for inviting me here that I can share with the guys our development on the material platform that enabled the robust high temperature operation of these quantum dot lasers grown directly on silicon, which can be potentially used for monolithically integrated light source for silicon photonics. Yeah, so currently there are about like 5 billion people and about 30 billion devices are connected to the internet these days. So this generates a huge amount of data traffic. And this number is increasing at about like 27% annually. So this calls for a low power, high bandwidth density optical interconnects. And if we can do that from 3.5 substrate, so if we can do that, move from 3.5 substrate to silicon substrate, then we can leverage the well-established CMOS manufacturing, and so that ensure the yield and also the output. So silicon photonics is not only going to be useful for telecom or datacom applications, there are many other applications like optical metrology or sensing, and currently the integrated quantum photonics and also newly emerged neuromorphic photonics are also very hot topics for silicon photonics. So silicon is really good for its optical property to be used as a waveguide, but too bad that silicon is an indirect bandgap that doesn't really emit light so well. So to actually have a light source into these silicon integrated photonics, we actually need to integrate 3.5 light sources onto these silicon chips. The first is that comes is the hybrid integration, where the 3.5 materials and the devices are fabricated separately from the silicon, and then people integrate them together with a basically have to align these things very precisely. So this gives a high cost because of the packaging. Also, you need a 3.5 substrate, and normally they are really in a very large footprint. And next comes in the heterogeneous integration introduced first in 2006. Basically, this is like through wafer bonding technique. So you first bond these 3.5 wafers onto silicon, and then the alignment can be done through lithography. And the light can be coupled evanescently from 3.5 to the silicon waveguide. And these lasers functions exceptionally well. So the data here shows on the bottom right, basically that's the aging result from Intel. They basically age like 150 lasers, like 150 heterogeneously bonded lasers at about 80 degrees C and continuously wave operation. And these lasers, the performance of these lasers doesn't degrade at all after like 25,000 hours. So this is something the industry is looking for. If we can realize this level of reliability for, with these epitaxially grown quantum dot lasers. And that's actually the last, it's the ultimate solution where the light source can be directly deposited onto these silicon photonic chips. In that way, we can eliminate the need for bonding and the need for 3.5 substrate altogether. And also this can ensure a very high yield and also very low cost. But the big problem is, as previous speakers have been talking about it, is the crystalline defects. These are inevitable because of the dissimilarity between 3.5 and silicon from a polarity mismatch, lattice mismatch, and a thermal mismatch. All these mismatches will generate a huge amount of crystalline defects. And because of that, even the best quantum well lasers grown on silicon doesn't work so well. It has a very short lifetime, especially at higher temperatures. So this calls for the need for a quantum dot as a light emitter. Because, as I have bolded there, quantum dots are confining carriers all 3 dimensions. So this makes the carrier very localized, so make them insensitive to the crystalline defects. As you can see from the image on the right, this is basically a line scan of intensity across the identified misfit dislocation from a CL image. And from the intensity profile down there, you can see the extracted diffusion length is about like 500 nanometers. And that number can go to several microns in a quantum well. And because of the insensitivity to the defects, this makes the quantum dot an ideal candidate to be used as a light source when you grow the materials directly onto silicon. The other benefits of using these quantum dots is it has a very low threshold current because these quasi-delta function density states ensures that you don't need to pump it as hard to generate population inversion. The other thing is a low temperature sensitivity. I can see from the bottom left, this is basically a PL spectrum of an as-grown quantum dot, indium arsenide quantum dot grown on gallium arsenide. The energy spacing between the ground state and first excited state is much larger than the KT values of most of the technological relevant temperature range. So this makes the threshold less sensitive to temperature. Ideally, it should be completely immune to temperature change. And the AFM in the inside shows that that's basically how the dots looks like from top down. The other benefit of using this quantum dot is a low line width enhancement factor. So this makes the quantum dot very insensitive to the feedback. Because when you put these lasers in a package, there are going to be many facets and things start to reflect back to the cavity. But because of the low line width enhancement factor, the QD lasers are very basically immune to the reflection. So as you can see that when you reflect 100% power back into the cavity, they still maintain the coherence. But for a quantum well, that coherence starts to collapse just after about like 1.7% of reflection. So this ensures that these lasers can operate without an isolator in the package. And according to Intel, these isolators cost about 30% of the manufacturing costs in these packages. So if we want to realize these nice properties on silicon, the things we have to first solve is the reliability, because these defects in these crystals causes device to degrade drastically. So previously, as we were trying to reduce the threading dislocation density from about 3E8 down to about 7 to 8 E6s per centimeter square, the extrapolable lifetime, which is defined by the doubling the initial threshold current, increased from a few hundred hours to over 100 years at room temperature. But if you age the same laser, basically a Gen 3 laser, at 60 degrees C, that extrapolable lifetime drops drastically from over 100 years to just a few thousand hours. So the temperature acceleration for these degradation processes is drastic. And later, we introduced the P modulation doping in the active region to compensate for the hole loss, especially at higher temperatures, and further promote the reliability back to about 7 years extrapolable lifetime. But this is still far not enough. So Intel aged those lasers at 80 degrees C, and they're looking for something that doesn't degrade at all. So the first step is actually quite simple. We need more tools and more investigation into the physics of degradation to actually make that happen. So basically, the main two tools that we have developed is the first to deal with the lattice mismatch. As previous speakers have talked about, because of the 3.5s are generally much bigger than silicon, when we grow these two together, it generates the massive threading dislocation densities that penetrates through all device layers, and that causes the device to die eventually. And after about like 2 years of investigation onto which type of dislocation filters we actually have to use, we come up with this, we call it asymmetric graded filter, as shown in the bottom left. We sandwich those in-gas dislocation filters to create a grading in terms of both the strain and composition. And then it turns out that these asymmetric graded filters are extremely effective. They're about 99% efficient. And together with the thermal treatment of the initial gas buffer, we're able to get a threading dislocation density lower than 1E6 per centimeter square. And that's done within only 2.55 microns of 3.5. And the defect defects aren't even detectable via many plain view TEMs. So if we want to realize these nice properties on silicon, the things we have to first solve is the reliability, because these defects in these crystals causes device to degrade drastically. So the first step is actually quite simple. We need more tools and more investigation into the physics of degradation to actually make that happen. So The next thing we realized is the thermal mismatch problem, because the existing defects were there to release the compressive stress from the lattice mismatch. But because everything in MBE, everything is grown at a hotter temperature, around like 500 to 550 degrees, as the things cools down, the silicon doesn't shrink as much compared to the 3.5. So this basically makes the strain state change from compression to tension. And as you can see from the image on the top right, the existing defects will start to experience a reverse glide because the stress state is changing from compression to tension. But because of the existence of the active region, which composed of indium arsenic quantum dots in this InGas wells, it's really sluggish for the defect to move with it. Basically, a segment of that defect will be pinned in the active region. As a consequence, there will be misfits on top and bottom of the active region touching those dots directly as a misfit array. So as you can see from the image right down there, the CL image shows that there are many dark lines. That's just because the misfits are touching the active region that cause these non-radiated recombination centers. And the solution is we'll put two trapping layers in the cladding layers of these materials to extend that pinned region so that the form of the misfit will be not touching the active region, actually into the highly doped cladding layers so that the non-radiated recombination rate will be drastically reduced. As a consequence, the CL images lights up. So now we have these two new tools to manage either lattice mismatch and thermal mismatch. So we want to see how these tools actually work in the actual laser devices. Yeah, here's just showing that these trapping layers are very effective in pushing these misfits away from the active region from the cross-section TEM. So then later we grow these three samples. First is the most mature sample we used to have before, which generates that best lifetime we had before. And later we grow these sample B, which introduce those trapping layers, and sample C, where we use this low defect template. As you can see that before we even fabricate these materials into lasers, the room temperature as grown PL signals already shows that sample C is about like 60% more, has 60% more intensity than sample A. This is already very promising. Then later, we fabricate these lasers into this traditional FabriPro lasers and then just test threshold, slope efficiency, and especially the T0, which is the temperature dependence of the threshold current. As you can see that from sample A to sample C, there's about a 40% drop in the threshold current, and the T0 is as high as 167 K. So just combining this low threshold and a high characteristic temperature, we're able to pump these lasers much less harshly at a higher temperature. And that alone will generate a higher, more reliable devices because you're not pumping as hard. And these devices were able to laze up to 108 degrees at that point, and then we have a better stages now. They're laze up to 120 degrees Celsius under continuous wave pumping. So the next is that we actually age these lasers in the Intel aging rack. Then we can take these LI curves at 50-hour intervals continuously. Then as you can see, the sample A, which was the best laser we had before, now died within the 4,000 hours of aging. And previously, it used to have a 7th-year extrapolate lifetime. And by introducing that trapping layers, that increase of threshold drops from 100% down to about 27%. And you use a low defect template, that number further drops to about 11%. And on the top right, that's just extracted threshold and the bias required for 10 milliwatt output change for the best devices we have. As you can see, the threshold is remain relatively flat. So after about like 3.5 years, we finally can put more data points onto that plot, which is the green labels there. So now the best laser we have at 80 degrees C already has a really similar performance as the laser we used to have at room temperature. So this is a significant achievement as we considered it, because we basically this is not just through an iteration of parameters that I see which one is the best. We actually introduce new tools to manage all these defects, and these tools are still at a stage of proof of concept. So they're subject to optimization, but all of these expensive DOEs may be handled to industrial labs where they can just iterate this continuously. And after about 3 years, our extrapolate lifetime changed from about 800 hours at room temperature to more than 200K hours at 80 degrees C. So what's actually next for research, other than just try to optimize all these tools, is what I believe is the deposition in these pre-patterned templates. Because people have been thinking about these degradation is driven by temperature and also driven by the current. But the emphasis of how stress is driving all this degradation is less emphasized. Because without the stress, there's no energy landscape for these defects to actually grow. When you just have non-radiative recombination, the defect will just oscillate locally. But once you start to have stresses, these defects will start to grow. Then by depositing these materials in these well-engineered pattern templates, we can manage these stresses arbitrarily, almost arbitrarily in the in-plane direction, so that we can reduce the driving force for the degradation, and also we can even selectively remove the most detrimental defects, because not all defects are born equal. Some defects are more detrimental to the device performance. The other thing is, lastly, it's also architecture for integration, because we can grow these lasers in the pre-patterned pockets and then have all the waveguides already patterned in the template material, so that in that way we can just butt couple the light into the waveguide. So I believe this is growing in this template is the way that we can actually flatten that aging curve and to make these lasers commercially deployable. So if those were successful, they can benefit not just in the communication, but they also benefit the on-chip LiDAR systems where they need like quantum dot on-chip gain, can also be used for biosensor light sources, even integrated quantum photonics, and even the artificial neurons, where it's the newly emerging like neuromorphic photonics. And for that, I would like to thank you for your attention and open for questions.
Thank you, Dr. Sheen. Any question, please? Any question? Okay, thank you.
Thank you, Dr. Chen. Now, with the manager of the National Center for Nanotechnology and Semiconductors, please welcome Dr. Abdullah Al-Hassan.
Hello, everyone. First of all, I would like to thank my colleagues here at CAX and KAUST for organizing this event. It's my pleasure, actually, to present my work in here. So, do you have slides? Yes, perfect. Another one? Okay, perfect. Yeah, so this work started as a fun idea, honestly. Sure. So, and with the support of Steve, back like 2 or 3 years ago, it became actually a great work, and it's successful. And yeah, I'm going to walk you through it. And first of all, I'm going to give you an introduction about LED. I know that most of here the background is not LED, so I'm going to just give you a little bit about LEDs. So when you talk about LEDs, there are 3 main layers of LEDs to make an LEDs. So we have to have an N layer, a P layer, and an active layer, or the active area. So what's the role of the N or the P and the active layer? So the N to produce the electrons, the P to produce the holes, and to have an active layer to recombine these holes and electrons together to generate photons or light. I'm talking about visible LED now. Prof. Shuji and Steve and Abdullah Al-Muqbil talked about UV. I'm going to talk about now just visible LEDs. So when we talk about the materials, the suitable materials to make LEDs, it has to be reliable materials, a direct band gap, and also the right band gap. We need a band gap that can vary from 2 to 3 AV, approximately. And the great materials for this, to make LEDs, for visible LEDs, is the gallium nitride materials, the aluminum, indium, gallium nitride materials. So the great thing is about it, it's a tunable band gap. You can make your N layer and P layer from gallium nitride, and the active layer is from indium gallium nitride. You vary the indium percentage, you vary the band gap size, or the band gap, yeah. So the problem with this, so theoretically it should vary from violet to red, but in reality it's almost difficult to do it. So this is why we have now something called the green gap. So the green gap is to have a great efficiency of blue-violet LEDs. When you increase the percentage of indium or you go longer wavelengths, the efficiency drops significantly. And this is why it's created now for the commercial LED that right now. It's based on blue LEDs. Blue LEDs converted to white LEDs with phosphorus. And the right figures shows that the efficiency of this is not updated figures, but it's the same trend. So when we combine phosphorus with LED, we have a great efficiency, of course. But when we combine the three main colors, the red, green, blue, we're going to have much better efficiency. But is it possible? A lot of people are working on this, but we don't know yet, actually. So I'm going to talk about something here, the P-GaN. So I believe one of the greatest discovery in the gallium nitride history is actually done by Shuji Nakamura when he figured out the problem with the P-GaN. When we grow P-GaN with the OMOCVD, so there are two methods of growing gallium nitride layers, either with the OMOCVD or the MBE. So when you grow it with the OMOCVD method, the P-GaN become resistive. And the early 1990, I believe, Shuji discovered the problem that the P-GaN is passivated with hydrogen. And to remove this hydrogen from the P-GaN, the P-GaN need to be annealed at high temperature. And this is what he did, and you can see from the figure when you increase the temperature, and the resistivity drops significantly after 600 degree. So now I'm not going to talk about the N-type layer or the active layer. A lot of work been done in that area, in that layers. I'm going to talk about the top layer. So when we have a wafer, complete LED, so what's the right spreading layer to have on top of it? So for example, when we have the top figure, when we have an LED, so we have a P-GaN on top and deposit a contact layer on top of it and try to run the LED, the voltage will be really high. And the current spreading is not that great because of the resistivity of P-GaN. Even after removing the hydrogen, the P-GaN is still resistive. So this is why we need a spreading layer on top of it. We need an N-type layer, highly doped N-type layer, on top of the P-GaN to spread the current uniformly. A lot of choices. I mean, actually, several choices in as a spreading layer. The most famous one is the ITO. Also the zinc oxide. But what about using gallium nitride on top of it? What about using N-type gallium nitride on top of the P-GaN? So people have been doing this for quite time. For the MBE, they found it works. Why it works for the MBE? Because the MBE uses just only a little bit of hydrogen. This hydrogen doesn't passivate the P-GaN. But when we switch to the OMOCVD system, things get changed. So here, a few results from an LEDs or laser diodes with tunnel junction grown by MBE. So we have a great result, an LED in top, a semi-polar LED by Ben Yonke and Aaron Young. We have a VCSEL laser by John Leonard. Also, we have a green LED. All of these shows better performance than an ITO LED. So let's now switch to OMOCVD. Let's now switch to a tunnel junction on top of the P-GaN grown by OMOCVD. So the top figure, it's a really nice study. It shows that time versus annealing temperature. When you increase time and fix the temperature, you can see that the activation of the P-GaN is not that great, and the light is not uniform. When you increase temperature and fix the time, also the same thing. So what they did, they increased both the time and the temperature, but still, it's not as a reference layer. As Steve mentioned, for the micro LED, David from UCSB showed really great result with the tunnel junction when the LED is really small. So the hydrogen can escape underneath the N-GaN from the side. So this is where we came up with this idea. So let's have a large LED now. We need the activation not just only comes from the side, because it's, as shown in the top figure on the right, it's impossible because it's around 40, 50 micron, that's it. Other than that, the hydrogen need to be escaped from the top. So we design an experiment that we have an LED wafer grown by MOCVD, on the one on the left. We deposit silicon dioxide on top of it, a pattern. So what we did actually in this experiment, we varied the spacing between these pillars. So we deposited a silicon dioxide pillars on top of the p-GaN. We varied the size of this pillar, the spacing. So we started from 10 micron up to 70 micron. Also, the opening size, we varied from 2 micron to 5 micron. We grow an N plus GaN on top of this. After that, we remove the silicon dioxide easily by HF only. Etched the mesa of the LED, the right figure. Now we deposited the dielectric so that we can put our contacts on top of it. And finally, we deposited the contacts. So we have the P contacts on top, the N contacts at the bottom. We have a lot of results, but I'm going to show you the final result that we were able to have. So this is the final result. So this is the top figure, the SEM figure. This is the final LED. We have on the top right and the bottom right, we have the IV curve and the wall plug efficiency curve. The ITO is a little bit better than the tunnel junction in the voltage, but overall what matters a lot is the wall plug efficiency. We found that the MOCVD tunnel junction actually had better efficiency than the ITO, and also the other tunnel junction grown by MBE. This is just for record. So this is the end of my, and I'm going to show you just, this is a quick pictures showing the difference between when we vary the spacing. So we have here a reference tunnel junction, top left. So this is, we don't have opening in top of it. So we vary the opening 10 micron, 20, etc. We found that the 10, 30, 20, it's almost the same, but when we increase the spacing, like the 70, the light become not as bright as the 30 or the 10. And also for green, so a reference tunnel junction without opening, we can see that there is some areas it's not lighting. And the tunnel junction with patterns, it has really nice uniform light comes out of the LED. And thank you very much. This is the talk.
Thank you, Dr. Abdullah. Any question? So, Dr. Abdullah, I have a question.
Yeah, sure.
So, when you said that you increase and decrease the band gap energy, so that means you affecting the wavelength. So, did you like calculate how much, like when you put some topping material, and you do like indium and silicon dioxide or silicon nitride, what is the shift that you get from your wavelength?
You mean on top of the p-GaN or on top of the?
And in top of the p-GaN, like the shift, like increasing the band gap or decreasing the band gap. I think you will shift the wavelength. Did you calculate the maximum wavelength or the minimum wavelength?
You mean the pillars on top?
Yep.
I didn't do actually that experiment, but I don't think it's going to have
much
that
difference.
Effect, on the wavelength.
Because in the communication, like indium gallium arsenide, we get much intermixing and much wavelength. Thank you, Dr.
Maybe.
Thank you so much.
Thank you.
Thank you.
Thank you, Dr. Abdullah. He was awarded a doctoral degree in physical chemistry from the University of Mayence. Please welcome Professor Frederick.
Okay, good afternoon, everyone. So we are changing topics a bit. I'm going to talk about emerging photovoltaic technologies. And of course, I would also like to thank very much the organizers for giving me the opportunity here to talk about work that we have recently done at the KAUST Solar Center at the King Abdullah University of Science and Technology. So let's first look at the challenge that we have. And the challenge, I mean, is all very well aware to us. We have an increasing energy demand. And a big part of that increasing energy demand is electricity. So how are we going to cover this increasing electricity demand in the future? Well, one potential way, and probably the only way, is to have photovoltaics to generate electricity. And if you look at the installed PV capacity on Earth, and you see that in 2020 we had around 773 gigawatts of PV already installed. And only last week it was announced that we have now reached 1 terawatt of installed PV capacity. So I would say welcome everyone to the terawatt PV age. With the installation of more and more PV on Earth, the price of electricity generated by PV has significantly come down. So in fact, we have now reached a point which is called grid parity. So electricity generated from photovoltaics is as cheap as electricity that you get from the electricity grid. And when we look at the power conversion efficiencies of silicon PV technology, then we see that with the installation of more and more PV and the drop in the price, in parallel, we had also a significant increase of the power conversion efficiency. And the most efficient devices have now reached power conversion efficiencies of around 26.7%. So no wonder that PV technology, especially silicon technology, is actually the technology dominating the PV market because it's very, very efficient, it's very, very stable, and it's also now very, very cheap. So if you look at what has been produced in 2020, which was around 150 gigawatt peak of PV modules, you see that it's mostly silicon with a bit of thin film technologies such as cadmium telluride and SiC. And actually we have also seen a shift from multicrystalline silicon towards monocrystalline silicon modules. Now the kingdom is very, very fortunate to have a lot of sun. In fact, when you look at how much sun you annually have, it's about 2,000 to 2,500 full hours of sun. When you look at how much energy actually strikes the Earth here in the kingdom, you realize that this translates into 2,000 to 2,500 kilowatt hours per square meter annually. So just for a comparison, this is the equivalent energy of 1.5 barrels of oil per square meter. So no wonder that in the Vision 2030, the kingdom now has started to tap into solar energy as one of the electricity producing technologies. So you see here an image of the Sakaka power plant, the first PV power plant that has been inaugurated here in the kingdom and produces about 300 megawatt of power. And you see also that the prices of the energy, what is called the PPA here, has come down to a few $cents per kilowatt hour. One interesting point to note about the Sakaka power plant is that you not only have stationary PV modules, you actually have modules which are on a one-dimensional tracking system. So the modules track the sun, and with that you increase the energy yield and you decrease what is called the LCOE, the levelized cost of electricity. So you see here that over the last 10 years, the LCOE has significantly come down, and we are now in the range of a few cents per kilowatt hour. So here you see the development of what is called the power purchase agreement price for PV technologies in different countries here in the region. And when we look at the technology that has been installed, then you see that currently the technology is mostly on one-dimensional trackers. So the next step in order to go down with the PPA is to have what is called bifacial PV modules on single-axis tracking. So what is bifaciality of PV modules? A bifacial PV module can basically harvest the sun or light from the front and from the back side. So you see here a photograph, a comparison of a monofacial and bifacial PV module. On the right-hand side, the monofacial PV module. On the left-hand side, the bifacial PV module. And you see that you have transparency at the back, so you can harvest light also from the back, which we call the albedo. With that, you can increase the energy yield by up to 20%. And in parallel, of course, you decrease the levelized cost of electricity generated by this PV technology. Now, how can we reduce the L3E of PV even further? Well, and this is where we have to look at emerging PV technologies. And just as an example, I would like to talk a bit about crystalline silicon perovskite tandem solar cells, metal halide perovskite devices, and at the end also a bit about organic semiconductors used in PV modules. So let's look first at the crystalline silicon perovskite tandem models. Well, so if you just look at a single layer silicon solar cell, then simple physics actually tells us the Shockley-Queisser limit that the efficiency for such a cell is somewhere around 33% power conversion efficiency. So now with recombination mechanisms kicking in, the upper theoretical limit for silicon is actually more around 30%. And when you look at the power conversion efficiency development over the past years, you see that we have now reached around 26% power conversion efficiency for what is called a heterojunction silicon solar cell. So we are getting closer and closer to the theoretical limit. So eventually, this technology has to branch off from just using a single layer PV material to what is called a tandem device structure. And in a tandem device structure, you combine two different PV material systems which harvest different regions of the solar irradiation, and thereby you increase the efficiency. So for a perovskite silicon tandem solar cell, we have an anticipated yield gain of around 20 to 30%. So we do a lot of work in the KAUST Solar Center on making tandem silicon perovskite devices. And you see here two of the examples of recently made devices in the center. On the upper part of the slide, you see a 1 square centimeter silicon perovskite device for which we can reach a power conversion efficiency of now around 28.6%. On the lower end of the slide, you see a larger area, around 3.8 square centimeters. And with larger areas, we have a bit of a drop in the power conversion efficiency, but nevertheless, we reach efficiencies of around 26%, which is quite impressive. So now, in order to be, of course, relevant for installation or implementation into PV modules, we have to upscale this technology to larger areas. So in the KAUST Solar Center, we run a project on combining silicon heterojunction technologies of 6-inch substrates with perovskites into 6-inch perovskite silicon tandem devices. And the technology that we have chosen here is silicon heterojunction because it has certain benefits, which in particular are important here in the kingdom. For example, silicon heterojunction technology has a much better temperature coefficient, meaning that you don't lose as much power conversion efficiency when you go to higher temperatures as you would lose for other silicon technologies. And in fact, devices in the field can easily reach temperatures of around 60 to 70 degrees Celsius. So in the center, we reach around 22.5% power conversion efficiencies for 6-inch silicon solar cells, and on top we put the perovskites. And here we are now optimizing the power conversion efficiencies and also working on encapsulation technologies in order to reach cells which can then be implemented in PV modules. Now, another step in order to increase the efficiency is to make bifacial silicon perovskite tandem devices. So you see here proof of concept of a silicon perovskite bifacial solar cell, which can harvest light from the front and the back side. So now, in order to be commercially relevant, we need to ensure that these devices are also long-term stable. And in fact, we have begun to look at stability tests of perovskite silicon devices. And one of the tests that you have to do in order to commercialize the technology is the so-called damp heat test. And here you see an example of a silicon perovskite solar cell which survived the damp heat test, meaning that the power conversion efficiency didn't drop more than, we didn't have more than 5% loss of performance after 1,000 hours at 85 degrees Celsius and 85% relative humidity. And on the right-hand side, you see a photograph of the encapsulated silicon perovskite solar cell. Now, we also do a lot of outdoor testing at KAUST. We are fortunate to have what we call the New Energy Oasis, where we can test devices in the field. And you see here different technologies that we test at KAUST in our outdoor field. For example, silicon heterojunction technology, perovskite silicon tandem devices, and also single junction perovskite solar cells. And I just want to share with you one of the recent results that we have achieved. Here you see a long-term outdoor testing of one of the perovskite silicon tandem devices that we have tested in the field. And you see here on the right-hand side that for more than 6 months, the device retained its open circuit voltage, and we didn't have much loss in power conversion efficiency, so meaning that the encapsulation protocols that we are applying, they also work for devices which operate outdoors. So let me move on to another emerging PV technology, which is organic semiconductors. So organic semiconductors have recently seen a significant increase in the power conversion efficiency. For many, many years, we were stuck at power conversion efficiencies of around 11 to 12%. And with the development of new materials, so-called non-foreign acceptors, the power conversion efficiency has now gone up to around 18 to 19%. So what is so interesting about organic PV? Well, one point is that when you look at how much carbon dioxide is actually emitted when you create this technology or when you make these PV modules, and you compare it to the CO2 generated per kilowatt hour when you apply this technology, then you realize that it's significantly better than other technologies that you can use to generate electricity. We're not speaking necessarily about coal, but for example also natural gas, nuclear, hydro, and even the other PV technologies such as silicon. So in the center, we do a lot of work on advancing OPV devices, and we cover the entire chain from material development to optimization of single junction OPV devices, and also integration of different material systems in tandem and even triple junction OPV devices. And this is research led in the center by our faculty, Professor Thomas Antopoulos, whom you have seen speaking this morning. And to be a bit more specific about what we're looking at, we're looking, for example, at molecular dopants that can improve power conversion efficiencies of organic solar cells. And here we already reach on small areas efficiencies of more than 18%. We are looking at advanced interlayers, so-called self-assembled monolayers, that increase carrier extraction and with that improve device performance. And we are also looking at integration of different types of material systems into tandem and also multi-junction devices to increase, for example, the open circuit voltage of these devices, which is interesting if you want to use those devices, for example, for water electrolysis, so speaking about green hydrogen generation. Now, we also test our organic PV devices in our outdoor test field, and you can just see here examples of power conversion efficiencies that we have observed in the field. This is before and after encapsulation, so here we have a bit of a power loss when we encapsulate our devices, so we have to further improve our encapsulation technologies, but we could actually show that OPV technology can also be very, very stable outside and can actually last for more than several hundreds of hours, if not even thousands of hours in our outdoor test field. And this is work done at the KAUST Solar Center in collaboration with Professor Daria Baran. So let me summarize what I've talked about today. So silicon perovskite tandem devices are now approaching power conversion efficiencies of more than 30%. While the next step in order to commercialize this technology is, of course, upscaling to larger areas, creation of mini modules, and then implementation into modules. It's very promising that this technology has recently passed the damp heat test, but nevertheless, there are other tests still outstanding. For example, thermal cycling, humidity freeze, potential induced degradation, and also reverse biasing. Organic PV has now reached power conversion efficiencies of around 19%. There's still a lot of material development and also device development required, also upscaling to larger areas. But stabilities of more than thousands of hours have already been demonstrated, yet, of course, on smaller areas and with less power conversion efficiency, typically less than 10%. So at KSC, we do a lot of outdoor testing and evaluation of the performance stability, well, of both actually commercial and also emerging PV technologies. And last but not least, I would also like to stress that there are still a lot of other challenges beyond just increasing the power conversion efficiency. Of course, we have to have a resilient PV technology, especially under the conditions that we have here in the kingdom, which are strong irradiance and, well, very, very high temperatures. At some point, and better sooner than later, we also have to think about recycling of PV, because the example of this Kaka plant is showing you that, well, I mean, there's a lot of PV modules that we may have to recycle in the future, and recycling probably will have to be done on site. There's, of course, soiling of PV modules that we have to address. And with soiling of PV modules, we have a loss of the power conversion efficiency and of the energy yield. And then last but not least, of course, the storage problem, because PV is generating an intermittent electricity. So you have to think about how can you store electricity in order to have a 24-hour supply of electricity when you use renewable technologies such as PV. And with that, I would like to come to the end of my presentation and thank you all very, very much for your attention.
Thank you, Prof. Frederick. If you have any question, please. Yes.
So for the tandem cell, what causes the perovskite instability, and how did you address that?
Okay, so that depends very, very much on the specific perovskite material that you're using. The classical perovskite, the methyl ammonium lead perovskite, is known to release, for example, methyl ammonium. Yeah. So with that, you will have a degradation of the perovskite material. Perovskite materials that have larger band gaps, where you have a mixture of iodine and bromide, or iodide and bromide, they tend to phase separate. So you have to have the right mixing ratio. But the good thing about perovskite is what we realized when we combined with silicon technology is that, well, in the field under higher temperatures, the perovskite band gap actually opens. So you don't need to go to mixing ratios of, for example, bromide and iodide, where you observe these phenomena such as separation, or ion separation, ion migration. So we believe that this technology can actually be very, very stable.
Okay. Thank you. Please, the microphone.
I got a loud voice.
Yeah, it's okay. Thank you so much.
So, wonderful talk. Thank you. I just wanted to ask, how do you do the current matching between the perovskite? This is a tunnel junction between the perovskite and the silicon. So, does that restrict your choice of perovskites to get current matching?
Yeah, so very good question about the current matching. Of course, in a tandem solar cell, you have to be current matched between your front and your back cell. So one parameter that you have is the band gap. So we have to tune the band gap of the perovskite material. And of course, you can also play with the thickness of the different layers. So you have those two parameters basically to optimize. And yeah, somewhere you have to find, the middle way where you are current matched. And so far, we could show that this can actually work quite well.
Thank you. For now, we can have a question in the panel discussion. Thank you, Professor Frederick.
Okay, thank you. Thank you, everyone.
I would like to thank all the speakers for their time and their knowledge. They share with us actually the latest application in advanced photonics. So now we have the panel discussion. Sake of time, we will take a couple of questions or more than that. So please go ahead, Dr. Saad. Please, could you bring the microphone here, please?
Two simple questions to Prof. Steve. Is that he mentioned that the laser light for the front light for the cars will give longer distance, but I mean the effects on the opposite drivers, on the eyes.
Sure. So there's actually no laser light exiting the light bulb because it's a reflective. So it hits the blue laser hits the phosphor, and then the spectrums. So the actual spectrum coming out of the headlight is a white light source. It actually has less glare, and so it's passed all the safety standards in Europe because of the fact that it's not a laser light that's coming out. The laser is down converted into phosphor white light. So that's how we get the safety. It's called reflective mode. That's the number one thing. But you may wonder why it goes so much further, and it's because all that light is coming from a small area, so it's a concentration of étendue. So a point source is a perfect light source, so you can put a parabolic mirror perfectly behind it. So you can think of it as just a much smaller light source. You're able to focus it. It's kind of like when you have a camera and you shrink down the aperture, the pinhole camera. You're able to get a very good focus and basically get parallel beams of white light coming out of the headlight. So that's why you get the distance, and the safety is gotten by the fact that it's down converted laser light.
Is the matrix doable? Matrix headlight, you know, I mean, like now the new car, the luxury new car, they have this matrix. So when there is a driver, they can turn off this light, you know.
Oh yeah, that's a good point. So it's actually automatically auto dims if it sees another car coming.
No, it can detect this object and dim the light on that object only. So if there is someone with the bicycle, it can dim the light on that.
Oh yes, so that's using an AI system that's called driver assisted. I've only seen it in the lab, but yeah. So that concept is the car headlight. If there's somebody in the road, it actually directs more light to that person.
Is it doable for the laser, like the LED? Now it's
now it's LED, but
now it's an LED. But what about the laser?
The laser is actually much easier to steer. So it's just you then have to put some MEMS behind it.
Okay.
So micro, machined mirrors and whatnot.
Okay.
So you could think of it as it's like a projector bulb. You know, you can also turn the laser off if it's hitting a MEMS mirror. You can do what's called a pixelated headlight as well. So that's actually the next step, and it'll actually draw lines on the road for you. So if you've ever been on a highway and you don't see the painted lines, they want to make the headlight actually draw the lines for you to drive and turn this way or that way.
And it's going to become much, expensive.
Yeah, well, sure, but maybe you'll pay. So right now the laser headlight is down to about 800 euros.
Yeah.
So it's expensive. It's $1,000 per car.
I've seen it in the new Range Rover. Yeah. I was just wondering, maybe the headlight just costs like another car, you know?
Yeah.
Yeah, so Prof. Stephen, actually I have a question, because you mentioned in the application that using gallium nitride is Li-Fi. Could you speak about that more, like in the Li-Fi application?
Well, so the Li-Fi is kind of like a technology in search of the real application. So, as I mentioned, Professor Bunoy is doing it for underwater communication because there's no way to do high data rate.
They call it Aquafy.
Yeah, he calls it Aquafy.
Yeah, Aquafy actually. The King Abdullah University for Science and Technology, actually they call it Aquafy.
Yeah, so that's an application where it's limited, but I think Aramco is very interested in mapping the sea floor. If you remember when I was surprised when the Malaysian airliner crashed in the Indian Ocean, which they still haven't really found. The only way they mapped it was with submarines and sonar, and sonar is very slow.
Yeah.
But you could imagine that you can use the laser light to map undersea mapping. So that's one application. But, you know, Suji's always said Li-Fi could do Wi-Fi speeds or 5G speeds. Yes. But, you know, you need line of sight, so that's the main thing. It's just going to be really high. So gaming is one area where you need a very high data rate. Yeah. So I could see it for that. So it's kind of like a technology inserts of the application right now.
Do you think like in 10 years it's gonna see Li-Fi in a real application? I know for sure they have like an phone right now using the Li-Fi technology, and we have detectors. They show it like in last year Las Vegas conference that for technology, and they show that a lot of product using the Li-Fi. But do you think that we're gonna see it like in 10 years in our phones instead of?
I think it could be. But I think we need to get it into VCSELs. So VCSELs could be cheap enough for Li-Fi. Yes. Right now, the edge emitting laser, too expensive for Li-Fi. But if we could, you know, VCSEL, the cost. There's a VCSEL in every iPhone now. Excuse me. There's 500 VCSELs. Yes. So I could see the you know, and it's used for facial recognition, but. They're already talking about doing LiDAR. Yeah. So the VCSEL is already being used for LiDAR in certain phones. It's just a matter of somebody writing the apps. But right now the VCSELs are too slow, so they've got to design the VCSELs for the Li-Fi app. But yeah, I think. Thank you. Just one more thing to add to your phone.
Yeah. Thank you. Any question? Any more question? Yeah, please.
Yeah. So I have a question for Derek. So I just now you showed us a lot of fantastic outdoor tests for solar cells. I think our solar center is trying to tackle this stability and thermal, you know, features for solar cells. So may I ask a question? Do you have to clean the solar cell every day?
It's already on.
Oh, it's already on. Okay, perfect. Yeah. Yes, we do. It's a short answer. I'm not entirely sure if it's every day, but so yeah. And we also look at actually the effect of soiling. Of course, if you don't clean, then you see the effect of soiling, and you have a performance loss basically every day. So it gradually goes down every day.
Do you have any comment? So you show us a huge area solar panel installed at Saudi Arabia. So how can we address this kind of maintenance issue?
That's actually a very, very important topic, soiling. So there is, as you know, I guess, I mean, also there's a company at KAUST looking at solutions for soiling. It's called Nomad. They're using robots that basically have rotating brushes to just brush away the dust on the solar cell modules. You just, have to make sure that, of course, you don't destroy your solar cell modules, but this has been shown that this is, I mean, not really attacking the surface in any way. And basically you have once then per day these robots just driving over the solar panels and removing the dust. And that also is done actually at Sakaka. Such a technology is used there as well.
Thank you.
Any more question? So in that case, I would like to thank the speaker again. It was an honor for us, and thank you again.
Thank you all. And now, time for our last technical discussion for the day. Devices for beyond 5G communication. He is the co-founder of Progmatic and the Chief Technology Officer with over 20 years experience in technology, commercialization, Please welcome Professor Richard Prince.
Thank you very much for the introduction. First of all, I'd like to thank the organisers at CAST and CAUS for the kind invitation to present today. It's an honour to be part of this inaugural forum for future semiconductors. So if I could have the presentation, please. Thank you. So today I'm going to talk about pragmatic semiconductor and localized semiconductor with the teasing headline of can we have a fab in every country? So first of all about the business. So pragmatic semiconductor is 11 years old. It's founded by myself and Scott White, our CEO, in 2010. We've grown now to over 170 staff. We have a base in Cambridge, and we also have a production facility in Sedgefield, which is just south of Newcastle in the northeast of England. We recently closed a Series C investment of $90 million. I'll talk more about that later, but that's allowing us to scale up our production, and that takes our total investment to date to over $150 million. We got a range of shareholders, a combination of professional investors and strategic investors. So they include ARM, which will be familiar to many people here, the world's largest semiconductor IP company. Avery Dennison, it's a Fortune 500 business, historically in materials and adhesives and labels. They're the biggest producer globally of RFID tags. Amcor recently invested in our last round. They're a world leader in sustainable packaging. And Cambridge Innovation Capital, which is a patient capital investor that supports game-changing technologies and world-leading companies. So what do we do at Pragmatic? Well, we're a world leader in ultra-low-cost flexible electronics. We make integrated circuits on flexible substrates. This is our wafer. So it's inherently flexible, and it's inherently low cost. So it's not a silicon wafer. Generally, these are much lower cost than silicon chips, typically 10 or more than 10 times lower cost. Often our applications, these may be cent or even sub-cent. And this brings the potential to connect everything as part of the Internet of Everything, to bring intelligence into everyday objects. We've taken the technology and we've encapsulated this into a unique factory in a box or fab in a box, which really revolutionizes semiconductor manufacturing, enabling localized production with a much lower capital investment than conventional fabs. We've got three areas of our business that are built upon our core technology. So we've got the fab, what we call Flex Logic, that encapsulates all of our process know-how. It's capable of producing billions of Flex ICs a year with a very low cost of capital. We have our first line operational within the UK. We're building our second line, which I'll talk about more later. We have a foundry service, which is enabled by that fab. We provide design kits to allow people to design in our technology, and we then manufacture. It's using standard industrial design tools. It's got a very low non-recurring engineering cost and a very rapid design cycle. And we've done tape-outs with more than 20 different customers. And finally, we've produced the first generation of product, which is an RFID product. It's on a tag like this. So we've replaced the silicon with a flexible circuit. This is an ultra-low-cost RFID, readable with NFC-capable smartphones, and there's a wide range of market use cases for that technology. And we're working with global partners and customers on that, with Avery Dennison, but also a wide range of other people. So why would you want to connect everything? Well, first of all, there's a very well-proven RFID industry based on silicon technology. Companies like Avery Dennison have pioneered this. It's already more than 20 billion tags a year. The proven use cases have clear return on investments. Typically, they are much more efficient stock control. You can reduce the amount of stock, you can reduce theft, and that leads to benefits in terms of increased sales, reduced losses. There's a very significant growth already in this based on silicon. But with our technology, there's a multiplier effect that's possible. So you take the words of one of the leading industry analysts at ID TechX, their CEO, Raghu Das, believes that with our technology, there's the potential to increase the size of this market by an order of magnitude. So rather than billions, we're talking about moving into trillions of connected devices. Our solution we developed is lower cost for two reasons. First of all, the chip itself is intrinsically lower cost, but also the nature of the way we can make these tags, particularly for high-frequency tags, is lower cost as well. We can simplify that assembly. We can actually make the chip bigger. We can remove that bump of silicon and make something that's really ultra-thin with no bump at all. So an example here of a use case, working with the National Health Service in the UK on pathology tests. So in the UK, this was pre-COVID, there were more than 1 billion pathology tests that are done each year, just in England. And it's a very inefficient process. They're manually written labels that are put on every sample. They often get lost. There is no visibility in the testing laboratories of any of the samples that are going to arrive. And there's a lot of plastic packaging that's used in there. So we've worked with the NHS to look at how we can automate this, how we can digitalize this, make it based on RFID in the cloud, fully automated, reducing lost samples, automatic test results back to the patients, reducing the number of doctor visits and so forth. And together we estimate that could be as much as a $500 million saving a year in terms of the operational costs. We're also working on what's called digital deposit return schemes. So there are similar things in Scandinavia and Germany where you have what's called a FAND on a plastic bottle. So take something like this. It would have a deposit associated with it. It might be a few tenths of cents. And when you return that, you get a reward for returning that back to the retailer. So typically that's using barcodes. But actually, the potential with our technology, if I can make the technology work, the art of the demo, hey? There, is you can have a unique ID specific to the individual item that tells you about everything about that individual item, where the plastic was made, how many times, if it's reused, it's been reused, and so forth. And that brings a whole range of information that you can open up about individual items. So we're working on single use. We're also working on reusable packaging, where we actually mold the chip into the bottom of the bottle, and you can count then the number of times it goes through the supply chain, which becomes very important for reusable packaging because you can get things like flavor migration as you reuse bottles. But this is part of creating more sustainable production and consumption within supply chains. Other types of applications, working with leading brands, merging the physical and digital worlds, so you can start to tap on products, you can get information about usage, you can get cross-selling of other products that might be complementary, you can get automatic reordering, loyalty schemes, and also you can get recycling information about specific products. There's also brand protection. So you can get very cost-effective brand protection. You can ensure that the brands that you're buying are authentic. You can identify them down to the individual item again. You can look at things like grey market. So this is where items are sold in one territory. They may be genuine, but they're actually intended for sale in a different territory. So the taxation may have been different. And again, there's opportunities for interactivity for customers, so brands can actually communicate directly with consumers. And then finally, you've got traceability. So Within Europe, for example, there are directives now around pharmaceutical packaging that must be identifiable back to the individual pack. We're working with companies like Shriner Medical on digitalizing that based on RFID so that you can uniquely identify packaging in a very cost-effective way. That allows you to prevent mix-ups. It also makes things like product recalls much easier to achieve. So the areas of what we call Connectic, which is our RFID family, are growing rapidly from traceability, interactivity, authenticity, and sustainability. But we see RFID really as just a first example of the types of products that you can enable with our technology. It's an important proof point for us as a business, and we think it's a very substantial market in its own right, but it's definitely not the limit of what is possible. We've heard a lot at the conference about semiconductor manufacturing, semiconductor supply chains, and the issues that have been faced over the last several years. COVID has been part of that, but as we heard earlier, that is not the entire story. There's been a squeeze on supply chains for many years. And the geopolitics has moved, and there's now a much stronger national agenda in many places to have localized, secure supply chains. You can see this with the growth of new fabs. 29 new silicon fabs that are being built this year. These are huge operations. They're kind of like small cities in their own right. They're very expensive, typically in tens of billions. A surprising thing actually as well is that silicon manufacturing, certainly at the bleeding edge, is now more polluting than automotive. So this growth is actually going to make the race to net zero worse. There are also opportunities as well, though. So in the US, there's a CHIPS Act, which hopefully is about to be passed with a substantial amount of capital subsidy that's been promised to the industry, similar legislation in Europe. And we can see even places that don't have a historic semiconductor industry, like India, are also looking to invest and to secure supply chain for themselves. So what we've developed at Pragmatic is what we call Flex Logic. So it's really intrinsically more sustainable in terms of the approach to manufacturing. So we avoid very high energy processes that are typical for silicon-based semiconductor processing. We don't need to purify silicon at 1500 Celsius. So we've got low temperature processes. We're much more efficient in terms of cycle time. So rather than months, our cycle time is measured in hours and days. We have very short processes. We use inexpensive materials within the process, very resource efficient in terms of water usage, in terms of energy usage, and much overall lower expensive process tools. We've taken process tools that are well established, but they're good enough for the job that we need them to do. This has been recognized by a range of industry awards. Most recently, last year, we were finalists of a very prestigious award for the Royal Academy of Engineering in the UK. We were finalists in that award that was presented by the Princess Royal, Princess Anne. And all of this is protected by hundreds of patents worldwide and also a very substantial body of know-how that we've developed over the last decade. One of the things about Flex Logic is it's very compact. It's a few hundred square meters, so it can be deployed anywhere in pretty much a standard factory environment. It's very capital efficient. As I mentioned, lower production cost, faster cycle time. It doesn't need large numbers of people to operate. So what we see and what our vision is for Flex Logic is to deploy these manufacturing systems around the world so we can provide local supply, often just in time, and we can simplify supply chains and compress them and secure them and meet that demand. And our vision is to be able to provide 100 of these distributed manufacturing lines by the end of the decade. So moving on now to our foundry. So we have what we call Flex IC Foundry. So this is built on our design kit. So we have a range of devices that we produce, things like transistors, diodes, capacitors, resistors, and then we produce from those standard cells. So building blocks like inverters, NAND, NOR, flip-flops, and so forth. They are all characterized and available within our design kit. It's supported by industry standard tools like Cadence and Mentor and Synopsys, and we have models and rules, and we can provide all this to designers both within our company and outside our company to allow them to design in our technology, and then we manufacture on their behalf. And it allows a very agile design and hardware optimization, which I'll build on shortly. But you get very low cost tape out, very fast turnaround using industry standard tool flows. So a typical cycle might look like this. There's a design effort which goes to a tape out, essentially a set of masks which have the graphical design of the circuits on them, are produced, and we can convert those into production wafers within as little as 2 weeks, and provide those within a further 2 weeks to the customers. So it's a much faster cycle time. Typically, if you're looking at doing an ASIC or an application-specific circuit within a silicon technology, you're talking about 6 months. In normal times, at the moment, that's probably 12 to 18 months. And you're much more cautious because the time and the cost is much higher than it is working in our technology. So we offer a range of packages. We work with industry. We also work with universities and other academic institutes to provide prototyping. So that might be a single tape out with just a handful of wafers. Product development, where we do these multiple cycles. So this is different than the way ASICs are done in silicon. We can do multiple rapid cycles rather than try to optimize a tape out over a long period of time, because it doesn't take lots of man years to do the design effort. Or we can work in a multi-design or multi-project basis where multiple partners may share a design. And then as we move into volume wafers, then we're typically in hundreds, thousands, or even tens of thousands of volume. So what's possible in the technology? I guess starting with a couple of highlights of the art of the possible. So on the left-hand side, we were featured on the front cover of Nature Electronics, July 2020, for some work we did in 2019. This was a collaboration with ARM and Unilever. It was a kind of project that was called Plastic Armpit. It's an odor sensor. So Unilever was interested in being able to sense different levels of body odor. So apologies for bringing the tone down. Essentially, these are combinations of volatile organics, and being able to differentiate between different levels of mixtures of volatile organics, because actually humans were doing that job, and they were looking to replace the humans with a machine. So we worked with Unilever and ARM. We took some organic-based sensors, which were trained with the mixtures of VOCs, which had different levels of essentially smelliness. And then those weights were hard-coded into the machine learning engine. So it was optimized for this specific application. And using an analog to digital converter, an ADC, we were able to differentiate between different levels of odor when we use the actual circuit to do that job, based on the hard-coded weights that had been done during training. On the right-hand side, a paper that was published in Nature in July 2021. This was a result of a long-term project with ARM that was codenamed Plastic ARM. This was the goal to implement an ARM processor, a Cortex-M0, in our technology. And we were able to achieve that and produce the most complex metal oxide circuit in 2020. Had more than 18,000 logic gates, more than 50,000 devices. So showing the state of of the art and the art of what's possible in this technology. More recently, we've worked on simpler microprocessors. So we've worked on the iconic MOS 6502. So this particular processor was used by Steve Wozniak in the Apple I. It was also in early Atari's, Commodore 64, Nintendo NES. And we did 2 implementations. So the first one, we worked with the original inventors of the 6502, a guy called Bill Mensch at Western Digital Center. We were provided with the VHDL, the Verilog hardware description language, and we were able to convert that into our design flow, tape that out and manufacture it within 2 weeks. And first time we got more than 80% yield on that design. We did a parallel development with IMEC. IMEC is an internationally leading center for nanoelectronics research based in Belgium. IMEC has developed a more bespoke standard cell library, slightly optimized for the technology. Working with IMEC, we did an implementation that was more power efficient and speed efficient. And that is what I have here in my hand. It says flexible microprocessor that's just floated off the stage. So if we look at complexity and we see the progression in silicon technology, it was nicely described earlier as well, and we've seen several different versions of Moore's law throughout the day. The state of where we are at the moment is around the 70s and 80s for silicon technology, so between thousands, tens of thousands, moving to hundreds of thousands of devices that can be integrated into a single circuit. That's a sweet spot for our technology. We won't be trying to compete with bleeding edge silicon semiconductor technology or 3.5 or anything like that. It's not where we're going to play, but in there we got a sweet spot because silicon is developed by a relentless focus on performance, almost irrespective of cost, irrespective of the environmental impact until very recently. What we've developed is the ability to cost-effectively optimize so you can match the performance of the circuit with the requirements of the technology, the requirements of the application. And that also means that you can optimize the overall cost, and you can do that with a very low environmental impact. So what are some of the other use cases that people are working on now and looking towards the future? So I've mentioned about plastics reuse. It started with single use. It's now moving into reusable packaging. We're working on next generation wearable health patches. So these already exist using conventional electronics. They're generally quite bulky and expensive. So with ARM, we're looking at how do we optimize these? How do we make them optimized for form factor, but also specific to a particular condition? So take something like an arrhythmia that might be indicative of a stroke. So people at risk could wear something like this, a very low-cost patch. You might wear it once a month. And if you detect a problem, you go to the doctor and you get checked out. It's a preventative, low-cost, few dollar solution to something which could eventually cost tens of thousands of dollars if not detected at an earlier stage, or in the worst case could lead to fatalities. Similarly, you can optimize the specific circuit for something like sepsis, which is often a risk after operations. So again, after an operation, you could wear a smart patch, maybe one every day for a week. And if there's an indication, you may go back to the hospital, get checked out, and they can detect this early enough and treat it. We're working on projects looking at food trust, so adding sensing with RF capability, so looking at quality of food throughout its entire life cycle, throughout supply chains. So this can be things like, again, volatile organic sensors, looking at moisture, temperature variations. And similar with IoT sensors. Looking a little bit further out, there's the ability to make capacitive rather than optical fingerprint sensors that are very high resolution. You can do this in silicon, but it's a very, very expensive thing to do because it uses a large area of real estate. We're working on electronic shelf edge labels with partners that can be updated depending on the age of the product, or maybe the environment has changed, so the product has been stored at too high a temperature, or maybe you can extend the lifetime because it's been stored at a low temperature and you can actually extend the use-by date of products. So there's the ability to connect the environmental factors with low-cost sensing and ID capability on things like products and shelf edge labels. We can imagine combining microfluidics with electronics, so you can start to do simple testing on chips, so a lab on a chip. A lot of the technology built into our flexible circuits is also used in MEMS, so there's very good compatibility there. And then even further out, looking at things like brain-computer interfacing. So we have an intrinsically conformal, flexible semiconductor technology. It can be made porous so that fluid can pass through it. It can be made stretchable, so it can be well suited to something like brain-computer interfaces, looking at, can you do rehabilitation? Can you turn on parts of the brain that have maybe stopped working? There's a whole range of other applications in toys and games, in haptics and so forth that I unfortunately can't talk about, but there's a range of customers, internationally recognized customers that we're working with across these areas as well. So at Pragmatic, we developed a technology for making what we call flex ICs, or flexible integrated circuits instead of silicon chips. These are thinner than a human hair, and typically they're more than 10 times lower cost. We've developed a technology, we've wrapped that into Flex Logic, which is a fully integrated, fully automated manufacturing line with a much lower capex and a much lower environmental impact than a traditional semiconductor manufacturing line. We're about to build the first 300 millimeter fab in the UK, which is our next stage of development. And it's really a template for rolling out globally distributed manufacturing lines that can meet local demand and secure supply chains. We have a foundry service that allows this agile design and hardware optimization of circuits, very low design costs, very rapid cycle times. We're talking days and weeks rather than months and years, which is the more typical rhythm for design cycles in conventional technology. And we've done our first product family, what we call Connectic, which is an RFID, ultra low cost, part of the Internet of Everything that allows you to add intelligence to everyday objects. And this allows you to have this potential to connect trillions of items. So finally, I challenge all of you to think about this. Thank you very much.
Thank you, Dr. Richard. An assistant professor in the Electronic Engineering Department at King Saud University, please welcome Dr. Abdullah Al-Ghayhab.
Alaikum. Thank you very much for attending my talk. So today I'm going to talk about designing low-power silicon for IoT connectivity. So I'm going to start my talk by giving the motivation for decreasing the power consumption for devices used to connect to IoT devices. And then I'm going to talk about some of the prior work and the proposed solutions to achieve this goal. And then I'm going to cover some of the recent low-power transceivers design trends. And then I'm going to give one of the examples to decrease the cost of IoT devices and make them ubiquitous, which is designing crystalless connected devices. And then I'm going to finish with the conclusion. So as you know, recently in the past decade, the number of connected devices has exceeded the world population, and it continues to increase. And the biggest increase in the past couple of years was, the majority of that increase was due to the increase in the machine-to-machine communication devices. And that is expected to continue to be true over the next few years too. And the majority of these IoT devices are wirelessly connected to the internet. And as you can see from this figure, more than 50% of these devices either use wireless personal networks or wireless local area networks, such as Bluetooth or Wi-Fi. So in order to support this tremendous growth in the number of devices, we need to make sure that these nodes are efficient. And I'm going to cover two aspects of efficiency, which I think are the most important when it comes to making these devices operate efficiently. The first one is decreasing the power consumption. So this large growth means that we will have to take into account and consider the battery replacements that will have to be done for these kind of devices. So we need to decrease the power consumption and design a power-efficient wireless system to minimize the battery replacement, or even better, if we can design a system that can run on harvested energy. So if you can see the picture on the right of the slide, this was done in collaboration in my previous research group at the University of Michigan with the University of Virginia. So this is a system-on-chip, basically, system that measures biomarks of the human body on a flexible PCB, and then sends these measured data wirelessly to the phone while running on harvested energy from the temperature gradient on the human body. So the second part of the efficiency is the cost and volume. So in order to achieve that, we need to minimize the off-chip component, so basically increasing the integration level of the system. And one of the examples is designing crystallless radios, which I'm going to give an example about of work that have been done and I participated in at the end of my presentation. So these systems cannot just be efficient, but also they have to be reliable. So the limited bandwidth is shared with a rapidly growing number of IoT devices using multiple wireless communication standards. So for example, at the 2.4 gigahertz a licensed band, there are 4 different wireless standards that share the same spectrum. So we need to find integrated solutions for interference rejection, which are efficient enough to achieve a successful communication. So over the next couple of slides, I will show a survey of the recent publications from the industry and the academia in the basically efficient wireless systems design. So on this figure, in the x-axis, it shows the sensitivity of the receiver, and you can see this as the range. So as you go to the left, it's better for the range of the transceiver, basically, or the range that the transceiver can work on, and the y-axis is the power consumption. So the bottom left, basically, corner is the basically best that we can achieve. So you can see that there is almost an empirical line that limits the performance of these wireless systems, except for a small group of basically receivers that have been published recently that operate at the nanowatt range. So the advantage that those basically receivers, or the characteristic that these receivers used to decrease the power consumption, was using or decreasing the data rate. So in order to make this comparison more fair, we can normalize the x-axis by dividing it by the data rate, which makes now the trend more settled, and this basically verifies that there is basically an empirical limitation for the performance of basically wireless systems in terms of power versus normalized sensitivity. We can see here that the basically red squares, which comprise of the standard compliant radios, are almost all clusters above basically 1 milliwatt of power consumption, which is considered high if we want to achieve basically, or we want to design a wireless system that runs on harvested energy. The other aspect is the interference rejection. High interference rejection or good interference rejection is a challenge for low power design. So out of the 180 published papers from the industry and academia, only 40 have reported their interference rejection because most of the time it's not incorporated into the system. And out of those, actually the best ones, like the ones near the edge of the triangle, are only measured for continuous wave, basically interference, which is, as you know, isn't a realistic, basically, assumption, since we have channel fading, which affects the wave power or the received power with respect with time. Another aspect of the trade-off is the frequency of operation of the device, and we can see, which is kind of intuitive, that most of these low-power, published low-power radios operate at below 3 gigahertz, and it's rare to find a device that works at high frequency without exceeding the hundreds of microwatts of power. In addition, also the modulation, most of the low-power radios use non-coherent modulation because it simplifies the hardware since it doesn't have to track the phase of the carrier. So when it comes to the recent trends in wireless nodes or low-power wireless nodes designs, I can say that mostly there are 5 major trends, and I'm going to focus on 3 of them in bold over the next few slides. So the first one is designing wake-up in standards, in existing standards like Wi-Fi, like MBIT and Bluetooth, low energy. And the second one is using backscattering and RF powering. The third one is using passive energy detection front ends with voltage boosting, basically using the Q of a resonant circuit. The fourth one is improving the interference rejection. And the fifth one is co-designing the chip with the antenna to minimize the overall size. And the last one is minimizing the off-chip components in general to increase the level of integration and decrease the cost of the system. And the example I'm going to show in the next, or at the end of my presentation, is a way to get rid of the crystal oscillator, which gives the timing reference in a circuit. So communication through existing or adopted standards like Bluetooth, Wi-Fi, and NB-IoT with ultra-low power radios is challenging, and most of the demonstrated work is not standard compliant, as we have showed in the survey. And the research effort is still underway to bridge this gap using companion radios and back-channel communication, which I'm going to give an example of the work I have participated in the next few slides. So over here we see the gap between standard compliant radios on the top and low-power radios on the bottom. And in order to successfully integrate the wireless nodes, the low-power wireless node is in existing standards, we have to bridge this gap. So one of the techniques they have worked on in my previous research group was using a new technique, which we call the back-channel communication. So the idea is that we can design basically a frequency hopping back-channel receiver by embedding the message into the advertising message that is sent, in this case, in Bluetooth. And so the receiver will detect the message by decoding the advertising, basically order, instead of decoding the every single bit of the channel, which will result in a much simpler hardware and decrease the power consumption of the system while still being able to talk to a Bluetooth low energy standard phone or device. And a second example of integrating wake-up and low-power radios into the standards is a technique that is being integrated in the Wi-Fi standard by its task group. So basically, a low-power wake-up receiver is being proposed as a companion radio in 802.11, and it only requires changes in the existing firmware to generate the wake-up message from existing compatible radios. And so there is also emerging research when it comes to NB-IoT. So NB-IoT stands for Narrowband IoT. It's a cellular, basically, section of the, it's an IoT section of the cellular standard developed by 3GPP. And it's also part of the 5G NR and also of the LTE standard. Most major network providers began to offer this service worldwide over the past 3 years. It coexists with existing LTE and 5G standards. And the emerging research is how to lower the power of a given network complexity of a cellular standard. So everything that makes MPLT act attractive for marketing, like its security and reliability, that it's optimized for low power consumption, that it's integrated in the cellular system, which makes it easy to deploy, that it's extended, it has extended long-range coverage, that it can connect billions of connections per cell, actually makes it more complex for hardware designers. So the security and reliability will require SIM cards interfacing. The claim of a low power consumption is still actually only achieved by duty cycling the device, by doing very long duty cycling, which basically increase the latency in the system. And also it requires an integration with a complex network synchronization protocol. And also it requires very high sensitivity, around minus 120 dBm. And as we see in the previous survey, none of the current low power radios were able to achieve that kind of very good sensitivity. And also the power consumption and so still the state-of-art NB-IoT devices consume a power in the order of milliwatts, which makes it challenging to run it on a very long life battery or on harvested energy, for example. The NB-IoT wake-up was introduced in release 15 about 3 years ago, and it's a wake-up signal to reduce the active power of NB-IoT nodes. But that is still complex from both the analog and the digital hardware. It requires OFDM modulation. And so one of the solutions is to basically co-design the front end with the digital detector to decrease the power consumption. And so this will provide some way of feedback from the digital modem to back to the RF in order to increase the efficiency and decrease the power consumption, basically, of the system. Another aspect is the interference rejection in ultra-low power radios. So RF interference will increase in the future since the limited bandwidth is shared with a growing number of IoT devices using multiple wireless standards. The traditional integrated solutions for interference rejection are either high power and require narrowband channel, or they require discrete components, like, for example, SAW filters, which are bulky and will decrease the level of integration in the system. So one of the techniques to improve the SIR, or basically the interference rejection ratio in RF systems, is by using or avoiding to use active RF gain, basically, or low noise amplifiers, which is the traditional way of designing RF front end, and instead using a mixer first, basically, architecture to save power. And we can still achieve very good selectivity using these techniques with sub-milliwatt power budget by down converting and also by baseband filtering. In addition, we can basically design a very narrowband matching network along with the mixer first architecture to decrease basically the bandwidth of the RF front end. In this case, the dominant power consumption block will become the local oscillator and the buffers connected to the local oscillator. So in this chip, this is the work they have done with my previous research group using a mixer first, basically RF front end to design a wireless sensor node. And you can see in this, using these techniques, we were able to decrease the power consumption to 150 microwatt in the first prototype and still be able to achieve around minus 10 SIR, minus 10 dB, basically SIR at 2 to 3 megahertz adjacent channels. The third trend that I'm covering in this presentation is basically to decrease the off-chip components. And in this case, it's the crystal. So the crystal usually or traditionally is used to give a frequency reference for the wireless radio. However, it increases the cost and the volume of the system, as you can see on this basically commercial BLE transceiver example. And so it will be very helpful to use alternative methods for calibrating the local oscillator without this additional cost and volume. So several attempts have been done in the past to achieve this, either by using on-chip, very accurate on-chip LC reference, which unfortunately consumes high power, so that defeats the purpose of designing efficient wireless nodes in terms of power, or it relies on on-chip relaxation reference, which is has highly variations and high basically jitter. Or the third option is using open loop LC oscillator, which basically has insufficient frequency accuracy for wireless standards, since the frequency will drift away from the desired center frequency. A fourth technique that was proposed by basically using carrier frequency interlocking. However, this method is not standard compliant since it has above allowed error, and also the lag time for this technique is not in the allowed range too. The last technique that I'm listing here is recovering the clock from a received signal. However, the first prototypes that tried to achieve the crystalless communication using this method took hundreds of milliseconds to calibrate the frequency, and also we're not using a standard compliant basically communication, and which also defeats the purpose of designing efficient wireless nodes that are standard compliant. In the proposed solution that I have participated in, we designed a crystal-less transmitter with symmetric over-the-air clock recovery, which is compliant with the BLE standard. The PLL combined lock time was less than 100 microseconds, and also it meets the BLE blocker rejection requirements and also the other requirements as defined by the BLE standard. So the novelty was that we proposed using a frequency hopping back channel receiver to detect the advertising event from a broadcaster, while also rejecting the interference by predefining the expected sequence of channels that the receiver is expected to receive. And so we can see in this measured result that the receiver did successfully lock the second local oscillator, the transmitter basically, local oscillator to the correct frequency, and was able to transmit back basically with a standard compliant packet for 300 microseconds. And this all was achieved without using any crystal oscillator or off-chip reference. So this table summarizes the system performance. The transmitter was running at 600 microwatt. It was also covering the basically BLE frequency band at 2.4 gigahertz. It did achieve excellent adjacent rejection, around minus 27 dB at 3 megahertz. And also the frequency locking time was less than 100 microsecond, and it was compliant with the BLE standard. And this also was a fully integrated solution that didn't require off-chip crystal oscillator or off-chip components. So this was fabricated in TSMC 40 nanometer CMOS, and this is a type photo of the system. So in conclusion, with the coming age of IoT devices, demand on these devices will increase, and it requires us to design low-cost and low-power systems. And in order to achieve this goal, additional development to achieve these specifications with standard compliant is required, which is a really great opportunity for researchers to work on. We presented a couple of silicon prototypes to basically reduce the power consumption of wireless IoT nodes using back-channel BLE receiver. And also we presented basically a crystalless transmitter that can calibrate its frequency from over-the-air packet without requiring any off-chip components. I would like to acknowledge my previous research group, which I have done all of this basically research on at the University of Michigan. And thank you very much.
Thank you, Dr. Abdullah. He's an associate professor of electrical and computer engineering and principal investigator of integrated microwave packaging, antennas, and circuits training lab. His research focused on applications like personal area network, automotive radars, and wireless sensors. Please welcome Dr. Atif Shamim.
Thank you so much for inviting me here, and thank you, the audience, holding the fort at this late hour. I know all of you are tired and sleepy, probably time to get a coffee. So I'm going to be talking more about the conventional RFIC design, the radio frequency IC design. So my research, one of the segments of research in my group is about wireless IC design. So that's, I think, was suitable for this conference theme. So this was supposed to be an animation, but anyways, it doesn't work. So if you start from the leftmost, see Martin Cooper from Motorola. April 1973, he made the first call from the streets of New York to his rival in Bell Labs, telling him that they have made the first successful mobile phone call. And many decades later, fast forward, if you see there are billions of users, almost everybody has a mobile phone. That's the impact of that researcher work. Not only that, but you have now Wi-Fi, GPS, Bluetooth, so you have wireless all around you. If you move forward from where we are right now, you could see that 6G, there's a lot of now work going on going hundreds of gigahertz. Also Internet of Things, people have talked about it, where non-living things are going to be connected with the internet. Also connected cars, with the environment, so V2X, so vehicle to environment communication, and virtual and augmented reality. All of this is present and upcoming future of wireless. And we see the trends here, and some of them have been reflected in the presentations here before me. For example, higher frequencies, people are going towards millimeter waves, sub-terahertz, higher level of integration because you want to make things compact. Of course, lower costs, lighter weights, conformal, as Richard was showing in his first talk, and then enhanced functionality, which means you want to stuff in more and more functionalities into this. Now, microsystems integration, just before I go into the main system on chip aspect, traditionally there have been multi-chip modules, which is on the top. You could see that digital ICs, analog mixed signal ICs, and RF ICs, they all require their separate processes. Digital guys want to stuff in billions of transistors because they want to make compact and large memories and fast processors. RFIC, on the other hand, has different requirements of maybe faster transistors, but do not need a lot of like billions of transistors. So they are done in separate processes, they are packaged separately, and then they are placed on a system, and of course the antenna at the end on a separate PCB which just gets connected to the IC. Now this, of course, takes a large space, and the trends have now been moving towards vertical integration, which is now system in package. System in package, you still have separate ICs for your digital mixed signal RFICs, but they are vertically stacked. And they can share one package. And there could be a number of ways, which means either a ball grid array or solder balls or through silicon vias for that vertical integration. Now, another emerging trend which is becoming popular is system on package, where the package which is traditionally used only as a cover or mechanical protection is now being made functional by embedding passive components in it, like transmission lines, antennas, and stuff like that. ICs being in the package still, but then you make those connections. So these are all microsystem integration strategies, some of them emerging. But the best one, as you know, is the system on chip, where you could combine the digital, you can combine the analog mixed signal RF all on the same chip, right? This is the lowest cost. Richard's not going to agree with me, but the mainstream CMOS, this is the lowest cost because you do not need separate ICs processes, you do not need separate packaging, you do not need interconnects later on, bond wires and all that. So interconnects are through the chip. And the last part here is the antenna, which is traditionally not on the chip. And this is the area where we focus more in terms of research, how to get this antenna also on the chip so that we can get rid of the bond wires and all those interconnects. So the issue is that antennas, as most of you know, is typically the size of the wavelength, which is dependent directly on the frequency. The lower the frequency, larger is your wavelength. For example, the traditional Wi-Fi 2.4 gigahertz ideally should be 60 millimeters long, whereas a traditional IC is only a few millimeters. So how to fit this tens of millimeters long antenna on this, that has been typically prohibiting the implementation of antennas on the chip. Now, with the move towards higher frequencies, like wireless personal area network at 60 gigahertz, automotive radars at 77 gigahertz, imaging systems at 94, with all these systems now, the wavelength is becoming smaller, and then this means that your antenna size can be smaller, and so that you can implement. From the designer perspective, what is the advantage? Of course, traditionally the antenna designers have been separate and the IC designers have been separate, right? So they design their systems based on a 50 ohm boundary matching. So the IC designer or circuit designer says, okay, I have designed it here, antenna designer comes, and then later on, even now, this is the practice, even in your latest phones and all that, a company designs and makes antennas, the other company designs and makes the circuits, and then they meet at this 50 ohm boundary. Now, when you are putting this together on the same chip, on a single chip, you don't really need to care about that 50 ohm boundary, because you could do something which is called as conjugate matching, which results in the maximum power transfer, and then you could do it at the convenience of your, or the flexibility of your circuit design as well as your antenna design, without needing any matching components. And again, you do not need any bond wires and all those for connections. Now, this is a typical stack up for a CMOS process, and this is has a silicon substrate which has a very low resistivity, 10 to 15 ohm centimeters, right? And this is important for digital circuit guys because they want to avoid something which is called latching. And then your transistors, your active layers around poly, and then you have these the metal layers from M1 to the top metal layer, which could be 6 or 9 metal layers, which are all embedded in a thin silicon dioxide layer. So this is very thin. This is like 6 to 9 microns or 10 microns maybe. So the top metal is now in CMOS process is used for on-chip inductors. And people who do IC design, they know that a few decades ago, you could not do inductors on the chip, right? And because they had very poor quality factors. Now they have a special layer which is thicker, so this means that you can do inductors on chip. The reason I'm telling you this is because there's no special layer for antennas right now. So this may change in the future because the foundries may consider to have special layers of that. Now, there are a number of issues for implementation of the antennas with the circuits on this. First of all, the silicon substrate has very high dielectric constants, which means that most of the power will be absorbed by the silicon substrate instead of radiating it out. Typically you want very low permittivity over there. Also, the distance between the metal layers is very small. So for example, if you want to place your antenna on the top metal, and you need to put a ground plane at M1, the distance is only few micron, 10 micron maybe, So this means that you will have opposite currents between the antenna layer and the ground plane layer, so the radiation will cancel out. So this is very inefficient. So it's very difficult to fill. And also there's something called metal fill, which is in IC design, because a small IC is part of a big wafer, the foundries, to have the right stress and strain, put metals on their will. This is fine for the circuit guys, but for the people who are doing antennas, this is not good because if you put a chunk of metal close to your antenna, it will have reflections, radiation interference. So this metal fill, which is a design rule issue in foundries, is a big problem as well. Now, also from the design perspective, the antennas are designed in electromagnetic simulators, which means the way they are designed are based on, the solvers are based on Maxwell equations. So you solve Maxwell equations on those areas, whereas the circuits are designed on nodal voltage and current basis. So their simulators are traditionally different, right? So what does that mean? That if we have to put this EM structure on the chip, this means that you first optimize it in an electromagnetic simulator, and then you export these parameters or design into your chip simulator, then you simulate with your circuit simulator, and then when you create the layout, you have to go back into the EM simulator, especially at higher frequencies, because you want to see if this layout has changed the performance of your electromagnetic structure. And then you have to come back for the final submission of your layout to the foundry because you need to do your chip fabrication. So this back and forth is not very good, and I think there's work going on where people are trying to combine these efforts on the design. And also the layout issues because of the design rule checks. For example, the first time I was trying to do an IC and I was trying to put an antenna on the chip, one of the rules is that the top metal layer could not have more than 30 microns of width. Now, if you cannot have 30 microns of width, it's very difficult to realize an antenna. So the way I solved it, that I had to short this top metal layer with a ground plane so that there's no ESD or electrostatic discharge problem, and later on when the chip is fabricated, somehow cut that connection from the ground plane to find a way around. Also, you could see in this picture the metal fills. I would recommend the people who are doing this single chip design with the antennas and circuits together, co-design, to fill the metal themselves in the chip. And you have the flexibility to do that instead of letting the foundry do that, because now when you control it, you could place the metal fill away from your antenna or on different metal layers. Also, there is now interference issues because now you're in close vicinity of the circuit. So typically if you're designing a low noise amplifier, you have a bunch of inductors, and also you know that inductors also kind of radiate. And if there's an antenna there, that will also radiate. The high permittivity of the silicon wafer means that there's some surface waves which exist there, they will also radiate from the edges. So you really need to be very careful with the layout strategy. One of the strategy which I can tell you is, if you have inductors and antennas close by, you make sure that you do the layout in a way that the direction of current is in opposite direction to each other. So what does that do? This means that if they radiate fields, they will be 180 degrees out of phase in air. So they will cancel out and they will not mutually couple. So you have to do smart tricks to get rid of this in-air coupling or interference. And also in the silicon, you could have guard rings and other mechanisms to resolve coupling through the substrate. Okay, I'm going to show you two examples of a system on chip after this brief introduction. One chip which we have done jointly with the Sensors Lab in Kaus with Professor Khalid Slama is an implantable chip. That's the advantage of a single chip solution which is self-contained, that you could use it for very small areas. This is for glaucoma patients for measuring the intraocular pressure inside the eye. So glaucoma patients have a higher pressure because of which their optical nerve can get hurt. And this is, believe it or not, one of the major causes of blindness in the world. So typically, their pressure is measured through an external device, maybe in months, once in a month. But this pressure keeps on changing every day and they need to measure it. So the effort is going on to have an implantable device which can measure this pressure inside the eye and can send the data wirelessly out. So the idea is very simple. You should have a reader very close to your eye. So you press a button and you could send electromagnetic waves which will power up your chip. Your chip wakes up and it wakes up the sensor. The sensor takes a reading and sends it out, which is picked up by the same reader. So this means that you are doing wireless power transfer and you are doing sensing, and then you're doing like very low power transceivers and everything. The schematic is shown here. There's 5.2 gigahertz. I don't think I can use the laser here, but 5.2 gigahertz is coming in, which is the signal which we send in for wireless power transfer. And on the top block, you see the energy harvesting, which means the rectifier circuit. And so there's an integrated on-chip antenna, which is matched to this energy harvesting unit. And then you have MOS cap storage, which is the transistors. So you store enough power in this MOS cap storage so that it wakes up the sensors and the circuitry and take one reading, and each one of them has a unique ID, it's 4-bit ID, which is sent out through a 2.4 gigahertz transmitter, which is basically also connected to an on-chip antenna. So there's two antennas, and all of this needs to fit into a very small area because this has to be done through a minimal invasive surgery and of course has to be very low power budget. Now, I'm not going to go into details of everything, but I'm just going to show you one thing about the wireless part, which is the transmitter oscillator. Because we are short of space, the way we've designed it is that the inductor of the oscillator, which takes a big space, we've also optimized it to act as an antenna. Now, you know that inductor's job is to retain energy, and the antenna's job is to radiate energy. So, of course, these are two opposite jobs, and if you get one guy to do these two jobs, you have to come up with a trade-off, and which we design in a way that it would do enough for the inductor and would do enough for the antenna. So that red on the last picture on the top, you see the red loop at an M4 layer is the loop inductor, which is part of the voltage control oscillator circuit, but it's also acting as the transmitter antenna. On the receive side, we have a antenna which is basically more like a monopole, but it has inductive loops so that it could match with the high capacitive impedance of the rectifier circuit. Now, all of this, remember, has to be designed in the eye environment, because these are RF components and they behave differently in free space or air, they behave differently inside the human body. So we've created the simulation models which are based on the human eye model, and it is, I think, good enough for short range communication, very short range communication, so the reader is placed very close to your eye. This is the fabricated chip. You could see the whole system fits into a very, very small chip because it has to be implanted. Now, this has to be tested in the eye environment, and unfortunately, none of my students volunteered to have this chip in their eye, so I have to create an artificial eye environment. You could see on the right top where we plug the chip into this saline solution in a plexiglass where this is tested, and despite the complexities of the eye environment and all that, the chip actually worked. And you could see the simulation versus measurement in terms of matching, in terms of radiation. More importantly, on the bottom left, you could see with the external RF power, the electromagnetic energy, we were able to create the 1 volt required inside the chip, inside the eye, to power up your devices. So that was good. Now I'm going to show you another example of a higher frequency point-to-point communication system on chip around 71 gigahertz. And here, what we're going to address is the issue of losses in the silicon substrate for the antennas. So if you look at the topmost figure, you see the stack up. Now, I told you that the antenna could be on the top layer, right? And if I could put a ground plane there, which is like a perfect electric conductor, I can isolate the lossy silicon substrate. So this means that the fields or my energies will not go into the substrate, and I will be able to irradiate. Unfortunately, the distance is too small, so the perfect electric conductor will have opposite current, which is not good. So what we thought about this was, I cannot put a perfect electric conductor, but knowing from electromagnetics 101, I can put a perfect magnetic conductor. The perfect magnetic conductor can reflect in phase. So this is a very good solution, very elegant solution. There is only one problem, which is there is no perfect magnetic conductor in nature, right? So we don't have any PMC. So what we do, we create an artificial magnetic conductor. This is basically periodic structures, which will create a kind of a surface impedance for a narrow frequency band to have in-phase reflection. So you see that the periodic structure, which is a patch, which is periodic boundary conditions, and you see the phase of the reflected wave at the frequency of interest 70 gigahertz, around 71 gigahertz. You see that the phase is 0 degrees, which means that the reflected phase reflected wave has a phase which is in phase with the antenna. So it should be able to boost the performance. And then you have to have a periodic like cells, but you have limited area. So if you look at the chart on the right side bottom, you see that the number of unit cells which you need to have in the antenna, as they increase, the more gain you have, because you are trying to go to that infinite limit. But of course, you are limited with the chip space. You cannot go to infinite limit. So you come up with a compromise where how many number of unit cells you want. On the other hand, the driving circuits here showing you an oscillator at lower frequency. Now here, what we are doing is that we are working with a node which is a bigger node, which means 180 nanometers. And 180 nanometers ideally would not work at higher frequencies. For higher frequencies, you need more and more smaller nodes like 60 nanometers and all that, but they become more expensive, right? So in order to have lower cost, as well as working at higher frequency, what we use is that we multiply the frequency. So you see that there's a frequency doubler. So we create a frequency, and then we multiply it to create a 71 gigahertz in there. So that's the driving circuits here. And this is the fabricated chip. You could see where we have the antenna. You cannot see the periodic structures underneath because they are at a bottom metal layer, but the driving circuits. Another interesting thing which we did to boost the performance for this point-to-point communication system on chip was to have smart packaging, which means an IC has to be packaged, right? So, but how we package it, that we made the package into a lens. So, and this was done through low cost, again, 3D printing methods. You could see on the right, the lens, the IC is sandwiched in between this lens package. And if you look at the bottom table, you would see that going from a standalone single chip, going to with the artificial magnetic conductors, as well as with the smart packaging Fresnel lens, we were able to boost almost 20 dBs of gain, which is huge for this point-to-point communication system on chip. Okay, there's more work we are doing on terahertz, which I can, because of time, I cannot show it, but we have a poster outside where you could see some of the terahertz work there. Now, this is the reference book, my book, from which most of this material is coming up. Conclusion is basically there's a push towards higher and higher frequencies. Millimeter wave and sub-terahertz. So 6G, the bands are not allocated, but it is expected that it will go close to 100 gigahertz or more, right? Silicon CMOS has improved a lot. Now you could have silicon CMOS ICs around 400, 500 gigahertz, which was not possible before. So that's very encouraging because this is the mainstream technology. And the co-design of circuits and antennas on a single chip, as shown, gives you leverage to have optimum performance of both without needing to do matching components. The process is not ideal as I said for antenna implementation, so foundries probably will in future come up with special layers for the antennas like they have done for the inductors. CAD tools are being developed now where you could do EM and circuit simulations at the same time, so that you could do a complete IC design in one simulation package. Again, reflecting surfaces like AMC in smart packaging can really boost the performance of such high integrated circuits. So with this, I'm going to stop here, and I'd like to thank my group. Thank you so much for your attention.
Thank you, Dr. Atif. He's an assistant professor at Cox and the director of the Center of Excellence for Solid State Lighting. Please welcome Dr. Abdullah Al-Harbi.
Hello, Assalamu alaikum. Thank you everyone, and thank you for all people who work on arrange this event. Thank you everyone, and so today I'm going to talk about nano devices for digital transformation. We see the effect of the digital transformation alive today. A lot of people are watching the event through the internet, and thank you. This is through all the development of technology and digital transformation. So the development of technology, not just how to go back. Okay, sorry. So the effective digital transformation is a beer on all our life. For example, the robotics was stationary 50 years ago, and nowadays is movable and do life-saving work. Similar for the first computer was on the whole room, maybe a room like this or even bigger, just to create a simple computer. Nowadays, more advanced computers, more powerful computers on our wrist or on our hand. All of this development in sensing and technology related to the semiconductor device and circuit. Back to pre-CMOS, there was the vacuum tube, where is first computer built. Then the CMOS era, where all innovation and development happened. Later on, and nowadays people is working beyond the CMOS technology. Well, they are working on neuromorphic and quantum computers. All of these advances require in parallel or is led by the development of semiconductors devices and circuit innovation. So for technology, here is a list of technology that enable digital transformation. For example, artificial intelligence, IoT, cybersecurity, robotics, all of them. All of them is share one major thing is rely on semiconductors devices. You cannot enable all this technology, push it further without the development of semiconductor devices. IoT is heavily rely on sensors and communication, cybersecurity, and robotics as well. All of them are related on microcontroller, sensors, and electronics devices. So today I'm going to focus on one of these semiconductors materials, which is 2D materials for next generation. As Professor Shoji mentioned today, the strain relaxation is one of the issues with the growth and 3-5 materials. In these materials, the advantage is they are complete system. Each layer is complete system. That means there is no covalent bond or bond between the layer and the layer underneath. So you will, if you look, for example, graphene is complete system. There is no interaction or covalent bond effect by the layer underneath it. And likewise, and also they are covered wide range of materials from semi-metals, insulators, and semiconductors. So you can build the whole system, a complete system, using these materials. And there are many applications for this material, including RF electronics, sensors, flexible electronics, and this is one of the powerful of these materials because the thickness, as I mentioned, is less than 1 nanometers, most of them. It's just 1 atomic layer thickness. So they are, by default, by nature, are flexible. Logic devices, optical, and so on. So a lot of application and potential for these materials. So when we come to the high-speed applications, they are also cover wide range. So for example, TMDs is good for high-speed, low-power microprocess, Internet of Things, sensing, while for graphene, we can go even to further to terahertz. So these materials is good for low-power applications. So for example, graphene goes to even more than 100 gigahertz. And as I mentioned, the main advantage for this material, they are flexible. So it's complementary to other materials like gallium nitride, for example, for power electronics. This is complementary to be for flexible materials and sensors. So they are operated at high frequency, they are flexible, and their power consumption is very low. So most of these devices are made from a complete system. So the way they made it, they use HBN, another 2D materials, to be able to build these stacks. So, and then they go with the edge contact where the laser is not working. So whereas has to be go through edge, and then you have to make the contact at the side. So this is limit combine this material with other materials, for example, like 3,5 gallium nitride materials. So we need to find another way. So the reason for that, as many previous college talk about the exfoliation today, because the conventional way to do the exfoliation, for example, they do it on a silicon. They rely on the adhesion or strong adhesion between silicon and 2D materials. And when they do the transfer, they have to find a material has a strong adhesion to this 2D material, stronger than silicon. So there is a power or balance of energy between them. So it has to have higher energy. So this one is always, your device is going to be encapsulated by HBN. You cannot, for example, make high-quality devices because you can do chemical etching or so, but you cannot make high-quality devices using assembly. So to overcome this problem, we proposed or developed a new method where we use a thin film of polymer. It's less than 5 nanometers. It's called BFA. So this nanoscale polymer is dissolved completely in water. So by doing this, giving us we are using it as artificial layer. So we're able to build any system regardless the material. So not only be able to build a system, actually we found that at around temperature 85, close to the glass temperature of the BFA, so what's happened is that the adhesion has become even stronger than silicon. We know we don't need to, so it's stronger than silicon. This one enable and promote the exfoliation. The yield has become more than 10 times in size and number of the flake when you do the exfoliation. So to do the transfer, as I mentioned, is dissolve in water. So after you put the stamp to pick up the flake, just a small drop of water using a nozzle, you will be able to transfer it easily and use it for another system. So here is an example where we'll be able to build this material directly on 3,5 materials. So now is what is about the quality of this material? So most people use the conventional way. Are they good? So we actually do two kinds of devices. One is non-encapsulated exposed graphene devices, and the other one is so to show we can make unexposed devices. These devices good for sensing. Most of the sensing to get benefit of this material has to be exposed to the environment or what you want to sense. The other devices is encapsulated to similar to the other devices. And we found actually for the encapsulated devices at room temperature, the mobility is 200 K. So if you see is with the dash line is the phone limit models. At high carrier density, almost we're reaching the phonon limit. And the mobility is high. And for low temperature, the mobility is at more than 100 K. So this is in bar, similar to the other way when they use it, HBN. So this is when at the high level of the graphene devices. So now let's talk more about what is the key requirement to build any electronic system or optoelectronics or RF. What is you have to have large area, growth of the material. The larger is the better. Also, you have to maintain the high performance of this material and to be high security. So for the growth of this material, we study the growth of this material and optimize it to have the layer mode, layer by layer mode, whereas the layer is the start to inoculate and then go all the way and to have a complete sheet or complete film. So after, and we see as the optimal time, for example, for this growth is 4 minutes. So after you're reaching the optimal time when you have a complete monolayer, then the other layers start to be at the boundary of this material. So this is called the layer by layer mode. So this one is, the scale bar is 50 microns, so we can even grow few millimeters. So our limitation is the system. We can actually, if you want to expand it to wafer, is possible. So another one, the performance of this material. So one of the issues a lot of electronics devices, and so regardless of the application, is the variability from device to device. Most of this growth is happening at high temperature, around 800, C 850, so on. So study this effect. We study the effect of the substrate. So due the high temperature and cooling, there's a mismatch, there is a strong adhesion, the substrate is play a major role. So it affect the film. To study this, we prepare 3 films. One is as grow, the second is transferred and annealed at lower temperature, at 250 C. And the third one, just transfer them, and we fabricate the device at the same time, because we just pick them from one place on the substrate and we put it at the edges. So the fabrication go all together. And it's clearly from the IV curve, the variability is reduced for the transfer is, let's say, 3 films, and where there's no adhesion with the substrate. And also, the subthreshold swing is improved, and the on current is increased. Also, we fabricate as a control devices to eliminate even the fixed charge from the substrate on HBN. And for the 300 nanometer oxide, this subthreshold is very good. If you divide it by 10 to go 30 nanometer or 12, so it's going to be around, the thermal limit is 60 millivolts per decay. So as we see, the effect of the interfacial energy between the film and the substrate is play a major role. So from strong adhesion to the substrate, it's a lot of variability, because there is a variability in the strain. The edge of the film is not at the center. And when it's completely free and just transfer film, the variability is much less. The second thing, the last part of my talk is going to be about the security. So security is a major problem and major issue, and everyone is care about secure his data, his needs, his goods, everything. You want it to be secure. So especially nowadays with the chip shortage, a lot of fake chips is coming from everywhere. No one is around it. So people have to have something to secure these chips. Not only chips, even medicines. In fact, when in 10 medical products in developing countries are fake. So that is not just an economic issue, also health threat for people, a human health threat. So to do that, we developed this material. So before I'm going to what we are developing, let's talk about one way to protect your material is using buff, is physical unclonable function. What is that? Is by default is random. By default, from the fabrication process is random. No one can repeat it. Based on physical structure of the material, impossible to clone. Even the one who created cannot clone the same number. He can create another buff, but he cannot clone the same buff, the same number. So from manufacturing process variation, so there are a lot of applications for data protection, smart card, protection goods. So what we did, we tuned the CVD growth of this material. So instead of have layer by layer for good devices, we change the pressure precursor to have island plus growth. So when the growth is start to create islands. The way is creating islands, so you have monolayers. The red one is monolayers. It's just a single layer, while the green is false coloring, is more than one layer. So this one is a random device. When you control it, so you have the growth mode layer plus island. So we test this is a complete randomness. It's complete special randomness. Is not like uniform distribution. Is complete randomness, special randomness. So this one, no one can predict it. If you can, after we control this growth. So even for us, we cannot repeat the same. We can create another buff. We can create another growth with different numbers, but you cannot repeat the same number. So to do this, how to test our buff or our security nanotag? So we create 2D arrays. So this 2D arrays is built on the film, and you can see. By the way, this one, the thickness of this old pixel is less than 1 nano, 0.7 nanometer, the thickness, and the dimension is 2 micron by 2 micron. So after we fabricate this buff or the key, so we stimulate by challenge, which is light source, to have it, and then we measure the emission, the photo emission using CCD camera. It's just so put a light on this material. If you see, it's random. So what we have, the emission is different. So one properties of this material, when it's in one monolayer, is the direct gap. For people who in the physics, direct gap, that means the emission is extremely strong. While in bilayer and more than one layer, the band gap is indirect. So the emission is less by more than, it's around 85% less, more than 85% less. So, and even becomes more than 100 times in some flick. So we measure this one, and one strength of this one, you can use it as a key, you can use it as a random generation, random number generation. If you tune the theta, well, you want to be this to be, after we digitize it, you have a security key, or you can digitize it to tune the theta. Where is the threshold for off and on? Similar to CMOS, you have on and off. So you can generate different numbers. So actually we test this one. If you just, not just the 2D dimension key, if we just took one row, 64-bit, and we test it with all this, with the neighbors, if you know one of them, you need more than 10 to 17 try to predict the other one. This is a huge competition, required huge computation process. So at the end, we saw that continuous advances in semiconductor devices is the key for advancing various technology, either computing or sensing. So in this two-layered material, semiconductors cover a wide range of application, as we saw, it's RF devices, security, and even electronics. We introduce optical security primitive. Is unique physical properties of these 2D materials with the fundamental is make them for securing the value change, especially for chips, like chips or our file is good. This material, as we saw, can be combined with other material system like 3,5 gallium nitride materials to create an innovation application. Thank you very much.
First of all, I would like to thank all the participants in this session for the exciting and informative presentations. So I think I will start from my side and with some questions before we move to the audience. So starting with Prof. Richard. So I'm just asking about the RFID tags that you showed. Compared in terms of cost and efficiency, is it like, I believe it's passive?
It's passive, yes.
So compared to like the traditional that cost like in the market these days, 0.1, 0.2 US dollar in cost. Compared like if you can compare them in terms of cost and efficiency.
So, I mean, typically we're talking about cents and subcent, so that'd be 0.01 dollars or lower. They are they're a sort of hard-coded unique ID. So essentially, they do exactly the same task as a silicon NFC chip in that case.
With much cheaper price.
Yeah.
Okay. And is there any did you notice any limitations of the Flex logic or Flex ICs that you do in terms of compared to other products with using silicon? Like when you work with ARM, as you mentioned, the last project you talked about, do you face any limitations?
For sure, yeah. I mean, I think every technology faces limitations. And I think we're just really at the start of our journey in terms of development. So we're trading off power efficiency against speed and performance, and similarly against kind of noise margin, which has a relationship on the level of complexity, and the degree of integration also plays a part in terms of the overall footprint. So it's well known in semiconductors that as you move to larger die size, your yield will drop. Statistically, that always happens for every technology. So we have to play off all of those different trade-offs. So as I said, we're not looking to try to compete against sort of existing technologies, but provide a different sort of optimization and performance cost.
Have you tried with doing other technologies beside ARM, like doing some low power consumption modules like LoRa or Sigfox, or have you used them or like another means? Like, did you face any problem with power consumption in using your Flex logic or Flex ICs?
Yes. So to answer your first question, we haven't looked at those other technologies yet. There's some improvements that we need to make on power consumption for particular frequencies before we can do that. We have developed a gigahertz Schottky technology. It's in an alpha stage, so it's not yet in full production. But that will allow us to move up in terms of the frequency that we can work in the analog space, in the RF space. Sorry.
Maybe a question to Dr. Abdullah. You mentioned that we need to look for alternative option instead of the local oscillators to reduce the power consumption. But did you investigate any other option that can substitute the current local oscillator, also taking in regard to the cost?
Yes. So what I meant was the oscillators that provide basically the timing reference, not the main RF oscillator. So when we look at those, for example, the crystal oscillators, they're considered to be bulky. They add cost to the system. But the one proposed solution that I discussed in my talk was that in some cases, in some systems, we can design it such that it can calibrate its own local oscillator from the recovered carrier frequency. And in that case, it basically can operate at fairly accurate frequency without requiring an accurate crystal oscillator off-chip. So that's the first part. The second part, it can also optimize the phase lock loop, the PLL. So part of the power consumption in the local oscillator is coming from the feedback loop that calibrates its frequency against temperature variation, process variation, or voltage variation. Also, like time, like noise with time, like random noise, random jitter. So being able to calibrate the frequency with a relatively lower power consumption phase lock loop can also result in a much lower power consumption system. So,
Dr. Atif, just like I would like to know a little bit about the conversion between the SoC and SIP, system on chip or system in package. Is there any like big difference between them?
Yeah, so as I said, system in package, you still have separate ICs, like for different domains, digital, RF, in different processes. It's just they are integrated vertically, so they work in a system in a vertical integration fashion. System on chip, there is one IC, one single chip. So that's the idea of single chip has everything on it. That's the major difference.
You talked about the energy harvesting model that you mentioned on 2.4 gig, I believe.
5 gigahertz.
But I haven't seen any plot like talking about its performance.
So yeah, so there was not enough time to to show all that. Basically, there's an antenna. Of course, the efficiency of the antenna is not very good because it's very small and on silicon substrates less than 10%. The rectifier is 5-stage asynchronous rectifier, which is approximately 45% efficiency. But the whole point was there that we needed a certain amount of energy over a period of time. Over a period of time where the MOS cap, the storage, is completely charged. When it's completely charged, then it can give one reading. So it's a reading on demand. It's not a continuously operating system. So it charges, and when it gets charged, you can get a reading out of it.
And I believe also the last experiment you mentioned about talking about point-to-point communication, which is the 71 to 70 gig.
Yeah.
It will gain a lot of importance in the coming period. As last ITU conference, it was one of the bands that has been discussed to be approved for 5G, which is the above 70 gig.
Yes. So these millimeter wave bands are now used for 5G. Though there's no implementations yet, but their ICs are being done at that stage, and of course 6G will go beyond that. So these bands are increasingly become important and giving us more opportunities for people like us to put more stuff on chip because the wavelength is becoming smaller.
Okay, I think now we move to the audience if there is any question. Okay, I think the mic is in the next table behind that seat.
Oh, thank you. I have actually two quick questions, one for Atif and one for Richard. So Atif, for the implantable chip in the eye, that really was very interesting. Do you consider the biocompatibility of any of the materials that you use there?
Yes, of course. There is biocompatible coating on it. You cannot have this piece of silicon go directly into the eye.
I understand that. That's why I asked the question.
Yeah. So there is biocompatible coating. There were materials which we coated on the chip, and the performance was optimized because the RF components get affected by the coatings, right? So that's why even in the simulation stage we considered the properties of the coatings in the design.
I see. And the quick question for Richard: all your the chips that you showed are all designed in NMOS. There's no P-type there.
That's right. At the moment, we have P-type in research, but not yet in production.
Yeah, I have a very quick question. What I see is the IoT dominating IoT like a phone everywhere in future with this wearables and all this technology that is coming out. So my question is regarding the security of the of all these things, because I'm from Kaust, and we use IoT best technology to start our machine to turn it off. So I think security is very important. So I would like to get the comments from the panel members that if blockchain, which is a very secure network, can be can play a role in IoT devices, is there any kind of future? I would like to get a comment.
So for now, always there is a fight between security and hackers. No one is gonna win all the time. So, and the computing is advances. So as the computing is advances, and we reaching the quantum computers, I hope in near future, you have to find another way. So always, you cannot say something is secure 100% for all your life. Otherwise, the method was used 10 years, is gonna be valid nowadays. So this is my answer.
Anybody has a comment?
Yes. Hello.
Yeah.
One small question to Dr. Atif. Various low power solution that you presented, and you face challenges in the inductor design, high quality factor inductor design, and also with the efficiency of the antenna. So what I would say, we have already ISP technologies available where we could do local packaging to really improve the antenna performance. And we did use that, and we improved our antenna performance, and even as high as 245 gigahertz. And of course 60 gigahertz in all those frequency range. So provided if we use some of the low-cost technology available from ISP Germany, SiGe by CMOS technology. So of course these are the challenges with the CMOS, but they have been very carefully overcome by the SiGe by CMOS technology from ISP Germany.
It is very easy to use a high resistivity substrate,
Yeah.
right? The problem is that you want to be in the mainstream technology, because your bulk of your system on chip is being made on CMOS silicon, right? That's like 90% of your electronics. So you have to be in that mainstream so that your antennas can be mainstream. So using a high resistivity silicon is easy solution, but circuits don't work very well on that because of that latching effect I mentioned, right? So that's why the digital guys who dominate the CMOS industry, they don't
be only on CMOS.
Yeah, they don't like high resistivity silicon. So because the circuits don't work very well on that. So we have to work with them. They're not going to change their process for putting an antenna on the chip. That's the issue.
But at the back end, it does support the CMOS because bipolar and both this stuff could be integrated on a single chip.
It can be, but then these are additional steps, post-processing steps.
There are
of course.
certain
So
involved in
so if you look at the last example where we put these reflecting surfaces, we don't want to add any single step. Okay. Like we want that the chip comes out of the foundry, it is ready to use, right? So because every post-processing step will cost money. And the whole point of bringing the antenna on the chip is to save cost and save space. So you don't want to add steps to it. So I know my group, and I know the literature, a lot of people have done a lot of other things to make efficient antennas, but not in the CMOS process. By the way, in the CMOS process, the last example I showed, we actually went to more than 50 to 60% of efficiency, which is from less than 10% to 50 to 60% efficiency without doing any post-processing steps.
One question to Richard, Dr. Richard. You know, the technology that you presented with, I believe is to make the supply chain more cost effective. I mean, really targeted to make the supply chain more cost effective. My only question is out of curiosity. Are you targeting the mobile domain to use your new technology that your firm is really propagating?
Do you mean, are we targeting to get the technology into cell phones?
Yeah, mobile is
I mean, I think that's possible in the future. I think in the next several years, I think we're not quite at the kind of maturity yet for that integration, but I think it's possible in the future for sure.
So we do hope this could even be targeted to very mobile domain even. What is,
Yeah, and I think one of the things I didn't talk about is one of the big problems with electronic systems as opposed to chips is all of the passives. They're generally a much bigger waste problem than the chips themselves. So there are opportunities to implement passive chips essentially as kind of pseudo interposers. So you can simplify that integration and that kind of glue logic and passive requirements for systems.
Thank you. We have one more question on that side.
Hello. So my question is to Dr. Price. So you presented a brilliant technology in the flexible chips, and you kind of answered my question already. But I want you to elaborate more on how much are we trading off? Let's say price, let's say power consumption. Can you go more on the numbers? That would be a very interesting topic to go over. Also, the other thing would be, can you talk a little bit about how are these flexible chips are being processed, and also for the designers? Are the design rules any different, or are we still designing like, let's say, if we are designing to TSMC or whoever other manufacturer? And thank you very much.
Okay, so I'll start at the end and work my way backwards. So the design flow is very similar, if not identical, to the kind of design flow that you would use for TSMC. We have a process design kit, we have a design rule manual. Provided those are followed, then we can manufacture the particular designs. The kind of the processes we use, the name is intentional. So pragmatic means we make choices around processes that will work. So we don't invent things where we don't need to. So we use a combination of conventional deposition processes like PVD and ALD. We use lithography and we use coating where required, and we integrate that into a full process with very mature, well-established, high-volume manufacturing processes and tools. On the cost side, to a certain extent, the answer to that depends on, it's a little bit of financial engineering. So our cost models are all based on 5-year depreciation. Actually, most of the tools in this kind of process and industry will last for 20 years or more if they're well maintained, which they often are, and then fully depreciated at that point. So the costs we're assuming at the moment are pretty conservative, and you can actually distribute that cost even lower depending on the financial assumptions that you make and the modeling that you do.
Okay. I think we will have one last question here. Yes.
Actually, I have a short question for Professor Abdullah Ohabi. So in your slides, you have mentioned your new material. The mobility of your new material can be up to like 200,000 right, which is a very promising value. I want to know how do you measure the mobility of your material, and also, did you also measure the mobility of the graphene under the same condition? Because as I know, graphene has the highest, like it's claimed to be the with highest mobility.
Actually, the material is graphene. It was as shown, it's graphene. So, and we measure it using the rod model. So the material is graphene. We measure it using magnetic transport as well, and we calculate. We did the measure the magnetic transport quantum Hall, the Fan diagram for a quantum Hall effect, and also we measure this the number you showed using the rod model for graphene.
Okay, thank you.
By this question, I think we end the session. Thanks for all participants and the audience. And I think this is the last session for today, isn't it? Yeah, okay. Looking forward to see you tomorrow then for the next sessions.
As he mentioned, I would like to thank each and every one of you for attending. We appreciate your attendance. We hope to see you all tomorrow.